Good morning, colleagues.
Good morning.
Good morning. Здравствуйте, Дмитрий Владимирович. Рады вас видеть. А звук не слышен. Звук.
Звук
Okay,
слышен.
now it's perfect.
Okay.
Now yeah.
Good morning.
Morning, yeah. So the people just coming. I just look on the counter of persons.
Yes.
Yeah.
We have 2 minutes more.
Yeah, sure, of course. Yeah. So.
Good morning.
Good morning. Погода хорошая, да? Но, правда, уже...
Can we start? Good morning, dear colleagues. We start our session devoted to using of gravitational wave astronomy in elementary particle physics. The first speaker is Valery Domke, probing the scale of grain unification with gravitational waves. So 25 minutes, I will tell you when it will be 5 minutes.
Okay,
Yeah.
thank you. I think you need to stop sharing so that I can share the screen.
It is for organizer, yes?
Yeah, so whoever is sharing the screen now, I think needs to stop sharing because otherwise I cannot. Thank you.
Okay.
Okay, can you see my screen?
Yes.
Okay, perfect. Yeah, so thanks and good morning, everyone. So yeah, the topic of the talk today will be about learning about very high energies, in particular about grand unification using gravitational waves. And the key idea is depicted in this little image here, where you see the history of a universe from very early times. It was all hot and dense until late times with the universe as we observe it today. And the key property of gravitational waves, which makes them different to any other messenger particle that we know, is that even if they are produced at extremely early times, so even if they are produced, say, during cosmic inflation or at these very, very high energies, they can propagate throughout the entire universe, essentially unperturbed. And if we succeed in detecting them today, we can kind of learn about the information that they carry from the process that sourced them at these early times. And this makes them very different to, for example, photons, right, which cannot kind of traverse these early parts of the universe before CMB decoupling without being rescattered multiple times and losing the information of their source. So the question is, can we use this to our advantage? Can we use this to learn about particle physics? And of course, the challenge here is related to this exact same property. The challenge is that precisely because gravitational waves are so weakly interacting, it's also extremely difficult to detect them today, right? And this is kind of a challenge that gravitational wave detectors are facing. So what I'll be talking about today is mainly based on these three papers here with Wilfried Buchmüller, Hitoshi Murayama, and Kai Schmitz. In particular, the last one just appeared very recently. So let me start by giving a very brief overview about the basic properties of cosmic strings. So this is in some sense an old story. So cosmic strings are one-dimensional topological defects which are formed in the early universe in a phase transition. And the simplest example is if you have a U1 symmetry breaking phase transition. So this is the unbroken phase, this is the spontaneously broken phase. And as the web of the field which is breaking the symmetry, so the Higgs field of this configuration kind of goes into different parts of this Mexican hat field, then kind of you form non-trivial field configurations in space, which lead to one-dimensional configurations where kind of along this one-dimensional configuration, the vacuum energy is restored, right? So you have this vacuum energy here at the origin, and everywhere else you reach the true vacuum, so you're somewhere here in this Mexican hat rim. More generally, this happens if you're breaking from some larger group G to some smaller group H, and you produce cosmic strings if and only if the first homotopy class of the quotient group is non-trivial. So once we've formed these type of topological defects, then what happens is they evolve. So they can cross each other, or they can even cross themselves. They can kind of form a loop by crossing themselves. And what happens in these processes is that they split off loops of cosmic strings. And now this loop if you have a cosmic string loop, of course, it's no longer completely topologically, well, I mean, the loop is no longer topologically non-trivial, right? It can pull itself together. So what happens is that these loops emit gravitational waves, and in the process, they shrink, and this is the way the network, this is the main energy loss of the network. You can also have, depending on the details, you can also have emission of particles, but what we'll be focusing on this talk is really the emission of gravitational waves. And what happens here is, contrary to other types of topological defects, so cosmic strings, this energy loss is just such that the fraction of energy which is in cosmic strings is always constant with regards to the total energy of the universe. So they do not overclose the universe, as for example, monopoles would do. So this is the old story. Now, kind of a bit of, when we're now relating this to grand unified theories, we can look at a specific example, which is to start with an SO10 group, break this in an intermediate step down to the standard model cross U1, where the U1 here could, for example, be B minus L, bar number minus lepton number, and then you finally break this all the way down to the standard model. And so now you can ask the question that I was asking before, right? You can check, do we form cosmic strings? And if we look at only the second step of this process, only this step here, then what we see is that, okay, in the end, what we're breaking here is really, we're just breaking a U1, right? We can kind of cancel out the standard model from the quotient group. And so this is exactly the example I had before, right? So this gives cosmic strings. So we would expect this entire process to lead to topologically stable cosmic strings. However, if you don't care about this intermediate step, but you just really look at SO10, quotient group of SO10 in the standard model, then okay, you need to work a bit more, right? But you can show that this is actually in fact trivial. So from this, you would conclude that you do not form cosmic strings, right? But somehow this cannot be, right? Because cosmic strings are really a property of the vacuum monofold of the group structure. It should not depend on kind of what the Higgs web does at some intermediate step, or how exactly you break the symmetry group. So there's a contradiction between these two statements. This was noticed in the 80s, and the resolution of this is that you do form you do form cosmic strings in a setup, but they are not topologically stable. So what happens is that in this first step, you generate monopoles, so zero-dimensional topological defects. And in the second step, you generate the strings. So you end up with the gas of monopoles and cosmic strings. So the cosmic strings would connect with the monopoles. So the cosmic strings would no longer be kind of infinitely long, but they would have ends. And then because they have ends, the string tension pulls them together, and this gas of strings and monopoles actually disappears away very quickly. This was kind of the original thought what was happening here. But now something more complicated, maybe more interesting, can happen if we have a phase of cosmic inflation happening between this first step and the second step, because this would imply that the monopoles are diluted away. And this was, I mean, one of the reasons, after all, for cosmic inflation to be put forward in the first place. And then we generate, in the second step, we generate the strings, but now we no longer have monopoles in the universe. So the strings are seemingly stable. However, they are not perfectly stable because the monopoles are still in the quantum field theory. So they can still be produced non-perturbatively along the course of the string by string of production of pair production of monopoles. And this pair production is the same as what they say, the pair production of electrons in the electric field. This pair production is exponentially suppressed by the mass ratio of the monopole mass and the string tension. So essentially, these are the scales of these two symmetry breaking steps. So if there's a big separation between the two symmetry breaking steps, then there's a big exponential suppression here in the production rate of the monopoles and hence in the decay rate of the strings. And then so these strings become very stable on cosmological timescales, potentially even stable until today. Whereas if these two symmetry breaking scales are very close, then this decay can happen very rapid. So this now leads to interesting consequences for the gravitational wave spectrum of these types of topological defects. So what I have here is just a usual expression how to compute the gravitational wave spectrum of cosmic strings, just for the usual story of topologically stable cosmic strings, following, for example, this review here. And so this here is the energy density. This is the spectrum, so the energy density of gravitational waves per logarithmic frequency interval. And this depends on, okay, so here you have the string tension again, G is Newton's constant. We have the Hubble constant today. And then here, what we're doing here is we're summing over the gravitational wave emission of all cosmic string loops because they are the dominant contributor. So Pn here is the gravitational wave power spectrum of the single loop, where n counts the different harmonics of the loop. And Cn is the number of loops which are emitting gravitational wave such that after redshifting, the frequency that we observe today, so the frequency that shows up on the left-hand side here, is f. So to compute this quantity, we need to do an integral over redshift. We need to factor in the cosmological history, and we need to know at each point in time what is the number density of loops which have a certain length L, because the length of the loop is directly related to the frequency at which it emits once you specify which oscillation mode you're talking about. So the tricky part in the story is then to compute this number density here. And this has been, you can obtain this to some degree analytically. It has been refined by various numerical simulations. And I should also say there's some disagreement between different groups of what this number density is, even in the case of topologically stable cosmic strings. So what we're using here for the limit of stable strings is based on this, based on the simulations, based on this model here. So this is now so if we're just treating stable cosmic strings, you would just have some expression here in radiation domination is, for example, given by just this simple form, which gives you the number densities once you specify the time and the length of the loops. Now, what is different now is that we want to take into account that these string loops can decay with a lifetime which is given by gamma d, right, which was the exponential of the ratio between the two mass scales. And so this, what we get here, the second part is essentially where now this finite cosmic string lifetime enters. So we get an exponential suppression because the loops decay due to monopole production and gravitational wave emission. So you see the gamma d here, right, which is the monopole production, and you see the gamma g mu here. Gamma is just a total emission in gravitational waves. So this is kind of the term describing the emission of the loop. TS here is essentially the point in time when the decay is efficient. So at early times, everything kind of seems to behave just like they would for stable strings. And then at this TS time, kind of things start deviating because the decay becomes relevant. And finally, there's a theta function here, which just indicates that the loop production is in fact only efficient at times before this TS time. Once kind of the loops start decaying, there's no longer any like efficient mechanism to generate new loops. So we can plug everything inside, right? And with this, we now have all the ingredients to actually compute the gravitational wave spectrum. And this is the final result. So what we see here is this omega GW, right? So the gravitational wave spectrum as a function of frequency for different values of the string tension, so for different values of G mu. These black dotted curves is what you would get for stable cosmic strings for these relatively large values of G mu. So these are kind of really, particularly these 10 to the minus 7 to 10 to the minus 9 is really kind of what you would expect for gut scale cosmic string tensions. And you see, in comparison, what you see, the gray shaded regions are exclusion regions from existing or upcoming experiments, right? So there's an exclusion region here from LIGO, and there's an exclusion region here from pulsar timing arrays, the dark gray area. And you see that this dark gray area would completely exclude these large values of G mu, right? And this is the statement that pulsar timing arrays, at least until recently, the statement was that pulsar timing arrays exclude cosmic string tensions down to about 10 to the minus 11, which is the lowest curve here. Now, two things have changed, right? So one is that there's actually pulsar timing arrays now have a hint for a stochastic gravitational wave background, and this is this orange region, and I'll talk about that in a second. But the other thing is that now if we take into account that cosmic strings may not be perfectly topologically stable, this leads to a suppression of the spectrum at lower frequencies, and these are now these colored curves, where this kappa parameter is, again, it's the ratio of the two symmetry breaking scales. So these are strings that are relatively long-lived. These are strings which are more short-lived. And the cutoff is simply an artifact, or the cutoff comes from that kind of this shape of the spectrum is generated from cosmic string loops emitting gravitational waves at different times in cosmic history. And the right-hand side tends to come from early times, and the left-hand side tends to come from late times. So by introducing a finite lifetime of the string network, you cut off the low-frequency part. But this means, for example, if you take this kappa, square root of kappa equals 7 example, so a mass ratio of a bit less than 10, this tells you can have, in principle, you can have huge signals at LIGO while kind of getting absolutely nothing at pulsar timing arrays. And so this is a big discovery space for LIGO, which is kind of not probed by pulsar timing arrays. And then, of course, you can have kind of maybe the most interesting case is that you can kind of see something at both experiments and then kind of confirm by LISA. But the statement I really want to make, that if we're talking about cosmic strings at the grand unification scale, so something like, I don't know, G mu above 10 to the minus 9, this can really be fully probed with the experiments that we have and that we will have very soon. So I mentioned briefly the hint by the pulsar timing arrays. So this is from the nanograph paper, which came out last year. So they're not claiming a detection of the stochastic gravitational wave background, right? So what nanograph is they measure, they look at pulsars in the universe, millisecond pulsars. And so these pulsars send a very regular, because they're rotating, they send a very regular time signal to Earth. And the idea is that if a gravitational wave passes between the pulsar and the Earth, this timing signal will be distorted. And then you claim, or you can use this to look for gravitational waves. Now, of course, there's many things that can distort this time signal, right? You could also have some astrophysical object flying by or something like that. So you have to kind of look at many, many pulsars simultaneously and make sure that these distortions in the arrival times, that if you cross-correlate them over space, that they are consistent with actually seeing gravitational waves. And this cross-correlation over space is what is referred to as what you want to see the so-called helix down curve, which is this blue line here. This is the angular correlation as a function of the angle. And these violin plots are what they've seen. Okay, so they say with high significance, they say, well, they've seen some excess noise in the data, but they cannot claim or disclaim that is consistent with a gravitational wave signal. Okay, so it could be or it could not be. We have to wait. And we did wait, and then what came out just a few weeks ago is data from the POX pulsar timing array, or rather the data has been out for longer. Now what came out is the analysis. And they also, if they perform the same type of analysis that Nanograph did, they also see an excess noise with an amplitude and a tilt, which is consistent with what Nanograph saw, more or less. So these curves here, the yellow and the orange are the Nanograph, and the blue now are the pulsar time, the Parkes data. So they are somewhat consistent. The 2 sigma, they're very well consistent. And this is their version of the Hellingsen-Down curve. Again, not enough significance to claim that they see it, but also by eye you can see it's also not totally inconsistent with it. So again, conclusion is we have to wait. But while we're waiting, we can chase an ambulance. And so we wanted to know how well, if we take this signal, if we take this hint seriously, and if we claim this is a stochastic background, let's see how well it fits with this cosmic string picture, right? I mean, I should also say, it could also, even if it is a stochastic background of gravitational waves, it's much more likely, in my opinion, that it comes from astrophysical signals, supermassive black holes. But let's entertain for a moment the idea that it could be that we could actually be seeing this cosmic string signal and see how well that works. So what we're seeing here is, again, so I'm showing the amplitude and the tilt, and the orange here is the Nanograph. The black contours here are the PTA. So as I said, they are perfectly consistent. And these colored lines here, this mesh of lines is what we get in the cosmic string model for different values of kappa. And here the colors again correspond to different values of G mu. Okay, so we see that there is a sizable region here for like values of kappa of around 8 and a whole range of G mu values, which would be perfectly consistent with the PTA data. So can we, moving forward, will we be able to learn more about this? Will we maybe exclude this idea in the future or confirm it? And so what I'm showing here is the gravitational wave amplitude at LIGO compared to the tilt at PTA, because I think these are really the things that we'll get more data on pretty soon. So at the moment, as you can see from this previous plot, the tilt at pulsar timing arrays is very poorly measured, right? It's really just a measurement of the amplitude. Measurement of the amplitude is pretty good, but the tilt is just not constrained yet. So we need more data for that. But say we measure this tilt and say simultaneously LIGO improves, right? And we measure an amplitude at LIGO. So in this plane, we can see where the Nanograph data and the PPTA data lies, right? This is this contour here. And we can see kind of already that the current LIGO bound, depending on how exactly you do the analysis, rules out a significant part of this parameter space. And LIGO at the sign sensitivity, so this is not even talking about Einstein telescope or LISA, right? But LIGO at the sign sensitivity will already rule out down to here. And this gray region we cannot access in the cosmic string model, right? So if the data in the end ends up in this gray model, then it's something else, but it's not cosmic strings. And here's essentially a zoomed out version of that same plot, right? So with slightly different axes. So here we're looking at the model parameter space now. So we have kappa, we have G mu, and I'm showing kind of how different experiments, different upcoming gravitational wave experiments can probe this type of parameter space, right? So here we see the current LIGO exclusion bound. Here we kind of see what LIGO will be able to do. Here's the pulsar timing arrays, if you consider them as an exclusion limit, and the hint is essentially just at the bottom edge of this orange region. This gray hash region here, I don't want to talk about in detail, but this was kind of our original motivation to study these questions, because it was kind of a gut model which had some very interesting cosmological consequences. So with that, I want to conclude. So what the statement I want to make is that these metastable cosmic strings are actually a fairly generic byproduct of grand unified theories. So it depends on a symmetry breaking pattern, right? But there are plenty of patterns which lead to metastable cosmic strings instead of topologically stable cosmic strings. Essentially, if you want topologically stable cosmic strings, you need kind of an additional symmetry which reprotects them, which however happens, right? This is so it could really be either way. But the interesting observation here is that you can get large gravitational wave signals at all frequencies, and in particular, you can kind of get large frequencies at LIGO, which are consistent with strict stringent bounds at pulsar timing arrays. So this is really kind of a scenario that can be tested with upcoming gravitational wave detectors. And it would allow us really to learn about the highest energies. And what's kind of interesting here is that the way cosmic strings work is that the higher the string tension, the bigger the signal. So you're really probing these scales from the top and not from the bottom, as you would be with a collider type experiment. So the excess noise that we see in nanograph and POX pulsar timing array may or may not be a first glimpse of such a stochastic gravitational wave background. So the amplitude and tilt are compatible with metastable cosmic strings. They're also compatible with supermassive black holes. And I stress that we have not seen this quadrupole signature yet, this Helling-Zadown curve. But I mean, more data is already on record, and I think this is a question of time until this quadrupolar signature will either be detected or refuted. And I mean, I should also say that there's also various more subtle things in the data analysis that probably needed to be discussed. And the recent POX data, I think, did a very good job at pointing out several possible caveats that could maybe lead to fake signals here. Thank you.
Thank you very much. We have time for questions. Please raise hands. I see. Alexander Zakharov, please.
Could I ask a question? Do you hear me?
Yes.
I have a question about slide number 4. You calculated stochastic gravitational wave background for cosmic strings, but there are other sources of stochastic background. What about other sources? And also, you know, there are huge uncertainties in calculation of stochastic background, even in absence of cosmic strings. Thank you.
Right. Let me see if I have. No, I don't think I have a backup slide here. But yes, you're absolutely.
Oh, five. Slide number 5.
Yeah. So you're absolutely right. That there are astrophysical backgrounds, and it depends on the frequency range, right? So as at pulsar timing arrays, right? As I said, the probably most important astrophysical background is supermassive black holes. At LIGO, probably the most important sources will be kind of the solar, like 30 solar mass roughly, black hole mergers, or also the neutron star mergers. And at LISA, it will be a combination of things. So we'll see the tail of the distribution that we also see dominantly peaked at LIGO. But we'll also see things like extreme mass ratio in spirals, white dwarfs, and all these things, right? So there's astrophysical backgrounds in all these frequency ranges. The question is, how big are they, right? And I agree with you that this, sort of the properties of this signal here is that they are essentially isotropic, and otherwise like are kind of Gaussian and unpolarized and very similar to astrophysical signals, right? So if we're looking at extragalactic astrophysical signals, the only way to distinguish these two is by, looking at the tilt, right? This is why I'm stressing so much that kind of we need a better measurement of the tilt at pulsar timing arrays. There's a clear prediction what the tilt should be for the supermassive black hole spectrum. So that's a way to distinguish the two. Or also, I mean, in fact, these amplitudes that we're getting here are so large that they're probably above the astrophysical signals. Now, if G mu is very small, right? If we're at this 10 to minus 11 curve, this is very, very difficult, right? We can, if we're comparing to galactic astrophysical background, we have a chance because simply using that we know where's the position of the galaxy, right? So if we look at anisotropies, even with bad resolution, we can probably distinguish. But if we're comparing this curve to extragalactic black hole mergers, this is going to be very difficult. We have a chance, however, with ET, because the Einstein telescope, we should be able to individually resolve all black hole mergers in the entire observable universe. And then you can subtract, if you can do the parameter estimation, you can subtract, right? So this sounds a bit crazy to me, but apparently people think they can do it, but future will tell. But you're absolutely right that there's large astrophysical backgrounds here, and it's very non-trivial to disentangle them.
Thank you. We have also a question. Maxim Dvornikov, please.
I have a general question. I frequently heard the statement that primordial gravitational waves are generated in phase transitions in the early universe. Is it because it's easier to calculate the emission, or there are some physics behind it?
Well, I mean, I think that's one possible source, right? So, I mean, you can essentially, so what you need in order to generate gravitational waves, I mean, so gravitational wave, right? It's a tensor signal. So what you need is some sort of process, which is, sufficiently violent that it releases really enough energy in gravitational waves. You always have to fight over 1/n Planck factor there. And you need essentially some sort of anisotropies, right? Or some sort of quadrupole moment in order to generate gravitational waves. Otherwise, you just kind of generate scalar modes. And so in the early universe, there's various hypothetical processes, right, which can produce gravitational waves. So inflation is one of them, right? These cosmic strings are another. When people talk about, and I mean, these cosmic strings in some sense are generated in a phase transition. Usually, I think when people talk about gravitational waves from phase transitions, what they mean is kind of the actual process of the phase transition, not so much the potentially formed topological defect. But they're really, I think, talking about like the bubble collisions, like you form a bubble of false vacuum in your true vacuum, and then this bubble expands and collides with other bubbles, right? It's a very violent process and a very anisotropic process. And hence, this is a source of gravitational waves. And this then leads to a different type of spectrum that I'm showing here. The typical spectrum there is just kind of a peak, and it's peaked at an energy scale corresponding when that phase transition happened.
Thank you very much.
Thank you very much again. We have to come to the next talk now. The next speaker is Giorgio Carullo, Constraints on Modified Theory of Gravity from latest LIGO-Virgo black hole ring down observations. Can you share screen? Yes, okay.
Hi, can you hear me?
Yes, okay.
And I assume you can see my screen.
Yes, we can.
Okay, nice. Right, so I should start. So good morning, everyone. So today I'm gonna introduce you to recent constraints on modified theories of gravity that I've derived from the latest LIGO-Virgo observation using a specific phase of the gravitational wave emission, which is called ring down. And so I'll be essentially summarize the results derived in this paper, plus some other unpublished results. So I work at the University of Pisa, and I'm a member of the LIGO-Virgo collaboration. All right, so the content of the talk would be more or less this. So first of all, I'm going to introduce you to a subfield of gravitational wave astronomy, which is called observational black hole spectroscopy. And I'm going to summarize the recent results obtained in this subfield. And after that, I'm going to critically evaluate the results we have derived with the LIGO-Virgo collaboration and introduce a different parameterization, which, as I'll describe, allows to actually place constraints on various classes of modified theories of gravity using these observations. And I'm going to compare them to other experimental bounds. And finally, I'm going to conclude with some unpublished results that we have derived recently on considering Kerr-Newman black holes. Okay, so I'm sure you're all familiar with the fact that we now routinely detect gravitational waves here on Earth using interferometers. And the main source of these gravitational waves are binary black hole coalescences. And the way in which this process takes place is that you have two black holes in a bound orbit. And this orbit shrinks due to the emission of the gravitational waves. So the two objects get closer. And at a certain point, they have essentially emitted away all the angular momentum of the system. So they plunge one into each other and they merge to form a single remnant object. And this single remnant object is essentially a highly distorted black hole. So it's a highly distorted horizon. And this horizon this black hole tends to relax towards its stationary state by emitting a very specific kind of gravitational wave. So it essentially emits all its anisotropies in the form of normal modes. So this distorted object vibrates according to the normal modes of the black hole and relaxes until it reaches equilibrium. So these normal modes are actually damped because it is a dissipative system. So you have an horizon, you have the emission of gravitational waves. And so the signal you get is essentially a superposition of sinusoids times an exponential decay factor, which is this e to the minus c over tau. So what happens here is that you have a discrete spectrum of frequencies and damping times, which controls the gravitational wave emission, which happens in this last phase, which I have highlighted here. So the point of this process is that it's in some sense a simple prediction, in the sense that it's generic enough that we expect this kind of emission to hold also in other theories of gravity. So at order zero, the thing you want to do to compute this signal in modified theories of gravity is that you want to compute the spectrum of normal mode emission in this alternative theory. And also it's sensitive to light ring physics, which means that it's sensitive to curvature scales, which are close to the one of the horizon, so the highest ones that we can reach from experiments. So why do we want to test this emission? What are the questions that we want to answer? Of course, we want to understand, first of all, if you're really observing black holes, because we are assuming that these are black holes, right? But there's not yet a smoking gun proof that these are actually black holes. And also we want to understand things like, is GR the correct description of gravity desired curvature, or are the properties of black holes the ones predicted from GR? And then you can start to ask more, let's say, speculative questions like, can there be any possible quantum horizon effects, etc. All right, so before going into the results, I just wanted to have a brief slide discussing why are we using gravitational waves, and specifically gravitational waves from this phase of the coalescence compared to other experiments. So for example, compared to X-ray binaries. So first of all, so these signals probe the largest curvature regime experimentally accessible, which means that it is essentially the highest energy probes by these coalescences in some sense, from the purely gravitational point of view. And also, one other important thing is that when you want to test gravity, you have to be really sure that you are not missing any physics due, for example, to astrophysical systematics, because otherwise this can give you a bias in your estimation. So you can mistake possible mismodeling of astrophysical effects for violations of gravity. And one important thing is that gravitational wave ring down tests, especially with LIGO and Virgo, are actually clean probes from this point of view. So you know that things like accretion, magnetic fields, electric charge are not expected to play a role. And actually, if you find that these would play a role, that would be a huge discovery in itself. And there is a nice review from Barauce, Cardoso, and Pani if you're interested in this. All right, so it's not just me that's I'm interested in this kind of measurement. We, as a LIGO Virgo collaboration as a whole, are quite interested into this kind of signals, and that's why recently we published the first catalog of ring-down only observations. So the first catalog of signals which focuses on this specific emission, and there is a summary of the properties, so the remnant masses and the remnant spins of these black holes. And of course, there's a lot of information here. We did various kind of tests. Various kind of tests that there's not only ring down observation. Of course, we did also many other tests. But the thing I want to highlight here is the number of signals we are considering. So these are 17 out of the 50 total events, which means that they're just much more than 15 and 14 when it comes to testing gravity with the ring down emission, because there seems to be some kind of shared knowledge that maybe ring down was observable in the first event, but not really in the others, which is just not true, because we now observe confident signatures of gravitational waves, of ring down in gravitational waves from essentially 1/3 of the total events. And the only results I'm bringing from that paper is this one, which is one I particularly care about. So it's a bound on the deviations from the GR spectrum. What does this mean? So essentially what you want to, I showed you that these black holes are vibrating according to their own normal modes. So you have a spectrum, which is predicted by the Kerr metric, essentially. And so predicted by GR. And then you want to perturb this spectrum, so multiply it by 1 plus some deviation, and then you want to constrain these deviations from the Kerr spectrum. And we were able to do so. Unfortunately, the damping time is yet uninformative because it's harder to measure, while the frequency can be measured. And so the bound we have placed is this one. So it's consistent with 0, with plus or minus, let's say, it's 35% in accuracy. And this is the result, let's say, averaged about all the available signals. And also we have computed what's called a Bayes factor. So this is essentially a probability that there is either a modified GR signal or a GR signal in the data. And so this probability is favoring GR because it's a negative logarithm. So it's telling us that GR is slightly favored, that this is not strong enough that we can actually claim that the modified GR hypothesis is really excluded. And this result is interesting. We spent a lot of time and energy to get this, but now I'm going to have a bit of a provocative slide, let's say. And so I'm asking if this result passed the so what test. So what's the so what test? So the so what test is you take the results I've shown you before, so this bound on the deviation from the Kerr spectrum, and then you show it to theoreticians, so people who are interested in modified theories of gravity or alternative scenarios. Sorry, is there a problem with the audio or I?
Now it's fine. You can continue.
Okay. Thanks. All right, so you take the results I've shown you before, and you show it to people who are interested in modified theories of gravity, and then you count how many people say so what after looking at the results. And what I'm trying to convey here is that the bound on the Kerr spectrum is really nice and fine, but what people are actually interested on is the implications of these experimental results on specific modified theories or specific alternative scenarios like gravastars and so on. And the problem is that, unfortunately, the implication of these results to specific alternative theories are not immediately drawn. So, for example, when we measure the bound on the graviton mass, it's actually easy to translate that constraint on a specific theory, while withering down observation is not so. And so the reason why we don't actually constrain specific and well-motivated beyond GR theories that most theories are not proven to be well-posed, in the sense it's difficult to justify certain approximation in those theories. And also, once you step out the comfortable shoes of GR, there's a huge amount of possibilities that you have to take into account, like parity violations, additional modes, etc. So our policy has been to not consider specific alternative theories for which a framework has not been established. But this still doesn't answer our main curiosity, right? Because if I'm a theoretician who worked 20 years on Orava-Lifshitz gravity, I want to understand the implication of this specific theory. Fortunately, very recently, Maselli et al. Introduced a framework which allows actually to place perturbative constraints on specific theory. The price to pay is that you have to resort to a perturbative formalism. And so what you do is that you have your spectrum, so it's a frequency and damping time as a function of the black hole mass and black hole spin chi. And now what you do is that you expand the black hole spectrum. So the mass dependence, it's easy. Then you expand it as a function of the spin. And then what you have is that you have this numerical constant, which essentially summarizes the structure of the black hole spectrum from the dependence of the black hole spectrum from the spin. And then what you do is that you now perturb the spectrum at each given ordering spin. So you first do an expansion and then you perturb it. And the way you perturb the spectrum is that you have a gamma parameter, which is controlling the strength of the emission. So this gamma parameter depends essentially on the length scale, on the new length scale introduced by your theory, elevated to a certain power p. So p is essentially the mass dimension of the new length scale correction. So if p equals 0, you have a scalar correction, etc. And also now you have these other numerical constants which are independent of the specific signal that you are considering, unlike the LIGO parameterization, which was considering a global correction. And also another point is that now the mass and the spin are actually, since you are in a perturbative framework, you can use the mass and the spin from the GR prediction. So this formula has several advantages, some of which I already highlighted. And the consequence is that you now need a much smaller number of signals or smaller signal to noise ratio to detect a modification from GR prediction. So this framework is actually boosting our capability of doing GR tests. And so before describing the results, I'm going to classify essentially the classes of theory I'm going to constrain according to the mass dimension with which the coupling enters the action. So when you have a scalar coupling, so P equals 0, you have certain scalar tensor theory or Lorentz valuating gravity. For P equal 2, you have a dark photon. For P equal 4, you have essentially quadratic, the main theory which falls into this class, main theory in the sense that it's been well studied. It's quadratic gravity. For P equals 6, you have certain classes of effective theories of gravity. And so you see that most of these theories depend on, for example, this depends on this length scale L. And so this is the same length scale which appears in the gamma parameter as before. And so roughly you can think about this length scale if you think about the effective field theory length scale. So it's a length scale above which your theory is essentially GR and below which you're starting to see modifications from this other theory. And so now I'm going to show you results on each of these classes of theories in turn. So for P equals 0, this is the results I got. So what the constraint I've placed here is the constraint on the fundamental frequency of the black hole. So the 2 to 0 means the quadrupolar mode essentially, and this is the constraint on the lowest order non-spinning term, which you see it's still consistent with 0 with a precision of plus or minus 5%, which is several factors more precise than the one obtained by LIGO and Virgo. But now the probability that actually there was a modification of the GR spectrum is much lower. So this is 14 orders of magnitude in terms of natural logarithm. And so this is an improvement in a factor of 4 in the number of events needed to detect a violation. And of course, this result also depends on essentially the maximum expansion order that you consider. So if you add more deviation to higher orders in the spin, then you can, of course, constrain more terms, but your deviations will also be correlated. So your measurement blurs out when you increase the spin expansion order. But of course, you can still meaningfully restrict to the lowest expansion order, and you get this result. Next, for the case of quadratic gravity, so P equal 4, the constraint I obtained was essentially this one. So the length scale at which the theory is disfavored is favored to appear has to be smaller than 35 kilometers. So longer distances are essentially excluded by these observations. And again, the probability that GR is violated is negative. So sorry, the logarithm is negative. So this is favoring the GR emission. And you can compare this. You can compare these constraints to other constraints obtained by other experiments like Neisser-Platz LVC observation or X-ray for dynamical Chern-Simons or Einstein-Scarr-Gauss-Bonnet. And the length scale in the case of dynamical Chern-Simons is bound to be roughly 30-50 kilometers, while for Einstein-Scarr-Gauss-Bonnet is of the order of 5-10 kilometers. So you see
Gregory, sorry, 5 minutes left.
Yeah, thank you. So essentially, essentially, what this is telling you is that the gravitational wave result is more or less of the same order of magnitude in the case of some theories, or close to some other theories. But this can only improve with future observations. And also in this paper, I also noticed another result, which is a non-perturbative constraint on Einstein-Scarr-Gauss-Bonnet. So in this theory, essentially, what you have is that if you have a black hole, just from the fact that the black hole is stable, your length scale has to be smaller than a certain amount. And I notice here that if this signal, which is called 190814, is interpreted as a binary black hole, then this length scale is bound to be smaller than 3.3 kilometers, which is the best constraint available on this theory. And finally, I did the same thing for effective field theories of gravity. So actually, this is a special class of effective field theories of gravity. So it's the class that takes into account essentially other experimental bounds that we know gravity respects. And that the constraint for this theory was length scale smaller than 42 kilometers. The previous best bound was on gravitational wave spiral, and was the length scale smaller than 150 kilometers. So in the language of Sennett et al. Paper, which derived these previous constraints, we are now probing the finite size effect of the black holes and no longer just a long range behavior. So finally, I'm going to conclude with a special class, which is called the Kerr-Newman case. So Kerr-Newman black holes describe essentially charged black holes. And the reason why I focus on this case is that, first of all, this scenario does not just represent a black hole which has some electric charge, but it's also degenerate in the ring down emission with other alternative scenarios like mini-charge dark matter, magnetic monopoles, scalar tensor vector gravity, etc. And also, the reason why this is interesting is that you have essentially a deviation from the Kerr case, because astrophysical black holes are not expected to be charged. So you expect them to be represented by the Kerr metric. But now you have, let's say, a violation from the Kerr hypothesis because you have charge, where you know for arbitrary spin what should happen, because you know analytically the spectrum up to arbitrary spin. And so that's what we try to understand with collaborators from the UK. So we tabulated the spectrum up to very large values of spin and charge, and then we constructed the gravitational wave models. And what we did is that we placed bounds on the maximum amount of charge that these black holes could possess. So unfortunately, standard techniques do not work in this case, because there is a strong correlation between spin and charge. So we did a null test. So we only could compute the maximum amount of charge, which is compatible with these observations. And the result is that the charge should be smaller than 0.33. But also statistical analysis tells you that there's no evidence against or for the presence of charge in these signals. And finally, since we didn't find any signature of charge in current data, then the natural question to ask is, okay, can will we be able to have detailed information on the charge using future observations, using LIGO and Virgo and their design sensitivity? And so the answer is that the answer is in this plot. So the answer is that if the charge is large enough, like 50% of the maximum, because the charge, this is the dimensional charge, which goes between 0 and 1. If it's like 50% of the maximum, then you will be able to essentially constrain the value. But if it's smaller, then you will not be able to constrain. So essentially, you will need either a more informative model, let's say, taking into account other phases of the coalescence, or better detectors like LISA.
Very sorry.
Yeah.
No. So, thank you.
Yeah, that's it.
So, okay, so we can see the conclusions. And now we have a question from Alexei Starobinsky, please.
Thank you, for this very interesting talk. I have the following question. Let us remain in the scope of general relativity. What do you think about perspectives to prove observationally the existence of a super irradiance effect for gravitational waves using quasi-normal modes?
Sorry, you asked about super radiance, right?
Yes. Mm-hmm.
Okay. So as far as I know, the super radiance effect are best probed. So what happens is, what happens with super radiance is that you have essentially an instability mechanism, right? Which can So essentially, one of the best scenarios in which superradiance could be probed is that if you have some light massive field around the black hole, and so this light massive field essentially forms a cloud around the black hole, and it forms essentially a cavity which traps gravitational waves, and this. Because to have superradiance, you need some kind of containing mechanism. And so if you have these light fields, like, for example, the ones which could form dark matter, so if you have this light field which forms a cavity with a black hole, then you could have superradiant mechanism. And this, of course, will give deviations in the quasi-normal mode spectrum too. I think from what I understand is that the best perspective to probe these signals are either with stochastic backgrounds formed by the combination of black holes in the universe, or similar signals in LISA, because the quasi-normal mode emission is actually quite short-lived. So this effect is much harder probed by. Of course, it depends on the mass scale of this light field, which forms the cavity of the black hole. But I think that, you know, it will be a signature, but I think that this kind of superradiant mechanism will be probed by different kinds of gravitational waves better.
Okay. So,
But in fact, my question was about massless gravitons. So once more, are there can be some feature in the quasi-normal modes in normal gravity can be found that we specific to superradiance, which can be directly test from observations.
Yeah, so I know of a paper which predicts essentially it predicts what kind of constraints we'll be able to place with LISA on this on the effect you described. So when we have a massive graviton and superradiant effects, so I think that the effect, so the current sensitivity of LIGO-Virgo is not strong enough that we can actually meaningfully probe this effect with current observations. But of course, in the future, we'll be able to certainly place constraints on that kind of effect for sure.
Okay.
We run out of time. Alexander, just half a minute if you can.
Okay, I like your last part of your talk about Kerr-Newman metric. Do you plan to analyze also metric with tidal charge when Q squared is negative? Because I think you could easy to consider this case as well.
Okay, I'm afraid I don't know the theoretical framework you're referring to. So if you could send me
I will send you a recipe.
Okay,
that would be.
Thank you very much
Thank
again. And we have to pass to the next talk by Valery Korol, Listening to the Universe with Liza.
Hello.
Hello.
Let me share the screen.
Okay.
Okay. So do you see my pointer? Okay, so in this presentation, I will walk you through the astrophysics that we can aim to study with the future ESA's mission LISA that has been mentioned already a few times this morning. And to justify the title, I would like to open this presentation by highlighting that we are now living in the era of multi-messenger astrophysics, because since more than 5 years now, we can learn about our universe not only through electromagnetic radiation, but also through gravitational wave radiation. And since gravitational wave sources that we currently detect emit at similar frequencies that us humans can hear, gravitational wave astronomers like to use the analogy of adding another sense to our ability to explore the universe, which is hearing. And gravitational waves open to us a whole new spectrum spanning 18 orders of magnitude that allow us to study variety of different phenomena. And on this slide, just a couple mentioned here, such as the quantum fluctuations in the early universe, binary supermassive black holes in the galactic nuclei, stellar mass compact object binaries in our galaxy, rotating neutron stars, supernova, and so on. So let me zoom in on the gravitational wave window between 10 to the -10 and 100 Hertz, where we have the 3 measure gravitational wave experiments. So the highest frequencies are covered by the ground-based experiments, the LIGO, Virgo, and the upcoming KAGRA. The millihertz regime will be covered by the future space missions like LISA. And the nanohertz regime is covered by the pulsar timing technique. And here you can see what sort of gravitational wave sources these three experiments are sensitive to. So on the x-axis, you have gravitational wave frequencies, and on the y-axis, you have characteristic strain, that is basically the amplitude of gravitational waves. While these black solid curves delimiting the part of the parameter space accessible to those experiments, so above the curves. And I would like to call your attention to the fact that LISA has a privileged position here in this gravitational wave window right in the middle. And this makes it, in a way, really special. And this is because LISA can probe all relevant black hole masses. So starting from the massive black hole binaries accessible with PTA to the stellar mass black hole binaries accessible with LIGO. LISA can see astrophysical sources at all relevant redshift and even beyond the reionization epoch relevant for cosmology and fundamental physics. LISA has potential to detect sources with extreme mass ratio. So that, for instance, the combination of PTA, supermassive black hole, with the stellar mass black hole orbiting around it. Next, LISA can detect vacuum, so black holes, but also matter, for instance, white dwarfs, neutron stars, and even some non-degenerate stars, unlike the other two experiments. And finally, LISA has potential to survey our own galaxy. And this is truly unique for these millihertz frequencies and to LISA. So from now on, I will focus then exclusively on the LISA window. And at this these frequencies allow us to address a broad range of scientific topics, from astrophysics to cosmology and to fundamental physics. And we can roughly divide astrophysics topics in three categories by the source type. So firstly, we have stellar mass compact object binaries and multiples in our local universe. Then we have supermassive and massive black hole binaries. And finally, the extreme mass ratio binaries. So we can study them as resolved sources, so detected as individual events, but also some of these sources may form confusion foregrounds for the LISA. For instance, galactic white dwarf binaries are so numerous in the Milky Way that the signal blends together and forms the confusion foreground that is shown in the gray shading in this plot. So in my talk, I will focus on these three categories, but let me also mention that LISA can access stochastic backgrounds if they exist from the early universe, so prior to reionization, as for instance, Valerie mentioned already a couple of examples. And we can study cosmological parameters using standard sirens. And this is an analogy with standard candles that we use in electromagnetic observatories and much more. So let me start with supermassive black hole binaries. So these are regarded as a class of loudest sources detectable by LISA. They will be merging in the LISA band and will be observed, therefore, through the in-spiral merger and ring down. And overall, they will stay in the band for a month or weeks. And at what frequencies we will see them exactly depends on the binary physical properties. For instance, high mass black hole binaries of 10 to the 7 will merge at lower frequencies, so below 1 millihertz, as you can see on the plot, and therefore they will stay less in the LISA band. While the lighter binaries will merge at higher frequencies and they will stay longer in the band. So what we will learn from them. So on galactic scales, the observations of merging binaries will tell us about the formation and evolution of galaxies, because the formation and evolution of supermassive black holes is tightly related to the fate of their host galaxies. Then when going from kiloparsec to milliparsec scales, so moving to the middle of these panels, when the binary is really driven by gravitational wave radiation. So this journey is rich of hydro and stellar dynamics phenomena that we can study with LISA. And finally, at the milliparsec scale, we can study magneto and hydrodynamics that goes on during the merger itself, which with LISA will be possible to do for the first time in a highly curved and changing space-time. So because of the shape of the LISA sensitivity curve, the most likely target supermassive black hole binaries will be those with the total mass between 10 to the 4 and 10 to the 7 solar masses. And in principle, we can see them through the whole universe. So for example, on this waterfall diagram, you can see that the binary with the total mass of 10 to the 5 can be seen by LISA with signal to noise of 200 up to redshift 20. So now we can, we need to know how many of those binaries are there at those redshifts. And to understand this, we need to build synthetic populations. So of course, there are many studies producing such populations using different assumptions and technique. However, currently, all of the simulations more or less agree that the detection will peak between the redshifts 5 and 10. And this is for binaries with total mass between 10 to the 4 and 10 to the 7. That in this example on the slide, where you have redshift on the x-axis and the logarithm of the mass of the binary on the y-axis is highlighted in green, so the highest signal-to-noise binaries. However, still highly uncertain is the detection rate of the supermassive black hole binaries, and currently it spans 2 orders of magnitude. And this uncertainty comes on the uncertainty on how supermassive black hole forms and how quickly, if at all, they merge when 2 galaxies merge. So this is the peak of the detection. However, even if the majority of LISA signals will come from a relatively high redshift, there will be still several detections at lower redshift, so at redshift below 2, that is not shown on this plot, for black holes with the masses of about 10 to the 5 or so. And these lower mass binaries are very exciting because they can be studied jointly by LISA and Athena, which is the ESA's next generation X-ray telescope. So you see some of the characteristics of the 2 missions on this slide. And this line of research of joint LISA and Athena studies gained a lot of popularity in the last few years, when it became clear that ESA can launch the 2 missions in a way that they will overlap in time. And in a nutshell, the plan is to use Athena as the follow-up instrument for LISA. So LISA will start detecting the supermassive black hole binaries in spiral phase, roughly 1 month earlier before the merger. And as the spiral proceeds, gravitational waves will get stronger and stronger. And the sky localization of LISA, that is proportional to 1 over signal to noise square, will get smaller and smaller. So at first, LISA will provide fairly large portions of sky of tens of degrees that Athena can scan. However, prior, like hours prior to the merger, LISA sky localization will go down to less than a degree, which is then became compatible with the Athena's field of view. And at this point, 2 missions can witness the merger process simultaneously. So we can follow up the ring down with LISA and settling of the accretion disk of the supermassive, the final supermassive black hole, and the onset of jets with Athena. And this would be truly exciting for astronomers. So next, let's move to the extreme mass ratio binaries that we call extreme mass ratio in spirals, or EMRIs. And these are stellar mass of objects such as black holes, neutron stars, white dwarfs, brown dwarfs, orbiting supermassive black holes. So these sources stay in the band for years, so during the whole duration of the mission or so. And during this time, they compute 10 to the 4, 10 to the 5 orbital cycles before plunging into the supermassive black hole. So this property makes EMRIs exquisite tracers of the space-time around supermassive black holes. So Lisa will see them as individual events, and this is mainly at low redshifts, on average around redshift 1, and mainly for low mass black holes of 10 to the 4, 10 to the 6 or so solar masses. And in this mass range, actually, the black hole mass function and the occupation function is highly uncertain. And because of this, the predicted detection rates for EMRIs currently spans 3 orders of magnitude, from a few to hundreds, thousands, actually, events per year that we can detect with LISA. And in addition, it is also possible that these sources will form a copious unresolved background at around a few millihertz. However, again, this is highly uncertain. And finally, I wanted to mention that EMRI's waveforms are extremely complex, including frequencies that are orbital, pericentral, and orbit precession frequencies. So you see the shape of the waveform on the blue background on the left. And this makes these gravitational wave sources extremely challenging to model. The astrophysics of EMRIs is really fascinating because they take place in central nuclear star clusters that are the densest stellar systems in the universe. So they almost always harbor a central supermassive black hole in the very center. Which adds to the classical multi-body dynamics and relaxation processes, also the resonant relaxations. And these relaxation processes are those that deflect surrounding solar mass objects into the highly eccentric orbit that go so close to the supermassive black hole to emit gravitational waves at the pericenter passage. And those gravitational waves we hope to detect with LISA. So by studying, for instance, the rates and the properties of EMRIs, we can then rederive the relaxation processes producing this gravitational wave source. What we can also study with the EMRIs is the content of galactic nuclei. For instance, the rate and the existence of the source depends on the existence and the mass of the density cusp of compact objects surrounding supermassive black holes. So this cusp so far has been supposed theoretically. We have some indirect hints from X-ray observations. However, Lisa will tell us much more about its existence, if at all. And another line of research comes with EMRIs very recently, and this new picture, it is possible that the formation of EMRIs is assisted by gas surrounding supermassive black holes. So stars or other objects are captured by gas first, and then they migrate towards supermassive black holes, just like planets do around stars. And if so, we can study hydrodynamics of black hole disk and gas interactions with LISA as well. And finally, we may be also studying the center of our own Milky Way, where it is possible that we will see MRIs from low mass stars and brown dwarfs orbiting our Sagittarius A star. So LISA will give us a way to study the content of low mass stars and substellar objects in our galactic center, which is extremely challenging to do with electromagnetic observations because of the intrinsic faintness of the stars and because of the heavy dust extinction in the galactic center. And finally, stellar mass compact object binaries. This is mostly in our galaxy. So let me first show you the zoom of these binaries that populate our Milky Way. So the absolute majority of the binaries will be composed of 2 white dwarf stars. And this is simply because the initial mass function favors the formation of white dwarf progenitors compared to the high mass neutron star and black hole progenitors. And because low mass stars evolve on a much longer time scales, so we have more chance to see them. So LISA will see these double white dwarf systems in the detached and in accreting configurations that are called Canum Vanaticorum stars, or MCVNs in short. And the detached double white dwarfs will be the most numerous LISA source with tens of thousands of individual detections. Then we have white dwarfs with the helium star companions here in the corner. And these binaries are very special gravitational wave source because technically helium stars are not composed of degenerate matter like other compact objects, but of ordinary matter like our sun. However, unlike normal stars like our sun, they have been stripped of their outer layers so much during the binary evolution that they now can fit into a compact object, compact orbit emitting millihertz frequency gravitational waves. Then on the top right, you see artist's impression of a binary pulsar representing the class of double neutron stars. And in our galaxy, we will see from a few to a few hundred of those with LISA. And then binary black holes. Again, we may see them up to 100 from our Milky Way. And of course, you should also imagine all sorts of mixed systems. So white dwarf neutron stars, white dwarf black holes, and so on. And this plot shows you how far we can see these binaries as a function of their gravitational wave frequency. So for instance, 0.5 plus 0.5 white dwarf binary can be seen within the virial radius of the Milky Way. Heavier white dwarfs 0.2 plus 0.2 can be seen further out in the local group, somewhere up to the Andromeda galaxy, so a few megaparsec. And similarly for double neutron stars that have similar masses, while more massive black hole binaries can be seen up to tens of gigaparsecs. So now I will give you some of the source characteristics, and I will mainly refer on the most numerous white dwarf binaries. So this will be seen by LISA as in spiraling gravitational wave sources. And this is because they shrink due to the gravitational wave emission on time scale that is of millions or at most 1,000 years. And therefore, LISA can see them as continuous gravitational wave source. So at frequencies higher than a few millihertz, they will be distinguished as individual gravitational wave events, while at lower frequencies, they will form an unresolved confusion foreground that I mentioned before. So these binaries can be modeled with the simple, almost monochromatic waveforms, like it is shown here. However, this doesn't make these gravitational wave sources less challenging for LISA. Because they will be so numerous, so tens of thousands of resolved, but millions of unresolved ones in our Milky Way. This means that it will be extremely hard to disentangle all those signals. That I would like to stress that in LISA data, all of the signals are present simultaneously at all times. So it will be a really hard data challenging task, data analysis task.
Valerie, sorry, you have 3 minutes left.
Okay. And finally, some of the binaries of the white dwarf binaries that we know and observe right now with optical telescopes, and of which we know all of the orbital characteristics, we can use as calibrator sources for LISA when it will fly. So very quickly, let me mention some of the science highlights with these binaries. So firstly, the rates and the distribution of their properties will tell us about the binary, stellar and binary evolution, including some of the poorly constrained processes such as accretion on compact objects and common envelope evolution. At highest frequencies, these binaries will be, the gravitational wave signal will be also affected by tides, which means that we can study this, again, poorly constrained process, and we can study the response of the degenerate matter to tides, and hence the internal structure. So this will be possible for white dwarf binaries. As I mentioned before, LISA will see some of the heaviest white dwarf binaries that are type 1a supernova progenitor, and will provide us actually a complete sample of those in our galaxy and beyond. This is for the shortest orbital periods. And finally, LISA will provide us a survey of evolved stars in our own galaxy. And this survey will be complementary to electromagnetic surveys such as Gaia. And LISA data will enable us to study the overall properties of the Milky Way using gravitational waves, so such as the shape. And you can see that clearly from the plot on the left, where the gravitational wave LISA detections are shown in the blue and violet colors, and how nicely they follow the shape of the Milky Way. Their number will tell us about the mass of our galaxy, and their properties will tell us about star formation history of the Milky Way. So to conclude, I would like to show you how our Milky Way will look like as seen by LISA. So in orange and red colors, you see the Milky Way. So this is the galactic plane, and the reddest color is the bulge. This is in ecliptic coordinates, while the blue stars and points scattered around are known Milky Way satellites, so with the stars being those satellites in which LISA can detect this, the most numerous white dwarf binaries. And actually, some of the Milky Way satellites are massive enough to host hundreds of LISA detections. So we'll be seeing them on gravitational wave sky as a resolved galaxy. So here you see an example of the large Magellanic Cloud as seen by Gaia in white, and LISA density contours in orange. And so with this presentation, I've only given you a glimpse of a few of the LISA science cases. Of course, there is so much more to tell. However, I will conclude now by saying that because of such an enormous amount of science and its diversity for astrophysicists, LISA is not only a gravitational wave experiment, it is really an astrophysics observatory. And we are really looking forward to have it online.
Thank you very much for a very nice presentation. We have no time for just a short question about single rotating neutron stars, LISA. Is it possible?
So the rotating neutron stars will be seen at higher frequencies, right? Because they're just smaller.
Yes.
So short. So with LIGO, however, if those have a binary companion, perhaps at the larger separation, perhaps we can see that source in LISA as well.
Thank you. Thank you again. And we have to pass to the next talk by Adam.
I'm here. Hello. Hello to
Joachim.
everybody. Can you hear me?
Very good.
Super.
Okay.
I try to share my screen.
Mhm.
Can you see my slides?
Yes.
And now it should be in full screen mode even.
Okay.
So I just switch to this. Okay, so I start right now. Okay.
Mhm.
Thank you. So I would like to thank you to organizers of this nice conference for inviting me here to actually share with you our recent work. And as Valeria said, there is a lot of players in LISA mission to be disentangled. And I would like to present here one more of them. So this work has been done in collaboration of two Prague institutions, Institute of Experimental and Applied Physics at Czech Technical University, together with Charles University. And it is based on this published work in the last year. But since then, there was done some development, so I will report about it now. Okay, so we have gravitational wave antennas, and we can split them into ground-based gravitational wave antennas and space-based gravitational wave antennas. The difference is that for ground-based, we have actually size limitation because of the size of the Earth. And then we have also seismic noise. We need to use vacuum technology in order to suppress the scattering of laser beams. And we need to reach ultra high vacuum, which is 10 to 7 molecules per centimeter cubic. But we have this vacuum pretty much under control. We actually can keep some stability of this vacuum. To be compared with space-based facilities, we are actually practically free of the size limitation. We have no seismic noise, which is excellent, and we have vacuum for free. And this vacuum is much better what we can reach in ground. But this vacuum is, for instance, 10 particles per cubic centimeters. But this vacuum is not under our control. It means that if we are around the sun, there is solar wind, and this solar wind is governed by the sun activity. And yes, and pretty much this work, what I will present is about that. LISA mission is, the details are in this slide. I guess I don't need to go into details. Just what is important for us, that the LISA will orbit around the sun in the 1 astronomical unit, and it will have a variable arm length of 2.5 million kilometers. And there are many challenges to be tackled, and these are so many that it doesn't fit into this slide. And I would like to maybe highlight one of them, which is connected with solar wind. That basically solar wind, how as it is changing in time, it also changes the momentum transfer to the LISA instrument, and it jitter with LISA. So basically, you need to take that into account as well, apart from many other sources of different frequencies of different noise, basically. Actually all these informations, how LISA is challenging these things, can be found in this, for instance, in this paper. Okay. So LISA parameters are the following. Actually, the parameters which are relevant for our work are the following. There will be 6 laser links operating on the wavelengths of roughly 1 micrometer, super stable lasers. And these lasers will be shoot on the path between 2 spacecraft, basically between 3 spacecraft, and one arm will be will have average length of 2.5 million kilometers. And the LISA collaboration did amazing work to suppress the noise level, which can be expressed in terms of so-called strain sensitivity, which is here this quantity. And the collaboration made possible to be below this level. So this strain sensitivity is dependent on the frequency, and the result is roughly this dashed line here, the black dashed line on this picture. Here is taking into account also this galactic noise, and by colorful bars you can see what are the expected signals from various gravitational sources. Okay. So as I already said at the beginning, we are actually showing, we want to show here, or maybe yeah, we want to point to one possible other player in the game, which is the solar wind itself, but now not because of this mechanical transfer of momentum to the spacecraft, but because of the simply changing optical properties of the vacuum itself due to the changing density, and then due to the consequent change of refractive index of this environment in which LISA will fly. So basically the proper quantity to be studied is the refractive index of the medium, and basically that means the refractive index of solar wind plasma, which is mainly given by protons and electrons with average density, let's say 5 electrons or protons per cubic centimeters. And there is actually textbook formula for that. So we can use this formula for refractive index for such a plasma, which is very dilute. We can actually treat it as a collisionless ideal plasma. That's why we can use this textbook simple formula. And this quantity here, omega p, is a plasma frequency of the plasma, of the solar wind plasma, which is given by electric charge, electron density, and electron mass. And omega is the frequency of the electromagnetic wave. In our case, it is corresponding to this 1 micron of wavelength. So of course the effect is expected to be very, very small, because the density of electrons is so small. I should comment here that we don't need to take into account a proton component of solar wind, because as you can see, the dominant contribution comes from lighter particles, because the plasma frequency is proportional to inverse mass. That's why protons contribute only subdominantly. So we expect the contribution to be very small, and it's really like that. The contribution to refractive index is at the level of 10⁻21 for LISA environment. Okay. But still, it might be or might not be heard by LISA, and this must be answered. So for that, we just introduce so-called effective displacement or effective strain, which is this effective displacement in a ratio with the length of the LISA arm. And this effective strain we will compare with this required sensitivity of LISA in terms of their linear spectral density. So basically, we'll compare the quantity which I showed previously. It's this one with our effective strain of solar wind. For that, we made, and it was published last year, we made a preliminary analysis, and we just selected several let's say, time windows of solar wind, just pretty much randomly chosen to see what is the effect. And we used the data from wind mission. And this is the list basically of these, and we have chosen the length of the data samples to be at least 24 hours. This was motivated to cover the low frequency edge of the LISA frequency window of interest. And fortunately, the sampling frequency of wind spacecraft is actually 6 or 12 seconds, corresponds to 6 or 12 seconds, which actually corresponds to the high frequency edge of the frequency window of interest of LISA. Okay, and we don't want to also have another spacecraft or data from other spacecraft which are near Earth, because there might be some interference with Earth magnetosphere, which we don't want. So wind is actually a very nice source of data for this analysis. Okay, and the preliminary results came out to be this, what you can see here. So here in logarithmic scale, by black line, you see the required strain sensitivity of LISA. And by colors, you see the linear spectral density of each of the data samples which we selected. And you can see that it goes over this strain sensitivity, required strain sensitivity of LISA. In the first row, we have actually randomly chosen events. It means the data samples of randomly chosen solar activity. While in the lower row, we have chosen some events like solar activity events, some more profound. And you can see here, actually on the right column, you can see the comparison how much more it goes over this strain sensitivity, the solar wind signal basically. Here I must say that the paper was published with a small error. Actually, we overestimated this solar wind signal by roughly a factor of 3. We realized it very recently, and we understand the error and must be corrected. These pictures are already after correction, and so that there must be erratum delivered. Okay. Together with Charles University, we made more detailed analysis of the same, and we used actually much more data from wind, as you can see here. It was over a whole period of 15 years, and we took 24-hour window and we shifted by 1 hour, and that produces almost 80,000 of spectra. And we needed to, of course, resample it to make it to have the frequency 10 hertz, and basically this is the result, which turns out to be not so severe as the preliminary results. You can see here that actually, let's say 50% of spectra, they will not leave a signal in LISA, and so here you can see the percentiles of the spectra, how they leave the track in the LISA, and you can see that only small part of basically time or small part of data samples are leaving some observable signal in LISA. In the blue line here, we show the percentage of these data samples which overcome how many percent they overcome the strain sensitivity of LISA, above LISA strain sensitivity, how much they go. So basically, in conclusion, for this frequency of few millihertz, we could reach even 4% of time LISA could hear solar wind. That's basically the main message here. Okay. So the discussion here, what must be said? Actually, I worded the previous slide. I worded maybe too strictly. Maybe the effect will not be so profound, and the reason is that we made the analysis for one arm only, and also we take into account that the solar wind change or the solar wind change of density will actually span over the whole arm at once. Okay, so you can imagine that it would be the scenario as in the first picture. You can see that if you have a boat like long like this, and you orient it in this way with respect to the waves, then of course you will see you will feel the waves. However, if you orient your boat in perpendicular direction to the wave front, then such effect can be averaged out. Or another scenario could be that the solar wind changes are much more have much more smaller wavelengths. Actually, it would be like this. So compared to LISA arm length. So that would be actually the effect would be averaged out no matter on the orientation of the arm. So we try to answer that question also, because for that you need to have actually data over long distance, simultaneous data over long distance. And this is actually possible to see at least some hint from the mission, which is called Stereo, which is the pair of two spacecraft which are same, and they orbit in the sun in opposite directions, and they measure the same. They measure the solar wind density basically. So their mutual distance can be plotted here. So actually they go from when they were launched, they were at 0 distance, and when they are the furthest from each other, it's something like 50,000 of Earth radii. So basically the LISA arm length is in very bottom of this graph. So we can use basically this data from this period when they were very close to each other, around the distance of the LISA arm, basically. And from that we can derive what would be the correlation length of solar wind. So two stereo spacecraft will measure the same, and if the density fluctuates the same way, so there will be a big correlation between them, then we can assume that basically the solar wind change will hit the LISA at once, and then we could have a bigger effect than if the correlation would be very small, at very small distance. So from there we derived correlation length, which is 24 million kilometers, which is actually 10 times more than is the length of the arm. So basically, if I go back, this is a hint that the situation will be more likely like this, and the effect could be really visible on LISA. Okay, so of course there should be said also that we made this analysis only for one for single LISA arm, and that if you take into account all three arms, that also probably will suppress the effect, but this must be analyzed further. In any case, if we would like to somehow be sure that we know that some signal on LISA is from solar wind, we should maybe do something about it. And one proposed way is to measure the solar wind independently, which could be quite costly, because it would mean that we maybe need to deploy several satellites or spacecraft along the LISA arm and monitor in detail what's happening. Or maybe it would be enough just to put some solar wind detectors on 3 main spacecrafts and just monitor what are the changes. And if there is some peak, then we would probably understand that some signal might be solar wind and not gravitational waves. Or second solution is to deploy this LISA laser system by the second laser of different wavelengths, and then subtract the signals from these two systems in a given ratio, and that basically will effectively completely cancel out the solar wind signal. That was already proposed by Armstrong in 2006 for a mission called Doppler, which I found in literature the only mentioning of this effect of solar wind to interferometers, to space-based interferometers for gravitational wave detection. So there was a mentioning of this effect, and they proposed the same solution as is.
Adam, excuse me, you have only several minutes left.
Yes, I think that I go to conclusion slide. Yes. Well, conclusion, current status. So the current status of this work is the following. We were in contact with LISA collaboration. We made mainly the cross-check of the results, whether we agree on it. After all, we agree on the. We actually were able to reproduce each other's calculations. Thanks to them, we detected this error of factor of 3. We corrected, and now what should be? But actually, the conclusion of LISA is that it's not very profound effect and probably it won't be visible. It will not harm LISA. We agree on it. The effect is not so much above the strain sensitivity, and also it could be only visible if there will be some strong solar activity event. But still, we would like to continue in this in this project, and what we need to still do is 3D modeling of solar wind propagation, and mainly of these more powerful events. And then using this, we should also simulate the propagation of such event through the full-scale LISA. It means 3-arm LISA, and simulate the effect and see what is the response, whether it will be heard by LISA and how much. So thank you for your attention.
Thank you very much for a very informative talk. And I'm afraid that we have no time for questions because we run already the tea break. So, Alexander, what we do about time break?
So if you be so kind, probably I will just ask a question and then we shall move ahead. Yeah. So thank you for a very interesting presentation. And I just recall the talk presented 2 days ago by your collaborator, Maria Petropavlova, who discussed the correction to the photon index of reflection due to relic neutrinos. Well, I wonder about possible effect for LISA due to solar neutrinos, for instance, in the case of extremely high values of neutrino magnetic moment. Can you comment on this, please?
Okay, so I expect actually I expect no effect because one of the magnetic moment, which is how it is predicted, or what is the high limit or experimental upper limit to magnetic moment of neutrino, is much it's very weak. It's much smaller than we have from the electrons here. Electrons, if we say that the effect of electron gas is let's say 1, I would expect the magnetic moment effect of neutrinos to be suppressed by 10 to minus 24. And you can beat it only by density. So if the density is 10 times 24 higher than the electron density in the LISA environment, then I would start to think about it, basically. Okay, but for such small densities of neutrinos, still small, they are high at some sense, but for this effect, I think it's still small. One would expect that the effect would be maybe some, but small. But Maria actually reported that our conclusion is that there is 0 effect because of the nature of magnetic moment interaction on a refractive index. If one expects small effect, then there will be no.
Okay, well, thank you very much.
Maybe we can discuss later also.
So, thanks again, all the speakers. So we finish with this session and pass to directly to Marco. Alexander.
No, you see, thank you very much for all speakers, and also to Dmitry Galtsov for chairing the session. And I suggest that we shall have a break for 5 minutes, as my colleague Konstantin just indicating me. Well, okay, 5 minutes, and in 5 minutes we shall meet again each other here. Yeah, thank you very much.
Hello, Marco. This is Frank Eisenhower. I'm the second speaker. Good morning. Can I make, well, after that for make a short test whether the video works, but I see you already.
There's Alexei who is sharing his video.
He should.
So it seems to work. Alexei, would you mind leaving the sharing for a second so that Frank can share? Oh, here it is. Thank you. Спасибо, Alexei.
Thank you very much. Grazie.
And here it is.
Here it is. And then let me see if I can come to a more difficult movie, which challenges a bit more the connection.
The movie, wow.
Is it moving?
We'll see. The movie. Yeah.
Okay, super.
The world's largest and sharpest optical. Wow.
Thanks a lot. Okay, so I'm done.
How exciting.
Thank you for the test.
It's good to be chairman because I need to pay attention. Otherwise, online conferences are very difficult for me.
Absolutely, for everyone. Thank you.
So it all works. And yes, good to test. I can show to you something nice. I hope the connection will work well, but I'm gonna show you some nice place here where I am located. I don't know if you see it. It's in Liguria near the Cinque Terre place.
Cinque Terre.
And I was hoping to show a rainbow because it was just raining, but no rainbow. No rainbow. Привет, здравствуйте, Alexei. Last time I saw you, it was in Domodossola.
Indeed.
With Vittorio Gorini and Sergio Cacciatori. So it's nice to see you. I guess we should wait for 3 more minutes because Alexander said, 5 minutes. And is there anyone else who wants to, I don't know, try the screen or maybe not? It seems everything seems okay. It's the usual screen sharing, and Alexei is already showing his first slide, which is very good. So if you don't mind, I will remind the speakers. Recording is stopped. I would remind the speaker just a couple of minutes before meeting is being recorded. I would remind the speakers just, a couple of minutes before the end of the time to conclude. It would be nice if we could keep the time, but we are only 5-10 minutes late, so it's kind of okay. And the session will be very interesting.
Good afternoon, everybody. So I think that we have probably half a minute, before officially the plenary session will start. And just now I would like to address welcomes to all the speakers of this session, and in particular, I would like to address special warm greetings to our chairman, Marco, who is also the speaker of the 20th Lomonosov conference here. And in addition, and this is very important, Marco was among participants of the very first Lomonosov conference that was held in Yaroslavl in 1992. Marco, please start your work for the 20th Lomonosov conference.
Alexander, it is really a pleasure for me to start this session, and thank you for reminding of this beautiful time and the whole experience of the Lomonosov series conferences are really amazing to me. It's now really a major conference. So this session will be a session about astrophysics and cosmology, very interesting. And I would like to call the first speaker of this session, Alexei Starobinsky, with his talk about the simplest models of inflation, recent results and expected discoveries. So, пожалуйста, Alexei Alexandrovich.
Excuse me, I would like to recall that Alexei also was among the first participants of the first Lomonosov conference. I'm sorry for interrupting you. Thank you.
Okay, so thank you too. So let me first thank the organizers, in particular Professor Slodenikin, for inviting me to participate and present one more talk at this conference, at the 20th Lomonosov conference. And what I call the simplest models of inflation is simply I count the simplicity by the amount of free parameters, three-dimensional parameters, which does not follow from theory, but have to be taken only from observations. And so my statement is that while from the observations we have two fundamental observational parameters, the simplest models those have only one parameter. The second can be deduced from that figure, and I shall present you this result. And then there exist two kinds of this one parameter models, R squared, actually better to say R plus R squared, and the Higgs models. And I shall show you that actually, though it was known, I would say, a long time ago, it was sufficiently clearly presented only in recent years, that from observational point of view, as far as you're speaking about inflation only, it's actually the same model from the phenomenological point of view, but it's interesting to investigate combined R squared Higgs models, and I shall present you some new results of this. But of course, this is only from the phenomenological point of view, and observations may require us to consider models with more free parameters. In particular, if we shall find some deviations from the approximately scale-free spectrum first, and second, possible reason in the future if we found primordial black holes. And so I shall also present you some of my recent results in this direction. So let me remind you that actually inflationary hypothesis may be very briefly formulated as the assumption that some part of our world, which includes all the presently observable part, was as much symmetric as possible during some period in the past, both with respect to geometrical background and to the state of all quantum field. Still, the state is not a unique one. It's actually a family of states with what is important with a non-zero measure in the space of all initial parameters. And actually, successful realization of this idea. It was in some sense an idea about how to realize it practically. Actually, it is based on two more detailed and independent assumptions. The first refers to the background. Actually, it's the assumption of existence of a metastable quasi-de-Sitter state, which preceded the hot Big Bang, and this is characterized by this condition. And the second assumption is what is the origin of all inhomogeneities. The assumption is that produced just due to this effect, the gravitational creation of pairs of particles, antiparticles, and field fluctuations during inflation from the adiabatic vacuum state for a large range of Fourier modes, which covers all observable range of scales. We're very sure that remark that, strictly speaking, it's not the Bunch-Davies state. Bunch-Davies state is the assumption that this assumption is valid for all scales, but it's not so. It's not. It cannot be imposed for arbitrary large scales, and as a consequence, inflationary models typically does not predict the regular behavior of spatial infinity. And then another properties of viable inflationary model, which actually I consider as an advantage, it is not orthogonal to the usual physics because there exist analogs in other areas of physics where the first assumption is actually the properties of this unknown substance which supports inflation is actually very similar from the qualitative point of view to the properties of President energy. And second, the assumption about mechanism to create inhomogeneities is essentially the same as the effect of creation of electron and positrons in an external electric field. So just because the aim was, I was always main emphasis not on explanation, which is usually proposed in many textbooks, but so what is just as in all normal models, in particular of elementary particle physics, in all extensions of a standard model. So to what we need from any inflationary model, of course, it should be internally self-consistent. Okay, and okay, but what we need from these models is actually prediction about initial perturbation spectra, and it appears that in the super Hubble regime there always exist some modes of perturbations which are time independent as far as they in the super Hubble regime, and where trace part is just concerned with the so-called gauge invariant curvature perturbations, but there always exists some traceless and transverse part. And what we are most interested in is about the prediction of the power spectrum of scalar perturbation, where slope, which for historical reason is defined with this -1, so it's simply a notation, and also the ratio. Okay, no, well, of course, just because this process is quantum, the metric perturbations are quantum even at the present time, in the sense that HIK is an operator, but it appears just from the theory that omitting a very small part it's not important if you introduce some concrete process of the coherence, or you simply omit some small part. When what remains, it's some classical but stochastic quantity with Gaussian condition up to small terms quadratic, and this is really confirmed. Okay, so what we really see, this is the picture of the cosmic micro background temperature anisotropy, and this is as I said, to explain the reliable present observational data in both the polarization and correlation between anisotropy and the mode of correlation. One parameter inflationary models are sufficient, and this is just the yield results for this one parameter models, which I shall show in the next slide. And on you see extent agreement, apart from possible small features, I shall discuss one later. One feature is for multiple between L equal between 20 and 40, and enormously low equal to O. Okay, but once more, this is one the yield attraction for possible extension. of the simplest one parameter models, but okay, the same for the emote, and here you notice that here you don't see any significant deviation at all, and I shall, in fact, it will be reflected in one result about which I shall speak about the end of my talks. But once more, always this were pictures speaking about numbers always may be compressed, but from our observations we have two new fundamental parameters, two new fundamental dimensional parameters. I would say that where the status is more or less the same as the status of the fine structure constant, so they follows from observations. And what we have from theory, in all models of inflation, in all variable models, actually in all alternative models, we have to take the small quantity as simply some given. I cannot present you any more deep derivation of this constant, but the second constant, the slope, can be derived, and anything the actual expression is a little bit more complicated. But the main result is simply that this dimensional parameter is expressed, which refers to properties of the universe and some long time ago, is expressed in terms of this quantity, which is simply shows how large is the present universe. So, because what appears here is the cosmic microwave background, temperature, and the Hubble constant. And what's more, anything with 10% convection, which I shall show you later, is simply that this quantity multiplied by this, by in models approximately 2 in the simplest models. Okay, and you can see it immediately. Okay, so what are these the simplest models? Once more, they are both internally consistent and have what is called the graceful exit from inflationary stage. Actually, I don't have time to discuss it more, but the main statement that the main with inflationary model, the main problem is not how to begin inflation. The main problem is how to end it. And many models were unable to produce a graceful exit. And so this the simplest models, which actually a little bit simplified variant of my original 1980 models. It's modified gravity, the so-called F over gravity. It indeed has only one parameter, which is fixed just by the first measured constant. And after that, we have this prediction, which is in a very good agreement with observation data, and it has definite target prediction for future primordial gravitational wave background, and non-trivial prediction that it is suppressed. So actually, a large class of inflationary models which predicts are much larger of the order of first power in the small constants are already excluded. And so once more, the remaining model predicts that this quantity is of the order ns minus 1 squared. So it's small, but not too small. Okay, and when the properties of these models that indeed there was a period in the universe which indeed we have something very close to singularity, where the Hubble parameter was of this quantity. And the same prediction, essentially the same prediction in terms of the number of e-faults, is for if we assume a scalar field model with this asymptotically Higgs-like potential, a large phi, and strong non-minimal coupling. Strong and the sign opposite to the case of conformal coupling. The first it was actually considered by Spokane in 1984, but this model becomes much more popular when Ibuzuk and Kapitnikov tried to identify the scalar field, some strongly non-minimally coupled scalar field with the Higgs one. Okay, so once more, this speaking about first model, it can be read in this way. So it's a particular type of the so-called second of the gravity, but non-trivial and non-inspected fact that if we want to use this model at all, then nature requires us that this quantity, which is actually dimensionless, well, if h if the Planck constant is put to unity, it's not unity, and even it's not say number of elementary fields, which was assumed, say 100, suppose. It should be this one. Once more, I cannot say more why this number is so large. Apart from, once more, nature requires the observed smallness of primordial perturbations requires this number to be this large. Okay, and this is okay. This evolution of these models. It's just in the course of inflation. After it, and once more, what happens after inflation? After inflation, first you have rather short the miniature stage, but actually it decays due to the process of decay of the scalar particles in this model, just because it is a specific type of scalar tensor gravity. It exists as scalar particle and it decays. And once more, the advantage of this model, but you don't need to introduce any new model for decay. It's the same quantum gravitational process which you produce perturbations. And then you okay. And then once more, this model, of course, it's when logical. It can be considered either, as I said, that a specific kind of for the gravity, but once more, very specific kind in which this coefficient is first much more than is unity of the order, as I said, 10 power 9, and much more than this coefficient. But once more, it's another way that it was shown that it can be considered, as an approximate description of a second model. That's why I said that, in fact, from the phenomenological inflationary point of view, that these two models are the same. And this follows simply from the fact that during inflation, phi is algebraically related to the richer scalar R. And so, in particular, that's why the prediction for the strongly non-minimum couple of this model are the same as for this potential strongly non-minimum couple are the same as for this model. And that's why it was interesting to consider what happened in the mixed R-squared Higgs models, in particular when we have two scalar fields just due to this effect of the strong coupling between phi and R. It appears that this two-field model is effectively one field model in the course of inflation. But of course, that this is breaks after the end of inflation. It has some attractiveness from the quantum field theory point of view. I don't have time to discuss it. And this is its effective potential in the Einstein frame. But the main result, the most important result, that in the attractor regime, it's one field inflation, which can be also considered as a specific type of R plus R squared model. But we've simply redefined the value of the scalar field of the scalar mass. But all this is broken after the end of inflation, and actually this mixed R-squared fixed model appears to be very interesting in the post-inflation regime, and it appears that the most effective channel is through particle creation. It was investigated first in this paper, and it also appears that for some specific value relation of the parameters, it's possible to have tachyonic preheating. Once more, it's very I only present here the reference, but I don't have time to discuss more. But let me only show you what for some specific values of the coupling parameter you have, yes, it it's possible to have the resonance. But once more, there exist many subtle effects, but it appears that on average, I will say, but for average, still, you may say, indeed, the preheating occurs faster in these combined models as in the Higgs model, but the effect is mainly due to the effect of a strong non-minimal coupling. If you consider the original R-squared models, but with a channel of scalar decay not to minimal coupled non-conformal scalars, but to strong coupled, you got the same result. So once more, the statement is that in this mixed model, that critical heating temperature is of this order, and it's mainly the main effect actually just due to the assumption of a strong non-minimal coupling. Okay, and so now speaking about perspective of future discoveries, we have, I would say, two certain predictions. It's another case that this one parameter models will be falsified, but okay, once more. So, but in both these models, R-squared and Higgs, we have a target prediction. So different predictions. Once more, it can be falsified, but it's a prediction that this R is equal to 3 multiplied ns minus 1 square. Once more, it's small, but it's possible to measure it. Then more precise measurements of ns minus 1 expected for future. It just gives us a possibility to define the quantity capital N, which is slightly different, as I showed in both R-squared and Higgs. And Higgs between 54 and 50 and 58. So it gives us about new information. But really, what may nature may require us that we should have some more.
Let me suggest that you move to the conclusions so that we can keep the time for questions.
And so yes, and so in fact that, and so finally non-local, yes, indeed, non-local feature in the scalar power spectrum cosmological scales, which I showed you. And second, if it will be proved that some of the observed black holes are actually model of black holes, that we have to go to complicate this model. So it's possible to generate peaks in tax in the primordial power spectrum. In particular, I just show you some exact illusions which even produce that features with power suppression at small scales, and which is usually also additional oscillations. And let me very shortly mention the most recent paper, the most recent analysis of this type of spectrum. Well, the statement is, well, as was previously known, if you look only at anisotropy, it appears that the assumptions were the most, unfortunately, and this is actually the main result of this, that just adding the equalization data, it appears that equalization data does not support the suppressions. So I would say that though these models are not completely excluded, they present day, you don't see any necessity to go beyond this one parameter in models at large scales. And once more, let me only show you that if we really regarding primordial black holes, we in this paper we really produce some new mechanism, mechanism to produce these features at small scales, and this is to field inflation with large kinetic couplings, and in these models you can obtain also large additional peaks in the primordial power spectrum of scalar perturbations, which is needed to produce primordial black holes. And the additional feature, because that there was a question in some previous talk. So this produced another mechanism to produce additional gravitational peaks in the gravitational wave in background due to the second order effects. And so indeed, my conclusions that we have some critical inflationary predictions which are confirmed in one parameter models that we have target predictions for the quantity R, and this prediction is the same for both the Higgs and mixed squared models, where the actual values are slightly different. So inflation in F over gravity represents a dynamical attractor for slow rolling scalar fields strongly coupled to gravity. So some interesting behavior, actually very interesting behavior in the post-inflationary period in the mixed R squared models, but typically the heating temperature is high, and this effect is mainly not due to all the subtle effects, but due to large non-minimal coupling to gravities. And finally, so speaking about local non-scale free features at cosmological scales, if you consider both anisotropy and polarization, data they do not favor them. And speaking about possible features at small scales, it's possible. It's possible to add to complicate inflationary models, and then from the point of introducing a new parameter that you have, if nature will require this, we have to introduce at least two new parameters, and this can be checked both by observation of primordial black holes and the corresponding peak in the primordial gravitational waves. Thank you.
So thank you, Alexei, for this very wide talk with a lot of information. I'm afraid we have time only for maybe one question from the audience. Your talk has a lot of references as well. So if there are no questions, the material is there, and I propose to move on to the next speaker, who is Frank Eisenhower of the Max Planck Institute for Astrophysics in Garching, an experimentalist's view on black holes and gravity, the galactic center and black hole. So Frank, it's your turn now.
Thank you very much, dear Chairman, dear Professor Stodelikin. Thank you very much for your very kind invitation to give this opportunity to present here experimentalist view. So you asked me to give this experimentalist view, and so I will restrict myself to it because there will be another talk just after that by Professor Sakharov, who will then talk about the implication for theory and our understanding of gravity. So let me go to this presentation, and I'll start with this photographs from the control room of the observatory, which you see in the background. And here I want to start with the top right. Actually, this is my kid's view a few years ago, which is at the wall of the observatory. And this is in a way also my view of black holes as experimentalists. So black holes are black. They are surrounded by stars, which move, and for us are the main tools to probe the gravitational potential. And if you zoom in, there's emission which is coming from a accretion disk, and less what I will focus on from the jet in the shadow here in the center of our Milky Way. Now, the experimentalist view is what you see here when you're at the observatory. On the right side, this is now what we call acquisition cover. It's like looking through an eyepiece through one of the telescopes, and then you see the center of our galaxies. You see a lot of stars and not a black hole, but you see the stars move. I will come to that. And the even more modern view is on the left side. I can't show you directly an image. What we observe here is we combine telescopes to make double slit experiments. And from the entity of this experiments, you do a Fourier transform and you come again to images. And you see here a zoom in what we've observed this year by another factor 20. And you see a handful of stars very, very close to a central object, which you see all the time, which is the black hole. This is Sagittarius A star. And so what is this interferometry and what is this instrument which we call gravity, which was specifically developed to observe the galactic center? Well, in short, it's the world's largest and sharpest optical infrared telescope. So we do that by combining the 4 biggest telescopes from the European Southern Observatory to then achieve milliarc second resolution imaging at a few 10 microarc second precisions. This is how accurate we can measure positions. And all of that are a good 1,000 times more sensitive than earlier interferometers have been able to do so. So I will not go into the technology here, but please let me give reference to the collaboration which has built this instrument. So we are a handful of observatories, institutes, and together with the European Southern Observatory here in Europe, in Germany, in France, in Portugal, who've built this experiment. And so I'm presenting here on behalf of the collaboration. So this experiment has achieved really a revolution in high angular resolution astronomy. I won't have time to go in the aspects of the exoplanets, but I want to touch a little bit on the supermassive black holes, which we can now also observe at cosmological distance in the form of broadline regions and active galactic nuclei, which you see on the top left. And the real focus will be on the galactic center results, which are here displayed on the right, and which I will go to. And indeed, the gravity experiment was to contribute to testing the black hole paradigm. And we are very proud that this field has been awarded with the Nobel Prize last year to Andrea Ghez and Reinhard Genzel for the discovery of the black hole in the center of galaxy, and to Roger Penrose to actually give the theoretical foundation that these objects must exist if a concentration is high enough, because it will inevitably collapse to a black hole. So how do you test this paradigm as experimentalists? Well, you have to measure the size and measure the mass to see whether it would be consistent with event horizon, and then you need a theory. So you need to test the theory as well. And I'll introduce the subject with a zoom what happened over the last 40 years. So if you look towards the center of the galaxy, you see nothing because there is dust. So at the optical wavelength, you cannot go there. And the first trick was to go to infrared wavelength. And so I'm jumping in here now. At infrared wavelength, like in X-ray, you can look through the dust, and then you see many stars. Now you have to sharpen the telescopes. This was our big quest 20 years ago to overcome the atmospheric turbulence. And then you get diffraction limited images from single telescopes, and you see star moving around. And so you already see there must be a dominant potential point source which dominates the potential, the black hole. And now the last development since 5 years, we are observing by interferometry, this combination of telescopes to form even sharper images. So we zoom in by another factor 20. We can follow the motion of the star day by day, and then we can even see within 1 hour a jitter of the central source, the black hole, which we then can interpret as a motion very close to the last stable orbit. And so with this new instrument, gravity, the trick to all of that is that we can come to a very high, what we call astrometric precision. This means ability to measure the relative position between 2 objects, here the black hole and the star, which is falling around the black hole, to a level that we can see the motion of the star from day to day, despite this is 25,000 light years away. And with this precision now, which you see here, then in 2018, it was going through its closest approach, then you can do a mass measurement. This is what you see on the left, it's the orbit on sky, and on the right side, you see the radial velocities. This is the line of sight velocity. And if you have both of them, you can solve Newtonian laws completely. You get both the mass and the distance to this object. And this is what we get now to well below 1% accuracy. We know the mass of the dark object and the distance to the dark object. So we have the first 2 things fulfilled. Now we need to get the size that this mass is truly within a region comparable to the size of an event horizon. And this is traditionally done in the radio. So on the top right, you see radio emission. You see mostly synchrotron emission from gas around. And then you also see a bright point source in the middle. And you can measure the size of the point source by combining telescopes across continents, even in the radio. I don't go into the detail, but in the end, what you find is that this radio source is of the order of few Schwarzschild radii. But is this radio source truly the gravitational mass, or is it something else? And this is now where our gravity experiments come in. So now I have a similar experiment like following the star around a black hole, but now not over months, but within 1 hour, measure the position of the emission from the black hole relative to the star, which is de facto not moving within an hour, or linear motion, which you can easily subtract. And what we find is that the emission around the black hole is moving in a pseudo-circular motion, which, if you would translate it to physical units, is in about 45 minutes at 30% the speed of light within an astronomical unit around this mass. So we now know that this mass must be included. This is a few Schwarzschild radii, what you see here. So we now know that this mass must be included within a few Schwarzschild radii. And this gives the summary. It's both historic, but also from in physical dimensions. So from on the horizontal axis, the distance to the black hole. On the top, you see it in units of Schwarzschild radii. So farther out, you see the motion of the stars, and then you go in, get closer and closer. This is to the left. And on the vertical axis, the enclosed mass, and you see it doesn't change anymore if you go farther in. This means this potential is dominated by a single object. So we have now the 4 million solar masses within a few Schwarzschild radii. I do not touch on the astrophysics. I will keep that slides if there are questions later. So the main theme here is just to give you the theme is about the magnetic fields, which we can tell a lot, and we find it that it's aligned magnetic field probably with the black hole spin, and the magnetic field is dominating the energetics in this object. So now we come to the last element to come to the black hole paradigm, which is that we need a theory and it needs to be correct. So for us, it's this Einstein's theory of general relativity, which we want to test. And the experimentalist view here is also a simple one in a way. So we have a curved space-time, and how can you probe curved space-time? Well, you can do a clock experiment. This is, you know, from the clock experiment on satellites, for example. Or so compare how fast time goes on the outside and on the not on the inside, deep down in the potential. Or you make an orbit experiment. You follow test particles. And both of them we've done with gravity and with the other instruments. And the first one is indeed what was this gravitational redshift. This is this clock experiment. We do not measure directly the time, but we measure the speed of the time, and the speed of the time for us reveals as a redshift, like a Doppler shift. So we measure it in the spectroscopy of the star for an orbit, which we perfectly well know. And then we can measure the deviation from what the Newtonian prediction would give. And this is what you see on the right-hand panel, the deviation from a best fit Newtonian orbit and the excess redshift, that is the time delay from the gravitation, which is shown here. And this peak around at 2018, this is when the star comes closest. We call it Perry approach, and the time goes slower, the redshift goes up. And so this is a very significant detection by now by our group, but also by the group from the Keck Observatory then a year later. And so we could go on to the next one, which is more difficult, which is the Schwarzschild precession. So this is that the orbit of the ellipse, that the ellipse is not closed, but that the ellipse rotates within the plane of the orbit. This is called the Schwarzschild precession, which was first discovered in Mercury. One of the motivations for Einstein to come to a theory. And so in 2020, then we could, for the first time, detect it also now around this supermassive black hole. And the observational signature is now a location. This is what you see on the right. And again, you see the deviation from one here from the x-coordinate in this image relative to a best fit Newtonian perfect ellipse, which is closed. And you see when you go through peripassage, then you get on a new ellipse. And so you come to a linear deviation from the old one, which we've been able to detect to a 5 sigma in 2020. Then in 2020 was hard because of the COVID shutdown, we couldn't observe, so we could only get one more point confirming the result. But this year now was again fantastic, and you see that the position of the deviation from the Newtonian orbit is very nicely now shown at very high significance for the Schwarzschild precession. Indeed, if you look on the left side, this is now we followed the star already twice around the black hole. The red orbit is 16 years ago, still observed at poorer accuracy. That's why the error bars are large. And now you see the position this year in black symbols in 2021. Accuracy such that you don't see the error bars anymore, and you see very nicely the Schwarzschild precession. You're on a new tilted prograde orbit. And so this brings me to tests of general relativity, and I'm going here to a diagram adapted from SALT, where you see from the left to the right the mass of the central object, and on the vertical axis the strength of the potential. So at the very top you see black holes, and then there are these traditional classical tests in the solar system and nearby white dwarfs and pulsars. They are in blue. Then you have the tests from the gravitational wave, which are very close to the event horizon for stellar black holes, so here in the middle on the top. And then you have tests and observations of relativistic effects for supermassive black holes, so million to billion times the mass of the sun on the top right. And the galactic center actually has a very sweet and beautiful spot here, because other than all the other objects here, actually we can probe a quite large separation or depth of the potential. We can go out from where already the potential from the surrounding star dominate. Then we can go to orbits of stars closer and closer, down to the orbital motion of hot gas very close to the event horizon. These are the three symbols. And again, please let me point to the presentation a few minutes from Professor Sakharov, who will tell you what you can learn from the orbits of the stars about the theory of general relativity. So these are elements of equivalence principle, limits on scalar fields, fifth force, all of that, variations of the fine structure constant, but I'll skip that. Instead, let me give an experimentalist view outlook on what to come next. And the thing to come next for us to measure is the spin of the black hole. So this is a rotating space-time illustrated here in this animation to the left. And the most important or the easiest imprint of this rotating space-time is that the last stable orbit, this is where you can still have stable orbits of matter around the black hole without being dragged into the black hole, actually for given mass gets smaller, it shrinks. So you have a higher period of the orbital motion, and you have a higher gravitational redshift. So this is the imprint of the spin for given mass. But you also see that the size of the last stable orbit, the period, and the redshift are also depending of the mass. So you are fully degenerate with the mass of the black hole and the effect of the rotating space-time if you go to the last stable orbit aspect. So can we do it differently? And yes, it's again like with the Schwarzschild precession, it's the beauty of orbit experiments. So if you have a test particle, which is now farther out, not at the last stable orbit, you will again get a precession. This case, a Lenz-Searing precession. This means the ellipse of the orbit will not rotate within the plane of the orbit, but the plane of the orbit will rotate with the spinning space-time around the black hole. So this is the next goal we want to do. The problem here now, or the challenge, let's call it like that, is that this effect is smaller than the Schwarzschild precession. And so what you see here in this calculation on the right side is for a star which is 10 times closer than the star which we have been using so far. You see two orbits, one where the lancering, so the spin is included, and one which only has the Schwarzschild precession. You see, they are very difficult to discriminate. Indeed, if we would keep the star which we have, it will be almost impossible to measure because the star is perturbed by other stars in the gravitational field. Even though they only have a few mass compared to a few million mass of the black hole, at that level they will perturb the orbit and also unknown objects, which is illustrated here on the lower left. Again, I don't go into the details. The bottom line which you have to take away is you have to go as close as possible to the black hole. The effect gets stronger and the density of unseen objects is smaller so that the orbit is truly tracing the potential. And from the density profile of the stars, we expect to have about of the order 1 or a little bit less of such stars, very faint in the center, K20. This is a number how we describe brightness. We call it magnitudes, larger numbers is fainter, and such a star is what we are looking for. This is roughly a factor 100 fainter than what we've seen so far. And so this is now what we are looking with this gravity experiment. And after this bright star, S2, which probed the potential for the Nobel Prize, has moved away. Now the region is dark and we can see fainter objects. So the first one is already of this order of magnitude. Unfortunately, the star which we found last year is on a foreground or background orbit, so we don't see it move. But now this time, see on the same scale, we have seen now 3 more objects coming in. Some of them were known from earlier times and then lost in a very dense inner field. So now we have a handful of stars as close as the star which we the Nobel Prize was then coming from. So we have one which has a shorter period, it's called S55, and we have one which gets even closer than S2, this is the star S29, and so this is from a paper to come soon, where we now can combine all of this potential, these probes for the potential to make progress. And this is what you've seen in the very beginning on the Schwarzschild precession, on the mass distribution, and so on. So this will ultimately now bring us towards the spin of the galactic center black hole. The stars which we have observed are not yet going deep enough to the potential on the right side. Different colors means different months this year. You see this is moving like a pool billiard, all the stars moving around. But the advantage of going faint, and this again, don't look into the details of this astrophysical plot on the left. If you go faint, what you should take away is you go to lower mass stars, and lower mass stars are colder, and colder stars have many more spectral lines. This is what you see on the top. The stars which you observe right now are massive and hot and have only broad lines, this is the lower part. But if you go faint, you will have many spectral lines and you will measure several order of magnitudes more precise the Doppler shift or the gravitational redshift or the redshift, as we see. This will come with the next generation of telescopes here, the extremely large telescope, to get to the spectroscopy where you need the photons. And then actually, if you're at this 100 meter per second radial velocity and the positions from gravity, then you are in this world of pulsar science. So you will not only be able to reveal the lancering precession, but you will also, if you have multiple stars, disentangle the quadrupole moment of the gravitational field from the spinning space-time. It is something which in general relativity is strictly linked. This is amongst others called the no-hair theorem, but not for all theories of gravity. And so we will be able to test now these things which go to the very core of GR, the cosmic censorship, the no-hair theorem. And in that we are then in a good company with the other projects which are coming forward, which then will really allow us to really test against alternatives. For the moment, we are proving GR and we are confirming GR, but we are not in a position to really discriminate yet other theories. And if you take a very generic view here, I'm following Cardoso and Pani review from 19, so you see how big is the last stable orbit, or how big is the Schwarzschild radius, or how big is the quadrupole moment for given spin, and parameterize this as a epsilon. You see from the gravitational wave experiments, from the shadow experiments and rings, we already have this order unity also here with gravity, what you've seen from this motion close to the last stable orbit. But then in the next years, we really expect to then reach levels of 10% when we combine gravity with large telescopes. And then in the future, then when LISA comes in with all its beauty, we will really be able to discriminate. And so what we do here on the observatory on ground is we've just started a new project now to equip all of these telescopes with laser guide stars and yet better technology to bring us to these faint stars, which I was illustrating before, to measure the spin of the black hole, hopefully in the next 10 years to come. Thank you very much for your attention, and I'm happy to take your questions.
So thank you for this amazing talk, very interesting. And so let's have maybe a few questions here. I have a question myself. I don't know if I can start with this question, which is, aren't you afraid of effects of the accretion disk? At some point, there's some accretion disk that should be around the singularity, around the horizon.
Yes, there is an accretion disk around the black hole, but the one in the galactic center is very, very low mass. So this is the thing which is actually very particular about the galactic center. So it's about typically a factor million less luminous, which also means a factor million lower mass accretion than many of the black holes you see. So right now, just to give you a little bit order of magnitude, very close to the black hole, we can measure the mass. Better, I would say, the amount of accretion from radio and also here from the infrared emission. It's of the order 10 to minus 8 solar masses per year. So indeed, to add up one solar mass, the black hole is 1 million, you would have to already wait 100 million years. Indeed, our black hole in the center of the galaxy is starving, and this is why it is so beautiful. Actually, you see in this more typical active galactic nuclei, which are easier to observe, they are dominated by the jet in the accretion. Here it's even the question, not only the accretion disk, but what is from the jet and what is coming from the accretion itself. But the black hole in the galactic center is actually quite forthcoming in that respect, that this one is not.
Thank you. Thank you so much. Other questions? If not, then I would like to thank Frank for this talk, and I would like to invite
thank you very much.
Alexander Zakharov of the Kurchatov Institute, who will be giving a talk on orbits of bright stars near the galactic center as a tool to test gravity theories. Welcome.
Do you see my slides?
Yes, we do.
Sorry, I started from the end. Thank you very much. First of all, I would like to thank organizers for this nice opportunity to present this talk just after excellent talk of Professor Eisenhower, because I like this trajectory very much because they are so beautiful. So and also, in his book, Chandrasekhar said that black holes are one of the most perfect macroscopical objects in the universe because it's described only with practically two parameters, mass and spin, because astronomers do not believe that there is significant charge in these objects. And so it's in some sense, it's again, I am repeating that it's one of the most beautiful objects in the universe. But some time ago, I followed Zildovich lecture, and he said, I dislike null-Hare theorems. But, in the last year, it was, let us say, it was like general recognition of importance of this branch of science, because Nobel Prize was given to Roger Penrose, Reinhard Genzel, and Andrea Ghez for their studies. So it is these three persons who was declared as winners in the last year. But in addition, many other famous scientists got important prizes in the last year, such as Roger Blandford, Andy Fabian, Clifford Weil, and Saul Tikolsky. So it was like a year of black holes. But Nobel Prize Committee also said that there are all problems are solved, and also we have to test our gravity theory under extreme conditions. Sorry. It's outline of my talk, references, and also I'd like to note that 3 Nobel prizes in physics in last 4 years was given for gravity theory practically and related issues. And also in last years, important results were obtained in gravity theory, like LIGO-Virgo discovery, and also discovery of kilonova gravity, Keck, and new tests of general relativity. And also 2 years ago, Event Horizon Telescope reconstruct image near M87 center. So, and also, as Professor Eisenhower said, it was confirmation of relativistic precession for S2. It's these 2 people, and also only, I would like to know that only 4 women physicists got Nobel Prize over more than 200 men in this. It was, let us say, strong violence of gender balance. But Kip Thorne also wrote book, and also he listed Andrea Ghez among the most important scientists in the field. But for many years, people expressed skepticism in respect to existence of black holes. Even in Nature magazine, you could find articles with these titles, like black holes do not exist. And even probably one of the first person who expressed skepticism was Albert Einstein. He published an article in 1939 when he said that the essential result of this investigation is clear understanding as to why the Schwarzschild singularities do not exist in physical reality. And his assistant, Peter Bergman, wrote one of the first textbook on general relativity, and he also showed almost picture of gravity from precession of S2 just near the galactic center as the cover. And also he noted that there is no chance to detect such object with Schwarzschild singularity, because there is no chance to, because it cannot be formed with moving object, because Einstein considered this case. But astronomers believe that there are black holes in center of many galaxies, including our galaxy. It's also list of estimates of black hole mass in center of our galaxy. And also one of the most beautiful things is just to how to evaluate mass of black hole, and not only mass, but also potential, gravitational potential in the galactic center, analyzing trajectories of bright stars. That is, again, that is S2 star orbit, but also, again, following Professor Eisenhower claims, there is elliptical curve. It's a first approximation, it's elliptical curve. And also, you know, Robert Hooke wrote a letter to Newton, and he said that it's probably we call it Newtonian law, could be explain Kepler laws. And Hooke wrote this picture where he tried to prove that you have this law and to explain Kepler laws. And also it's also a pleasant thing that in Bremen there is a special institution, our space institution, which located at Robert Hooke Strasse. But also you remember particle physicists remember famous Rutherford experiment. He used alpha particles just to evaluate gravitational nuclear potential, sorry. And also it's analyzing trajectories of particles, you could evaluate potential. Keck and VLT gravity collaboration use trajectories of bright stars to evaluate gravitational potential. It's very typical, but it's very complicated problem. Also I would like to remind one of the first person who analyzed estimates for masses of black hole, the galactic center, was Martin Rees, and many years ago, almost 40 years ago, he said mass of black hole has to be around 5 million solar masses. But about adaptive optics, you know, Kolmogorov, Obukhov, and Tatarsky, Kolmogorov, Obukhov, and Tatarsky, practically mathematicians, they introduced theory of turbulence. And so in this theory of turbulence is using for development of adaptive optic techniques. That is answer that is sometimes people are saying mathematics is practically useless for technology, but that is illustration that is not. And so Kapitsa said that many things were really invented in Russia, but efficiently realized in Western countries. And also, you know, here, you know, Charles Townes, he was, let us say, in some sense, advisor of Reinhard Genzel, and practically Reinhard Genzel in his interview said many things were only realized now, which was suggested by Charles Townes. But also that is old paper of, let us say, Charles Townes and Reinhard Genzel in the subject. About adaptive optic techniques, laser is one of the most important component on this, and the Nobel Prize Committee showed this picture in their press release. So analyzing structure of atmosphere, small winglet could improve a wavefront and to produce flat wavefront, and after that, let us say, image reconstruction started to be much better. That is illustration how good maybe this image with adaptive optic techniques, for instance, for 30-meter TMT telescope, which is developing now in Hawaii. But also important thing that is, it's also illustration for this case, it's telescopes for different cases. And here also you see that is trajectory of bright stars, they are moving along elliptical trajectories as a first approximation of their trajectory. Of course, you know, if you take into account general relativistic correction, this trajectory have to be precessed. It's one of the important problem and target for observations with 39 telescope, European telescope, which is constructed now in Chile. It's also this S2 star orbits, and also it's a picture of this telescope, and also about gravity project. But if you have a standard mass distribution, you have a shift of pericenter in opposite direction, and here is illustration that is here if 10% of mass is inside orbit is in extended mass distribution, you have shift in opposite direction. It gives opportunity to constrain dark matter mass models when there is significant concentration of dark matter models mass inside orbit. And also it's, if you took some dark matter concentration of masses, you could constrain some dark matter models for these cases. And also you could constrain alternative models, because now previous theorists suggested so many alternative theories of gravity, and some of these models have non-Newtonian limit. In this case, you could constrain it like FR theories of gravity, as we did, and Yukawa gravity, and also we could constrain even massive graviton, because it's initial version of massive graviton theory were not very good because there are hosts in discontinuity and many other defects, but Claudia Duran built theory without costs and now started to be treated as respected theory because LIGO collaboration considered massive graviton mass as alternative for general relativity and got even constraint on graviton mass, like 10 to the minus 22 eV. And later it was improved, significantly improved, and currently it's around 1.7, 10 to the minus 33 eV. But also we constrained graviton mass from the available data for S2 star orbit. It's comparable value of graviton mass. That is list of estimate of graviton mass from our paper, and later Keck people, including Heath, Getz, and others, improved this data with their new observational data. That is was the impact of our studies. It was in review and also quoted by observers, including Heath and Andrea Getz and others. And later, if we assume that prediction of general relativity will be improved, in this case, we have to conclude that in principle, we could reach almost estimate of graviton mass of which was done by LIGO collaboration. I will skip this detail, and also we could constrain tidal charge, analyzing precession, available precession for trajectories of bright stars. But I will skip also the remarkable results of gravity collaboration because it was discussed in the previous talk. But also important thing, again, I would like to emphasize here that important thing that now many theorists propose theory with alternative theory when there is no Newtonian limit in these systems. But here in this investigation, it was observational confirmation that of universality of general relativity and Newtonian mechanics for this case. So because it's also very, and Newtonian mechanics have to be ruled out with very high confidence level, as one can see from this picture. And also gravity and later Keck collaboration confirmed this, let us say, refined these results about precession, about, let's say, gravitational redshift. And also gravity collaboration considered some alternative theories for orbit of S2 star. And also beautiful picture, you see, it's reminding of cover page of Bergman book. And also detection of Schwarzschild precession, it's also very nice. And alternative theories, fundamental theories. Recently also Keck collaboration considered variation of fine structure constant from observation of bright stars. It's also a very popular subject for investigation to consider variation of fine structure constant, which may be done from different kind of observations. And also we are also proud that our results were included in constraint on graviton mass in particle data group, including this, where there are also constraints from LIGO and other collaborations. And also a few words about alternative potential for elliptical trajectories. Recently, some group of authors said that they suggest some potential for elliptical trajectories, and also some list of these papers. And also important thing that there is a region when there is a constant density. Constant density, ball with constant density. It's key approximation in this approach, and also it was early it was proposed by Bilic and others. You see constant density. What about potential for this case? For this case, we have harmonic oscillator potential. It's because also there is many papers when they consider this case. But there is so-called Bertrand theorem. If there is a central potential, all bounded orbits are closed in the elliptical only for two potential. One potential is harmonic oscillation potential, another one Newtonian. It's very well-known Newtonian. And also Arnold considered this case. And if you can consider harmonic oscillation, you see that is phi angle. It's phi angle. It's an angle between pericenter and apocenter. And for this case, for harmonic oscillation, we have this angle pi over 2, and we have for that is a Newtonian potential is pi. But from observational data, you can see that in harmonic oscillation, potential is in center of elliptical orbit. And second, periods of orbital periods do not depend on semi-major axis as in Newtonian potential. So concluding, so that is the most important conclusion are listed here, and also so main conclusions, and also that is we could conclude that this harmonic oscillator potential is not suitable for galactic center because, as you saw from previous talk, so stars are moving, let us say, around foci, around focus of orbit, but not in the center of gravity, as it was predicted for harmonic oscillation potential. Thank you very much for your attention.
So I would like to really thank you, Alexander, if I can call you by name.
Thank you. It was a pleasure.
Your beautiful talk, and for keeping the time, even too much at the end, your conclusions, but so interesting. So I like to invite some the audience to ask some questions to the speaker. The audience is a bit shy, so let me make a very small comment to you. I remember you mentioned Zeldovich, of course.
Yes.
And I remember when I was young, I started reading a book by Zeldovich, and he was skeptical even about the cosmological constant.
Yeah.
Very skeptical. So this field has really changed a lot, and I personally am really amazed that you are now treating somehow the galactic center like a solar system where you test general relativity in a much stronger gravitational regime. This is just a comment.
It's a very good point, but also interesting thing. That's what is one of the most important issue. So orbits of bright stars are so beautiful. They are elliptical curves. If they're the elliptical curves, it has to be at the first iteration, it has to be simple theory, which is behind of this observational result. But as Bertrand theorem is saying that if you have all bounded curves are, let us say, if all bounded curves or trajectories could be described only with two potentials, only two, so nothing more. So if we do not see bounded orbits which are not closed, so it's simply Newtonian because we are far away from the galactic center. Newtonian approximation is very good. In this case, it's let us say direct, like Rutherford. So it was direct confirmation that it has to be nuclei. So it's unavoidable. So and about Zeldovich, also about cosmological so term, because it's very important issue. But let us say it's also some people saying that is introduction of Einstein said, the biggest blunder of my life, introduction of lambda 2. But source of this legend was, let us say, George Gamow book. Mm-hmm. So, but it's not reliable because also Soviet and Russian people knew that Gamow was great joker. So, and he introduced this joke. But after that, since many people were repeating this claim, so people were saying that it was really Einstein claim. But Mario Livio wrote a book recently that is also, he expressed skepticism that really Einstein said something like this. But many people are thinking also that is doubtful. So, but
Thank you so much again.
Thank you,
And,
thank you.
now it is
I'm
now-
stopping sharing.
Sorry. Yeah. Thank you.
Thank you.
Now the time to call Professor Jack Singal at the University of Richmond, who will be discussing about mechanics and evolution of supermassive black holes with AGN population studies. You are welcome to share your slides and give your talk.
Thank you. Can you hear me? How's my audio?
Yes, we can hear you.
And can you see the slides?
Yes.
All right, thank you. All right, well, it's great to be here in the middle of the night at my time. So let me start with a quick outline of where this talk is going. So first, I want to tell you why we should be interested in doing population studies on AGN, that's active galaxies. And then I will look at why this is statistically challenging, and then I will get to some results. So to start with the case for doing studies of active galaxies, in the context of this talk and fundamental physics, it comes down to what they can tell us about supermassive black holes. So as a reminder, when we have an active galaxy, we'll start with a galaxy. We call it the host. And in the middle, we have an accretion disk of matter, which swirls around a supermassive black hole at the center. The interaction of the black hole and the matter gives rise to jets of high energy particles that stream out both sides. The charged particles interact with the magnetic field in each other to send out light. Now let's consider what this would look like from several different perspectives. The radio emission, which is the lowest energy light, goes out in all directions, but the higher energy light moves more forward along the direction of the jet. So if we're looking at it from over here, what would you see? You would see two concentrations of radio emission at the ends of the jets, and that's the phenomenon of a radio galaxy. What if we were looking down here? If this thing was oriented to point at us this way, we would see the high energy radiation, X-rays and gamma rays coming at us. So if it was far enough away, it would be a point that's very bright in X-rays and gamma rays. And then if we're at some other orientation where we're out here, well, we would see some of the radio coming at us, some X-rays and gamma rays, and that's the phenomenon of a quasar. Now, what's going on at the center? Well, it's not, let's say, completely understood, but the leading paradigm for this is called the Blanford-Genaic mechanism, where the rotational energy of the black hole, the spin of the black hole, the energy associated with that, is extracted to accelerate the matter into the jets. And so if we think about that, if we have a more rapidly rotating black hole, that's more energy, we should have brighter jets. Now, the amount of matter that gets near the black hole is determined by how much gravitational pull it can have, and therefore its mass and the amount of material in the accretion disk. So we would think that if we have a more massive black hole, then we would have more matter towards the middle and brighter jets. And so the luminosity of the jets, the brightness of the jets, should be related to the rotation of the black hole and how big it is. Also, if we have a bigger black hole, we should get more matter to the middle and therefore a brighter accretion disk. So by studying how these galaxies change over the history of the universe, we are indirectly studying the evolution of the supermassive black holes. So again, as the reminders here of those things, now let's talk about the light that these put off, which we observe astronomically. The accretion disk is primarily hot gas, so we would expect that to be glowing in optical light, ultraviolet, maybe some X-rays. The jets are high energy charged particles interacting with the magnetic field and each other, so we'd expect synchrotron radiation, we'd expect particle processes and so on. So we would expect them to put out light in radio, X-rays, higher energy X-rays and gamma rays. We also have in some situations a so-called torus of dust surrounding the accretion disk, and so that we would expect to glow in infrared light and to possibly obscure the accretion disk at certain angles. So with those astronomically observable quantities, the different kinds of light, To learn about the nature and evolution of supermassive black hole systems, we could do two things. One is we could study a few nearby objects in great detail, ones where we can resolve them and see where the radio light is, where the X-ray light is, where the optical light is, infrared, etc. Or we could do population studies of tens of thousands of unresolved objects, the ones that are way out there, so they just look like a dot to us, to find out how the radio, infrared, optical, X-ray, and gamma ray emissions have changed over the history of the universe and how they're correlated with each other. And that's what I'm talking about here. So we like to access, in the terminology here, the population distributions and correlations in these different kinds of light. And to do this, we can utilize publicly available data from large-scale surveys. Just as a sampling, we have the Sloan Digital Sky Survey. It's a great resource in optical light. From radio, we have the FIRST Radio Survey. For infrared, we have WISE and Spitzer, X-ray, Chandra, XMM, gamma ray, we have Fermi. That was the case for. Now let me briefly talk about the statistical challenges that arise when we try to do population studies of many thousands of objects. Let's consider this plot here. This shows the radio luminosity, let's just call that brightness for now, on the vertical axis and the optical luminosity on the horizontal axis. So we're looking at the luminosity versus the luminosity in two wavebands, radio and optical. And we could ask the question, are these luminosities correlated? Well, they certainly look correlated. The top is real data. This is real data from real objects. And the bottom is simulated data, where we simulate a bunch of objects and then view them with a flux limited survey. I have to tell you that these simulated objects, because I made them not correlated. The luminosities, the radio and optical luminosities of these objects are not correlated. They appear correlated to us because of the observational selection effects and because the luminosities have similar evolutions with redshift. That is, the luminosities both change over the course of the history of the universe. And the moral of this story here is that the observed correlations that you might see do not necessarily accurately reflect the intrinsic correlations of the luminosities. That is in flux limited data. That is where we're not seeing every object. We only see the objects that are bright enough to be included in the survey. As a reminder here, let's talk about the terms flux and luminosity, just for the non-astronomers. The flux is how bright an object appears to us. It's what we measure. The luminosity is how bright an object actually is, how much light is actually putting out, and they're related by the distance, the square of the distance. So with that in mind, let's now take a look at, for example, if I take data in both optical and radio for a bunch of objects here. This is about more than 5,000. Here we have a plot of the optical luminosity versus redshift, and here we have a plot of the radio luminosity versus redshift. Remember, these are how bright they actually are. And let's remind ourselves that when we're saying redshift, that also means distance, how far away. And because of the time it takes the light to get here, that also means how far back in time. So we're seeing the objects at higher redshift as they appeared farther back in the past. But focusing on the distance for a moment, as an object would go to higher and higher redshift, its flux is going down, because remember, the flux, what we measure, had the square of the distance on the bottom. And so the surveys are limited by flux. They can only see things down to a certain dimness. And so we are missing these objects here and these objects here. We are missing potentially most of the objects because their flux is too low. They are too far away in redshift. And so you can start to see here, we're missing potentially most of the data because of the flux limits. And this is why such a radically induced correlation could arise. Now, determining the correlations between the luminosities and the changes in the luminosities over time with redshift is a nuanced statistical challenge that I won't go into the many techniques here to do this properly, but I instead want to go straight to some results. So let's look at the luminosity evolutions, the changes with redshift. Now, luminosity evolution, that's the term for if a class of object changes in average luminosity over time, okay? So let's parameterize it this way, where we have the luminosity in this wave band A, optical, radio, infrared, whatever, as a function of redshift, the average luminosity. We will parameterize the way it changes this way. We'll say it has some average luminosity at redshift 0 times some function which says how the average luminosity changes with redshift. We would call that the luminosity evolution function. It could be possibly a power law like this, or it could be a more complicated function in order to have it not just keep going and going up and up and up. Something like this. We'll use the form on the right. So this would be the best fit correlation function between luminosity and redshift. So let's then, it comes down to this parameter K here. If this parameter K is positive, then the objects are getting brighter on average in this waveband. If we go to higher redshift, that is back in time, that means they were brighter in the past. So to go to a result here, let's take the optical and radio luminosity evolutions from the data set of optical and radio fluxes that I looked at before, and applying all of the statistical techniques that I mentioned but won't get into, we can find the best fit K factors for optical and radio. And they're here, you can see for optical, it's about 3.5. For radio, it's about 5.5. And remember, if K is positive, that means the luminosity evolution, the objects get brighter as you go to higher redshift. So we would say that quasars have undergone significant evolution with redshift in both the radio and optical bands. Both of these are positive, but greater evolution in radio. The radio one is higher. Quasars were more radio loud at high redshift, that is in the past, than compared to present. And so now we can go into some results for supermassive black holes based on that. First of all, quasars in general were brighter in the past. We also see that they were more radio loud in the past. That is, the ratio of radio to optical emission was higher in the past compared to now. So we would say that going back into the past, the jets, which put out the radio emission, were brighter, bigger relative to the disks, which put out the optical emission. Remember that the radio emission comes from the jet and the optical emission comes from the disk. So we would say that supermassive black holes used to be spinning faster because remember, it's the spin of the black hole which gives rise to the jet. Okay, so in the past, supermassive black holes were spinning faster. Now we'll look at what happens when we turn toward the optical and infrared data set. So this is a data set now where we combine the optical observations from Sloan Digital Sky Survey and the infrared observations from WISE. Here you can see again the many missing objects due to the flux limits. And again, if we come in and do all the statistical stuff, which I won't get into, we find the best fit luminosity evolutions. The optical luminosity is coming out the same as we saw before. That's good. That's consistent. The infrared luminosity is coming out a little lower. So again, around 3.3 for the optical, but the infrared is lower, 2.7. So we would say quasars have undergone less evolution with redshift in the mid-infrared band than in the optical band or the radio band. So again, to get to some implications, again, both of these were positive evolution factors. So the quasars were brighter in the past, and there were also more of them in the past. Quasars were less infrared loud in the past. The ratio of infrared to optical emission goes down as you go to higher redshift as you go back. So that would tell us that the source of the infrared emission, the dusty torus, the multiple tori and multiple quasars, are getting smaller as we go to the past or bigger as we go from the past to the present. They're growing over the evolution of the universe, which makes sense because more dust is available as you come more toward the present. Also, I didn't get into it here, but there seems to be just a minimum infrared luminosity for quasars. And so we can then take that as confirmation that infrared emission is dominated by something other than the jet. That is, even the weakest spin black holes with the weakest jets still have a torus of dust. Now, to rush forward because of the limited time, let me talk about the luminosity correlations. So remember, we want to get to whether luminosities in different bands are correlated intrinsically. That is not what we observe due to the flux limits and the redshift evolutions, but how correlated they actually are naturally. That's actually encoding two questions. So one is, how closely are they correlated? That is, if there's a function that describes their correlation, how closely do they adhere to the function, or is there a lot of scatter? And another question is, what is the form of the correlation? That is, the luminosity in one band being related to the luminosity of the in some other wave band is some power law. And if that power law is 1, then it's a linear correlation. If that power law is 2, then it's squared, etc. Now, focusing on the latter, and again, without being able to get into all of the statistics behind it, here are some results for the red shows the radio and optical data, and the green shows the infrared and optical data. And where these lines intersect 0 is the best fit correlation. And so you can see that the radio and and again, this is the best fit form for the correlation. And so the radio and optical have a correlation which is far sublinear. This is about 0.25. The infrared and optical have a correlation that's much closer to linear. It's about 0.8. And so the correlation is stronger between infrared and optical than radio and optical. And so for some conclusions about black holes from that, the optical and mid-infrared luminosities are very highly correlated, both in the degree of the correlation, which I didn't show, and the power law form, which is close to linear, which we just saw. While the optical and radio luminosities are less highly correlated, again, both in the degree of the correlation and the power law, which is far sublinear. And this does make sense in the picture we have of jet launching. If the accretion disk luminosity is primarily responsible for the optical and mid-infrared, because the accretion disk heats the torus, which then puts out the infrared emission, while the radio emission depends on both the black hole size, which will be correlated with the accretion disk, but also the spin of the black hole, which has nothing to do with the accretion disk. So to wrap this up, some overall conclusions that we can have about population studies and the evolution of supermassive black holes. So first of all, large-scale population studies of AGN are enabled by large extragalactic surveys and statistical techniques that we have to access the true intrinsic distributions from flux-limited data. We've employed some particular techniques here. We can estimate the luminosity correlations, and we can estimate the luminosity evolutions with redshift. And a fairly consistent picture is emerging where these active galaxies were brighter in all wave bands in the past relative to now. I didn't show the results for, say, gamma rays because of time, but all wave bands, radio, optical, infrared, gamma ray, X-ray. We also see that AGN activity was more common in the past than now. Considering the weaker evolution in optical than in radio. Radio evolution, luminosity evolution was stronger over time with redshift, relatively brighter in radio in the past. We see that jet emission in the past was proportionally brighter when compared to accretion disk emission. The weak correlation between radio and optical luminosities, relatively weak, supports the Blandford-Janaic model of the black hole spin launching the jets. Therefore, the spin of the black hole affects the radio emission, but not the optical emission. Black holes were spinning more rapidly in the past relative to now. That's how the radio evolution is brighter in the past. The strong correlation between mid-infrared and optical luminosity supports the picture of infrared emission from a heated torus, which is heated by the accretion disk, which is putting out the optical emission. And the weaker infrared luminosity evolution relative to the other bands indicates that the torus emission is proportionally more important at later times than earlier, so that the tori have grown from earlier times to later times. And I'll stop there.
So thank you so much for this interesting talk on very subtle properties of AGNs, and so it's subtle for me because I don't understand astrophysics. But so I like to invite the people from the audience to ask a question.
I have one question.
Maxim Dvornikov is going to ask a question.
You told us how an active galactic nucleus will look like in different wavelengths. I wonder how it will look like in a neutrino telescope.
Yeah, that's a great question. So for one thing, it would almost certainly have to be a blazar type system where the jet is pointing directly at us. And so, yeah, potentially, because there is a theorized to be an astrophysical neutrino background, right, on top of the cosmological neutrino background, which would be due to blazar systems pointing at us. However, there's been no individual detections.
All right, thank you.
Thanks.
More questions? I have a very, very short question myself. How large is the sample and how big are the samples that you are considering or going to consider in the foreseeable future?
Yep. So the current kind of state of the art, there's about 5,000 objects when you combine radio and optical. There's about 30,000 objects when you combine infrared and optical. Going into the gamma rays, we have about 2,000 blazars from Fermi. And we're currently working on an X-ray sample that has about 4,000 overall. These numbers will increase dramatically in the LSST era. They're actually limited by the optical observations because the optical observations are what can determine that an object is a quasar or a blazar.
Okay. So thank you so much again for the talk. Let me invite Professor Vyacheslav Dokuchayev of the INR of the Russian Academy of Sciences, and his talk will be on the visualization of black holes images. So you're welcome to share the screen and present your slides.
Okay, you see my presentation?
Yes.
So I may start. Thank you for this possibility to take participation in this famous conference, and I will start. So on my title slide, you see the famous image produced by the Event Horizon collaboration very recently in last 2 years. in which you see at first time the real image of the black hole in the galaxy M87. And this is a very great discovery in the 21st century, because at this picture you see the image of the black hole with the resolution of the scale of the event horizon. This black region is of the order of the gravitational radius of these black holes. At first, you see that there are no surface on of these black holes, and the aim of my report is to present you some understanding what's the physical reason and physical explanation on this enigmatic black region on this image of the black hole. Okay, in flat space time, when you, I'm sorry, and first at flat space time, the closer the light source to the object, the bigger the shadow of the image of this source on the screen. This is the light source, this is some pencils, and this is far distance walls with the shadows of these pencils. In curved space-time, the bending of light might be taken into account, the so-called the gravitational lensing. In my report, I will use the Kerr metric in the framework of the general relativity, and I will describe and will show you a lot of illustrations for real geodesic trajectories of photon in Kerr black holes by using the famous Brandon Carter equations of motions. This is results of these equations when we see that there are some potentials. There is so-called polar potential for polar angle theta. This is because in non-spherical coordinates of Kerr and Kerr-Newman metrics, there are dependence of gravitational field not only on the radius and also on the polar angle. And there are so-called integral representations of geodesics for particles in this gravitational field. And this is some special integrals of the so-called second kind. And this is the integrals along the directory of the particle trajectory in the gravitational field of the black holes, starting from some starting point and finishing in some very distant radius where we see the viewing the image of the black hole on the celestial sphere. So throughout all my report, I will use the calculations on of the real photon trajectories in these Kerr black holes by using the famous Brandon Carter equations. So the shapes of black holes images, which are in situ invisible, they depend on the distribution of emitting matter around black hole. It is very suitable to use the terms from the classical photography. And so I will discuss the two very distinctive astrophysical cases. The first case is when the luminous stationary background is placed behind the black hole. In this case, the classical black hole shadow is viewed, which is a captured photon cross-section in the black hole gravitational field. And the second, very important, most much a little bit understandable case is when the luminous accretion inflow there is near the black hole event horizon. In this case, it would be viewed the lancet image of the event horizon globe. And in the what forthcoming, I will discuss and will try to explain you what is the physical origin and the physical explanation of these different representations of black hole images. Okay, let us start with the astrophysical case one. When there is some very distant luminous background, and there is some photographic object, this is black hole, and there is some distant observer, a photographic camera or telescope, which sees the projection of this image on the sky sphere. And in this case, the shadow of the black hole is the classical photon capture cross-section. This is the case of Schwarzschild black hole. And the radius of this sphere is 3 times square root of 3 is approximately 0.2. It's very well known. And the photon trajectory is multicolored. Here, trajectory. It is really obtained by numerical calculations from using the Carter equations of motion. In the case of the very fast rotating black hole, the situation is very similar, but a little bit complicated because the trajectory of photons depends not only on the radius, but also on the polar angle. You see here some photons which start from here, from the far distant background, coming on the projection of black hole horizon rotation axis. And it is what interesting that in this case, the parameters of the black hole trajectories of photons are calculated analytically. And here, lambda and q are something like the horizontal and vertical impact parameters in this gravitational field. And they may be calculated quite analytically. Okay, this is an example of illustration. Let us suppose that there is some very compact star on the equatorial circular orbit with radius 20 around the supermassive black hole in our Milky Way galaxy. Here is the images of these small black holes in discrete times along the circular orbiting around these black holes. You see here the classical image of black hole shadow, and also are shown the so-called light echoes, which is the multiple images of a black hole illuminated by this star, because around the black holes may be the infinite number of images due to different number of winding of photons around black hole. In this picture, you see the 3D photon trajectories. There is the prime images. This is the circular orbit of rotating small star around black hole. This is the prime images. This is direction of the far distant observable. And there is very interesting first light echoes which intersect the black hole equatorial plane one times and going initially to the black holes and then back to the black hole to the distant observer. Here's the so-called the second light echoes which intersect the equatorial plane of black hole two times, going finally to the distant observer. Again, I will stress you that this is magenta trajectory is calculated numerically by using the Carter equations of motions. And now I will go to the most important and less understandable, the so-called astrophysical case 2. The best model for understanding of this case in the so-called the Blenser-Znayak process, in which there are a current intersecting the black hole. This is the red arrows, and this current is hitting the thin accretion disk up to the event horizon of the telescope. This is the picture from the supercomputer simulation in the general relativity magnetic hydrodynamics approximation. This is example of such calculations. Here you see the hotspot in general relativity magnetic hydrodynamical calculations, very old. This is 20.3. And here you see the example for the black hole since our galactic Milky Way galaxy. And what is the interesting, then these black regions quite different from the classical black hole capture cross sections. And the aim of the remaining part of this my report is to explain what is the physical region of this black high region in this image. This is another example of these calculations. There is some line emission around black holes in the galactic equatorial plane, and the observer, distant observable, a little bit higher around with respect to the equatorial plane of the black hole. And again, you see this very unusual black hole region. What is the reason for physical appearance of these regions? Here you see the emission of photons from the equatorial plane of the event horizon globe, which come to the distant observer. And you see here some photons with his impact parameters, which again is related with the horizontal and vertical impact parameters. And the emission of photons from this equatorial plane of the event horizon globe produce the outer curve of this in this picture. Again, if you imagine that there are some photons emitting very near from the event horizon globe, you may calculate where will come to the distant observer. You will find this point. You may find the point from the photons emitting from the southern point of the black holes. You see this point. And finally, you may mapping the old region of the event horizon globe. And what is interesting that in this case, it is the presentation of the transformation of the event horizon three-dimensional map on the two-dimensional map for distant observer. The similar picture may be obtained for the very fast rotating black hole. Okay, imagine that you have some probe illuminating from the very near the north pole of the event horizon globe, and you may calculate the trajectory by using the Carter equation of motion and find the place where it comes to the distant observer. This place. So again, we may map the whole region of the event horizon globe. The other example is the motion of the small star in the equatorial plane of the black hole with zero angular momentum in falling to the black hole. Initially, they fall nearly radially, then due to the frame dragging in the black hole ergosphere, it's going to the right and it's moving around and around and around the black holes, moving on the due to the moving to the black hole event horizon. Here the two-dimensional trajectories of two photons from moving hotspot, starting from just above the event horizon pole. In the case of very fast-moving black hole, Kerr black hole. And besides, this is the direct image. And additionally, it is shown by the red curve, the real photon trajectory, which is the first light echo. Here you see the corresponding 3D trajectories of such photons. This is direct photons coming to the distant observer. And this is the first light event photons from the first light echo going to the distant observer. Here's another example. Here is a direct image. And this is the photon trajectory moving to the distant observer and providing the counterclockwise first light echoes. And now we may provide the presentation of some moving spot in discrete time, starting from the north pole of the black hole, Sagittarius R star, and going along the rotation axis. And it is taken into account the Doppler effect and the redshift of this hot spot. And also are shown the first and the second light echoes. And here is this example corresponding to the black hole in the galaxy M87 with the other inclination of the rotation axis with respect to the distant observer. And now I will show you a short cinema producing by numerical calculation of trajectories of the bright spot in the jet from the supermassive black holes Sagittarius A and M87. At first, Sagittarius A star, which is in our galaxy, here is the presentation of the black hole globe in the absence of the gravity. Here's the shadow and the black hole's event horizon image. And the hotspot is starting from the north pole of the black hole event horizon. And you see here with some delay the appearance of the second and first light echoes. This is repetition of the same motion of the globe. The globe is a sphere, and it is taken into account the deformation of the globe, elliptical deformation only, and the Doppler and gravitational effects. This is the same picture in the discrete time. Now you see the similar simulation in the case of the black hole M87, for which we have the event horizon image. Again, you see the black hole classical shadow, the black hole image of the event horizon, the lancet image of the north sphere of the event horizon, and now you see the motion of the bright spot, which is composed together with the famous image produced by Event Horizon Telescope. And you see at first the motion of the prime image and the appearance of the, with some delay, the light echoes, the first and the one, by taking into account the Doppler and the gravitational redshift. And here is the motion of this bright spot in the along the rotation axis of black holes. And the famous black hole jet in this case, which is observable in different regions, you see in that directions. But in this calculation, I will use this one. This is discrete representation of this spot. And what is important, this is the images obtained in the so-called representation of gravity, which is in my case is the Kerr metric of the general relativity. But in future, you may provide the similar calculations of such motions in other classical or modified gravity theories, and obtain the other representations. And by comparison of these images, we will compare what the theory is really used in our universe. I am very near to the closure of my talk, and this is my conclusion. The conclusion is the following. The unique information for the verification of the gravity in strong field limit will be provided by the detailed observation of black hole images in the nearest future, including the motion of bright spots in jets. You see the details in with my colleagues you see, this is an archive presentation, but many of these archive papers are published in essay papers. And also you may see the animations on YouTube, of which I presented here very shortly. Thank you for your attention.
Thank you so much for this artistic presentation, artistic and astrophysical presentation about the imaging of black holes. Very complex, very interesting. Questions from the audience? I guess everybody can see the information that you have given, and also see the movies that are very fascinating. And I also was wondering myself how to interpret this these beautiful pictures. So I think this is very very exciting. It's also difficult to ask a specific question on the subject. So since I don't see anyone asking a question, I'd like to thank again. Only has a question.
I have a question.
Can you please speak louder and maybe on your camera, please? To interpret this.
Hello, can you hear me?
I think this is very exciting. It's also difficult to ask a specific question on the subject. So I see a raised hand here in the Zoom list by Maxim Dvornikov. Are you talking right now?
Yes, yes.
Okay, please go ahead and talk. If possible, show, turn your camera on so that we can see you.
Okay, I have one question. What is the model of the emission of photons by the accretion disk, which you use to form the image of a black hole? Did you consider that photons are emitted isotropically, or you use some angular distribution?
So my answer is very short. The image of the black hole, in the case of when the accretion disk is very thin, does not depend on the model of the accretion disk emission. It is governed only by the motion of photons in the gravitational field of the black holes. In our case, in my case, I use the Kerr metric, and you may use the other modified gravity. The real distribution of luminosity will produce only the length distribution on the image, but the form of the black hole dark region does not depend on the distribution of the emission in the accretion disk. This is very great and simple result.
Okay, thank you.
Okay, thank you very much again for the talk, and let's move to the next speaker, who is Professor Alexander Dolgov of the Novosibirsk University, who will be discussing anti-stars in the galaxy. Пожалуйста, Alexander Dmitrievich, if you want to show your slides.
I will try. Thank you. So, oops. Do you see me? Yeah.
Yes.
And I'll try to somehow to share screen probably. Command. It's always difficult. I think this is the one. Is it seen?
Yes.
Fantastic. Okay, I always have problem. So the title you already kindly announced. It is Anti-Star in the Galaxy. And oops, how can I move to the next page? Yes. So I will talk about very surprising recent announcement of anti-stars, possible existence of anti-stars in our galaxy, and the theoretical possibility of the explanation. So I start with something like basics of baryogenesis and models of CP violation. Now I turn to possible discovery of those anti-stars, and even briefly mention a paper of anti-star dark matter. So there is some activity on this subject, and then discuss a model of abundant anti-star creation in galaxies. And this model is rather old in a sense. If these observations are confirmed, then it would be confirmation of the model which was suggested many years ago. So starting with conventional baryogenesis, and I will talk later about somewhat unconventional that it was suggested by Sakharov. We need non-conservation of baryonic number, CNCP violation, explicit violation was supposed to be, I will mention later what does it mean, and deviation from thermal equilibrium. And under this condition, we have something like another cosmological constant, namely ratio of baryonic number density with respect to number density of photon background radiation. And in simple version of Sakharov mechanism, no antibaryons can be created. There are some modifications in a sense related to mostly to some kinetic things, some kinetics in which leads to maybe to negative beta. Anyhow, there will be excess of baryons over antibaryons, so that will be either a huge piece of space filled with baryons or antibaryons, usually well separated. Possibility to create antibaryons depends upon the way how charge symmetry is broken, C and CP, and there is explicit, everybody knows that, in particle physics especially, that Lagrangian contains, roughly speaking, complex imaginary part of coupling constants, so interactions of particles and antiparticles, because they are represented by Hermitian conjugated operators, will be different. There is so-called spontaneous CP violation, when there would be a kind of scalar field, complex scalar field, which coupled to other particles, to baryons, and which acquires non-zero vacuum expectation value because of well-known Higgs type potential, and because of that, there will be domains with positive and negative sign, whatever it does it mean, of CP violation. So there will be domains with baryons and antibaryons. This mechanism encounters serious problem because of formation of domain walls, very thin and astronomically, even cosmologically large structures with huge energy density. So there are mechanisms invented to destroy these walls, but still it is a serious shortcoming. There could be mechanism, I will call it dynamical, if simply accidentally during conflation some scalar field fluctuations of quantum fluctuations of certain scalar field rises, so in a sense this field becomes classical, and this field, if it is complex, it is very similar to spontaneous mechanism, would for a while leads to CP, would for a while lead for CP violation. This is later on this field evolves down to zero, but for some time it acts as effective force different for particles and antiparticles, and I would essentially speak about this kind of mechanism, but very well, very much different in some, in many serious aspects. In normal versions 2 and 3, spontaneous and dynamicals, antistars can be formed, but usually they would be very far away from each other, separated either by big distances, and normal galaxy would consist either of matter or of antimatter. The discovery, or so-called discovery, was announced. Let me see, in April or whatever. Well, no, it may be much earlier. Anyhow, there was paper by how we pronounce Duparquet, Thibaldeau, and von Balmus in Physical Review. It's already published in Physical Review. They wanted to put constraint on existence of anti-star fraction not far from the solar system, and found huge amount of huge, I mean 14 objects which could possibly be anti-star candidates. They have gamma ray radiation, which is not can be explained by as a usual gamma radiation produced, well, as gamma radiation produced by the usual stars. So possibly they are very accurate, very cautious. This could be really anti-stars. There may be some other, how to say it, features of observations, but at least the only thing at the moment people use is just gamma rays. There was maybe stimulated by this work, or maybe by stimulated by themselves. There was a paper by Sidhu, I don't know his first name, Rob Scherer and Glenn Starkman. They suggested that maybe antimatter, anti-star, can be macroscopic dark matter, a kind of matcha consisting of antimatter. It's I would say, even more striking and maybe easily falsifiable. But anyway, that they say that such anti-dark matter may be much easier to spot than other forms of macroscopic dark matter. So this idea is, well, observations are, this is a theoretical paper, but observation, of course, is very new. We discussed this problem many years ago together with Joe Silk and later with Masahiro Kawasaki and Nina Kivlishvili. We suggested a different model of formation of primordial black holes. And I will discuss this model later. It was our main driving force of our work, but as a byproduct, and we mentioned it in our paper with Joe Silk, and later on, later paper, which has in the title contained cosmic antimatter, which means that together with primordial black holes, which now it is admitted they may contribute considerable part to cosmological dark matter, though majority say that there are 100% of dark matter made by primordial black holes in the mass interval of around solar mass is excluded, but as Bernard Carr said in his talk that all bounds are model dependent and depends on very, well, it may be avoided. Anyhow, these primordial black holes can be formed by this mechanism, and I repeat, as a byproduct, not only black holes, but also compact stellar-like objects can be formed, which are not black holes. They're not massive enough to form a black hole, but they could be observed in the galaxy like, but it is just some very old compact objects, or can be equally well either stars and anti-stars. There is a certain evidence, very strong evidence of in favor of this scenario, namely the mechanism predicts log normal distribution, mass distribution of primordial black holes, and we analyzed it with Konstantin Pastnov and many people from, well, many of his collaborators, and also, well, that log normal distribution is definitely favored by the distribution of chirp mass, so-called chirp mass of in like events, very well agrees with theoretical log normal mass distribution. And what's even more surprising, we were able to find the value of the so-called central mass in this log normal distribution. Log, this is exponent minus gamma, let's say, log squared of mass over certain m0, and this m0 was of the order of 10 solar masses, and which is also in a very good agreement with the data. So I think it is quite strong support of our model, and maybe idea that there are anti-stars is not completely excluded. Then we, motivated by these old papers, there were our several works, and we tried to find bounds on anti-star in the galaxy, and can conclude that there could be really large fraction of those antimatter star. And the point is, essential point in few words is the following, that the process of annihilation took place only on the surface, thin surface area of anti-stars. Of course, there could be some atmospheric effects, stellar wind and something, but anyway, it is not the same as have huge anti-star cloud where annihilation proceeds in all the volume. If such anti-cloud existed and they were formed in a very early universe, according to the model, they would disappear to present time. But anti-stars in the galaxy could exist, and bounds are rather weak. They Okay, so there was, I would mention, a kind of competing mechanism that anti-stars or antimatter can be created by mirror matter due to transition of neutron into mirror, normal neutron into mirror anti-neutron. In the process of the mirror baryogenesis, they could transform into anti-neutron, and so these anti-neutrons could also mimic. There would be some antimatter content in the usual mirror stars. This, I think, model would encounter several serious, well, I didn't check it precisely, but some more work on this mechanism is necessary. Probably may be excluded or not. I cannot comment on that. The mechanism which I mentioned already, and which leads to this, our mechanism, to log normal mass spectrum, this is the form. And as I said, that we were able to find that m sub 0 is equal to 10 solar masses. We cannot calculate the normalization constant and this coefficient gamma. It is very much model dependent, and we don't know much about physics at very high scale, but at least m sub 0 can be calculated because black holes are formed at QCD phase transition, and m sub 0 is related to mass of horizon at the QCD phase transition, which is very close to 10 solar masses. And the idea is quite simple. We used so-called Affleck-Dine baryogenesis, and which is very nice model in the sense that usually baryogenesis scenarios leads to very small baryon, tiny baryon asymmetry, and theories has to work hard to make it close to the observed number, which is very small, 10 to minus 9 or something like that. And I would not go into detail. Probably how much time I have? Okay, probably. Do you hear me, by the way?
Yes. We hear you.
Okay, very good. Okay, so how much time do I have?
I think just, okay, 10 minutes.
Okay, I'll try to.
10, 12 minutes.
Okay, so we have well-known scenario, used well-known scenario suggested by Affleck-Dine, which was motivated by supersymmetric models at high energy scale, and this mechanism leads to baryon asymmetry of order of unity due to formation of condensate of this scalar of this field chi, which is a scalar field with non-zero baryonic number. And but normally people avoid the problem because condensate is not evolved by very simple means, and so the model leads to normal small baryon asymmetry. What we did, we introduced new interaction. It is general renormalizable interaction of Affleck-Dine scalar baryon chi to inflaton field phi. So what we wrote is cubic and quadratic interaction written in this funny form. And when inflaton field is close to certain value phi 1, which should occur, it is a minor fine-tuning during inflation, then the effective mass of chi becomes negative, and field chi evolve huge vacuum expectation value. Then inflaton field becomes larger than phi 1, effective mass becomes non-zero, and field chi goes down to 0. So it disappeared in this sense. But on the way, it creates big baryon asymmetry. And so as a result, there will be bubbles of formed in the early universe with very large baryonic number. Initially, perturbations are isocurvature and density contrast is almost 0. Of course, there is some non-zero contribution because this part of the field is non-relativistic, but it is minor. And at QCD phase transition, these bubbles with very large baryonic number turned into black holes because density contrast becomes huge, because massless quarks turned into massive protons and neutrons with a mass order of GeV. So we will have universe of a kind of Swiss cheese, where are bubbles full of baryons, and which mostly form black hole. And surprisingly, mass spectrum happened to be very simple. One can calculate it, and the rest would be have normal background with 10 to minus 9 ratio of baryons to photon. And I would probably say that it would, let me say, the point is the following, that the sign of the baryon asymmetry does depend upon rotation in complex sky plane in the face of the complex sky plane, either theta dot field kite rotate clockwise or anti-clockwise. It means that baryons or anti-baryons will be created. We either would have large objects with huge baryonic number or huge anti-baryonic number. If they are black hole, there is not much difference. I don't think that it's possible to distinguish black hole consisting of baryons from that consisting of anti-baryons, but if they didn't have enough mass to make black holes, we would have either stars or anti-stars. In that case, we expect these objects to have very old stars, which would be distributed not in the center of galaxy, but like normal dark matter. And they, well, this is, to my mind, is quite natural mechanism for creation of anti-stars. For example, they would look as very old stars with very large, very old. Indeed, there are data showing that there are some stars with the age of order of 10 billion years or something like that, and even one star was found to be older than the universe. In fact, it is not, of course, older than the universe, but because of different chemistry, they started with baryogenesis with large beta. So large beta means that heavy elements are produced. If baryon ratio to photons is of order of unity, we don't stop on lithium. We go to iron and even very far beyond that. So they have unusual chemistry, and such stars probably are absorbed. At least they look very old than now. I miss this, skip this numerical calculation, which shows phase rotation of field chi, and this is quite simple. So this is conclusion. So outcome of depends of production of anti-stars depending on this ratio beta and back and gamma, which could be, it could be of order of unity, but could be somewhat small depending. It is chaotic process. And one thing that log normal mass spectrum is confirmed by the observation very well. And then we expect some stellar-like objects. And as I said, there could be hydrogen or helium clouds with much and also enriched with metal, which would disappear because annihilation. Clouds disappear because it's volume annihilation. And the last but not the least, that the beta may be negative, leading to creation of compact anti-stars, which would survive annihilation with a homogeneous baryonic background gas in the galaxy. The density of those objects is model dependent, but using it would be rather speculative, but at least we can find some natural estimates. Of course, they cannot make full dark matter, but total dark matter, but some noticeable contribution, it can be done. I cannot say it is 3% of total dark matter or fraction of percent, but at least there could be some anti-stars in the galaxy. So from at least our point of view, it is quite natural that they are observed. Thank you. Let me see. That if true, the observation of anti-star is probably discovery of the century. I would not say of the millennium, and certainly more data are badly needed. Thank you.
So much. Thank you so much for the beautiful talk and for keeping the time. So let's see if there are questions from the audience. I have a little comment or question myself, if I may, which is about you said that would be really a very world-shattering discovery, would be a very important discovery. And I'm from the observational viewpoint, I'm a little bit worried about, annihilations, you need to demonstrate. I would be more excited if, I don't know, anti-iron nuclei would come from space, anti-carbon nuclei, so very complex anti-nuclei could be synthesized only in anti-stars, I would say. What do you think?
There are some observations of anti-helium by alpha magnetic spectrometer, and some anti-helium probably is observed.
But that's not enough. You know better than me. That's not enough to prove.
Yes, but anti-helium, creation of anti-helium in, let's say, proton-proton collision is, antideuterium can be produced, even helium-3 in some noticeable amount, and anti-helium is very small number, but of course we need more anti-helium. It would be really striking if anti-iron is found. It would be natural production of anti-iron is absolutely excluded. It is one of the possible other signatures which I didn't mention and which we discussed. We are now there is work in progress in our group. So
but you think anti-helium is already a good enough?
No, it is not bad. At least nobody knows how to explain anti-helium by secondary production. Okay,
so
thank you.
If there are no other questions, I would like to thank again.
There is a person called Davidson.
Sorry.
I see the hand.
Thank you.
Okay.
So thank you for the very interesting talk. I will need to read the paper. I just have a very naive question, though. I would have thought that if you make the eta equal -1 patches of the universe in Affleck-Dine, I would have thought the size of the patch is fixed during the Affleck-Dine process and not at the QCD phase transition. Why is it the QCD phase transition that sets the size?
Yes. The size of the object is fixed by the duration of inflaton field sits near phi1. That was you remember there was interaction of Affleck-Dine field chi squared by phi minus phi1 squared.
Yes.
And after that, there was no density. There would be antimatter in certain amount, but there was not, how to say, any density perturbations at this stage. And density perturbations appeared after QCD phase transition or during that, because initially quarks are massless, and it doesn't matter that if it is quarks or anti-quarks, and density contrast was, it was normal isochoroichy perturbations, and density contrast was practically zero. But after QCD, all of a sudden, phase transition when quarks became turned into baryons, then there was huge density contrast. And in this case, there was objects like black holes and compact stellar objects. That was a thing. And these bubbles with high baryonic number density, they were occupied minor fraction of mass, or minor fractions of the universe volume, but they have quite considerable mass and even could make whole dark matter sitting in these compact objects. And the key point is that density perturbation becomes. Okay. Are you Sasha Davidson?
Okay.
Yes.
Okay, so we met. Okay, great. So I don't
Thank
see
you
that.
again.
Okay, so I think we should move on to the next speaker now, who is Professor Nausheen Shah at Wayne State University, and she will be discussing WIMPs and missing energy signals and the galactic center excess. So you're welcome to share your screen.
Yeah, and I want to switch off my mic.
Please.
Yes, I can, and I cannot share
You
until the screen.
If,
the previous speaker stopped sharing their screen.
Yeah, right.
Okay.
Okay. Now we can see you.
Sorry.
And okay. Now you're sharing the screen.
Okay, you see my screen, you can hear me,
Yes,
and you see my pointer. Yes.
Go ahead, please.
Okay, so WIMPs and missing energy signals and the galactic center excess. So there's a lot of stuff going on here. But the first part of the story is you have to start with dark matter, right? What really is it? So dark matter is a very interesting story because from the perspective of the fact that we both know a lot and very little about dark matter. Hello, there's a lot of background sound. Okay, thank you. So we both know a lot and very little about dark matter, right? I mean, we know very precisely how much of it we have, but the big question is, well, what is it? So we know lots of things it's not. We don't think that it has any electrical or color charge. We know that it interacts gravitationally, but it could, in principle, have weak interactions. And it needs to be something that, you know, is stable on universe lifetime scales. So we can ask about, you know, is there more than one dark matter species, right? Is there a whole dark matter sector? We could ask about what kind of Higgs interactions there are. But also, we really don't have any candidate in the standard model of particle physics that would actually work. So it has to be something that we do not know. It has to be some sort of beyond the standard model physics that would explain this. So maybe the first place to start is to talk about, well, how would you get the amount of dark matter that is actually observed in the universe? So that brings me to a very popular story, which is of the thermal relic. So what sets the abundance of the dark matter that's observed? So you can imagine that maybe there are some interactions of dark matter with the standard model. And, you know, there's some back and forth annihilations of dark matter with the standard model. And that is what keeps it in thermal equilibrium as the universe is cooling down. Now, the universe, as we all know, is expanding. And so you can think about it that, you know, at some point, two dark matter particles can't find each other to annihilate. And so the density basically freezes out. Now, this clearly depends on what this annihilation cross-section for the dark matter would be. And you can imagine that the bigger the cross-section is, the longer it's going to remain in thermal equilibrium and the lower the observed relic density would be. And that is basically portrayed in this plot over here on the right. So now, that is what brings us to the WIMP miracle. You have this relationship between the annihilation cross-section, the particle physics annihilation cross-section of dark matter, which is then directly related to how much of it you would observe. And it turns out that somehow, automatically, if you put in, you know, sort of naive, weak scale couplings and masses for dark matter, you end up with a cross-section which matches almost perfectly with what is observed. So that seems like a really great story. But what is this galactic center excess that was in the title? And what is its connections to this sort of weakly interacting massive particle, the WIMP? So there seems to be this glow that's coming from the center of our galaxy. So this excess is observed in photons of energy between 1 and 3 GeV. And this has been observed by Fermi almost 10 years ago, I think. And on the left here is, for example, a picture of what this looks like. This glow that's coming from the center here. And now if you take the same thing and you remove all of the known sources, what we think is there, then you are left with what's in the right panel. So you still see this glow that's coming from the center of the galaxy. So, well, what could it be? So you do have the caveat that there are large astrophysical uncertainties here, and maybe it is, I said that this was the glow coming after the known sources are removed from this picture, but there may well be a population of, for example, millisecond pulsars or something that we don't actually expect to be there. So standard astrophysical objects, a population of these which may exist in the galactic center, which we don't expect to be there, but maybe that's what it is, and that's what's giving the glow. But the particle physics interpretation of this is intriguing. And the idea would be that, well, what kind of particle physics would explain this? And are there any kind of concrete predictions that we could make that we could then go and test in complementary experiments? So the idea is that, well, the galactic center is a pretty dense region, right? So you can imagine that, if there's dark matter around, the center of the galaxy is a place where you would expect there to be a larger density of dark matter than you would observe everywhere else. And so if there's a larger density at the center of galaxy of these dark matter particles, then they could still be annihilating with each other. And they could be producing a flux of gamma photons, which is what we are at the end observing. So this actually has a very distinctive bump-like spectrum. So what I'm showing here is the flux versus the energy of these photons. And the crosses here are basically the observed data. And this blue line over here is some model which has dark matter around 30 GeV, and it has this nominal cross section of 3 × 10⁻26. So you see that it looks like a really good match, right? I mean, it looks intriguing, as I said. So if you had dark matter particles of order of, let's say, 50 GeV or so, and these are annihilating at the center of the galaxy, this in fact would produce precisely the kind of signal that is observed. All right, so now how is this related to the relic density? So the galactic center excess is expected or assumed to also originate from the annihilation of dark matter. However, the difference with the process with what sets the relic density is the temperature at which it happens. So the relic density cross-section is given by this cross-section at some temperature T freeze out. However, the galactic center excess that we observe right now is basically at 0 temperature. So this here basically is what the cross-section would look like, and this is the nominal value that we need it to be, which also matches with what the relic density, consistent relic density would demand. So what you need is that this cross-section must be dominantly S wave, okay, which means that you don't want it to be temperature dependent. You want it to approximately be the same at both the freeze out temperature and 0 temperature. So you can think about what kind of mediators you could have for this annihilation, which would actually give that. And it turns out that if you had some CP odd scalars, those would be good mediators. You could also have CP even scalars or your standard model Z gauge boson with some small amount of CP violation. So that would work. Okay, so that sounds like it's a pretty nice looking story. Maybe we have gravitational evidence for dark matter, and maybe now we're starting to actually see hints of actual dark matter annihilation coming from these astrophysical observations. So then what's the problem? Well, the thing is, this crossing diagram, this crossing symmetry diagram that I have here. So the X's here would be, whatever, some dark matter particles which have some blob interaction and they go into some standard model. So going in the right direction, of course, you have the annihilation, and that is the principal way that you basically break dark matter, right? This is what sets the relic density, the process which sets the relic density for dark matter, and also would give you this galactic center excess, as I just showed you. But the other directions in this diagram here would also be related. So, for example, going upwards in time, what you have is a dark matter particle and scattering off of the nuclei and going off, but then you could have a nuclear recoil. And so that's what basically we have a whole bunch of what are called direct detection scattering experiments, which are looking for these nuclear recoils. And then they set limits on what kind of interaction this dark matter would have with nuclei. Then the other direction is going towards the right, which is that, okay, again, if this dark matter interacts some way with the standard model, then maybe we can actually produce it and when we do collider experiments. So this is, again, a very nice picture, and I think this is the reason this correlation expected between these different directions is why people got very excited about the WIMP paradigm a couple decades ago or so. So, but that is also the reason why there is some tension now with this whole WIMP paradigm. And it's basically to do with the direct detection, and in particular, the spin-independent direct detection cross-section. So you would expect, again, so the top over here shows you maybe, something that could be happening. So Chi is, exchanging something with the standard model and going off. And over here at the bottom is the limits that have been set recently. So these limits are getting more and more stringent. And then the question is, well, if you have this crossing symmetry, how is it possible to still have a large enough cross section such that you get the right relic density and or this galactic center excess that I'm talking about? Well, the thing to remember over here is that this crossing symmetry picture that I just showed you is a very EFT, effective field theory picture that is assuming that the blobs, the stuff that is in the blobs, can actually be integrated out. However, if you actually have additional degrees of freedom which are propagating at these energy scales, then that is really not the correct thing to do. So for example, you very well might have that you have, for example, resonances happening for the cross section that give you the right relic density, but or also you may have multiple mediators that could be, mediating the spin-independent direct detection cross-section, which could have, in principle, destructive interference, which would suppress the spin-independent direct detection cross-section while you are still able to get the right relic density and the galactic center excess. So, I mean, the picture that I've so far drawn out for you basically is saying that maybe it's not the right thing to be thinking that there is only a particle which describes the dark matter, but maybe there is a whole set of weakly interacting additional particles which could make this whole story altogether work. So with that, let's go to that means that you have to then look at this picture in specific models to look at the kind of things that could be going on. So, and in addition, then you have the LHC, which was the last direction that was there in the crossing symmetry. So on the top, I have, how the kind of processes you would have for the galactic center excess and the relic density. But again, if you have additional states, weakly interacting additional states, maybe you could produce, these additional states which actually interact, we have significant interaction with the standard model. You could produce those at the LHC, and then those things can then decay down to known standard model particles, for example, either the W or the Z or the Higgs, and a dark matter candidate. And this is what would show up in our collider experiments as basically missing energy signals. So this is the kind of thing that we'd want to look like associated with this whole dark matter story that we have. Okay, so with that, let's go to a specific model. So for example, I'm going to be discussing supersymmetry, which has a whole bunch of particles which could work for WIMPs. So at the very minimum, what you need is that you need to have every standard model particle has a SUSY superpartner, okay? And in particular, every fermionic particle has a scalar, and every boson has a fermion partner. So for example, and the naming convention is that you add either an S to the scalars or the enos for the fermion. So the top quark, for example, has a stop as its partner, and the Higgs has partners which are called Higgsinos. Now, you don't have any new couplings, but we know that SUSY has to be, in fact, broken. And so the masses of these superpartners can be some arbitrary masses, okay? And we parameterize them by these soft masses for all of these different particles. And you should really think about them as a way of parameterizing our ignorance about where this SUSY breaking came from and what it is, okay? So then, is that, sorry, hello? Sorry. So then looking at, the weak sector of these kind of SUSY models, we have the charginos, neutralinos, and the sleptons. So these are, all the different superpartners for the standard model gauge bosons, the Higgses, and in particular in SUSY, you require an additional Higgs doublet, and the leptons. So so when you get the SUSY partners of these in particular, you'd get a bunch of Majorana fermions, which are neutral, and the lightest of these guys can be stable due to R parity. So you get, a bunch of candidates that could be the WIMP. Now, the superpartners are, so the left-hand column has the standard model stuff, and then the right hand has the SUSY stuff. So, for example, the hypercharged gauge boson has a Bino superpartner, which is parameterized by this mass M1 and has the gauge couplings G1. And this guy will actually tend to be mostly what the dark matter, what a good dark matter candidate ends up being. You also have Winos, which are parameterized by M2 and then G2. You have both neutral and charged states, which you get from here. You have the Higgsinos, they have a mass parameter mu. Now, of course, these are then given by, the couplings are given by Yukawas, et cetera, again, related to what the standard model couplings are. These will also have both neutral and charged. And then the leptons will also have the sleptons that come with them. Now, generically, these neutral states, and of course, and also the charged states, they will, everything which has the same corner number, they will actually mix to give you finally the mass eigenstates that you actually observe. So for example, your lightest neutralino may well be mostly the Bino guy, but will have some small composition of these other Wino and Higgsinos in here. Okay, so that's the basic particle content. So how do you get the Rayleigh density to work here? Well, as I said, light Binos would make an excellent dark matter candidate. And you can have these resonances via either the Higgs or the Z or the additional Higgses. You can also have that there is this type of T-channel exchange of, for example, light staus, which are the superpartners of the taus. And this can happen pretty naturally when you have large tangent beta in the model. So just to give an example of this, what would look like for getting the right Rayleigh density and galactic center excess, this Wino mass in this picture for this part of the story is actually irrelevant. But here I show you in the mu versus M chi plane. So this is your dark matter mass, and this mu over here was the Higgsino mass, but it also parameterizes. If you look at the couplings with the Higgs and the Z, it is the quantity which goes into those things. So you see these contours here, which is where you would get basically the right Rayleigh density from this sort of S-channel resonance in there. But now the additional thing that you also get is that demanding that you get the right Rayleigh density also fixes this value of the mu parameter and this coupling to the Z, which is what drives the spin-dependent direct detection cross-section. And so, in fact, this type of direct detection constraints are pretty strong on this value, on this mu of how small this mu can be. And in fact, mu, this gray band that's shaded over here is what is actually excluded right now. So you really need mu the absolute value of mu to be, basically 300 GeV or above. But so this points to a picture where mu is, between 3 to 600 GeV, right? And you have light dark matter, order of 50 GeV or so, and that would explain the whole story. But there was also the question of the direct detection cross-section. And I mentioned that, if you have multiple mediators, then you can in fact have this cancellation, destructive interference between the different contributions. So for example, here I have a contribution from your standard model like Higgs, here from a heavy additional CP even guy, and also some additional sporks. Now, if you look at this form, what happens is that you get actually this cancellation for this cross-section once you have certain relationships fulfilled. In fact, it really actually only depends on the sign of mu times m chi, right? And it's not a very fine-tuned funnel for this cancellation, for this spin-independent direct detection to be suppressed. So for example, for some, benchmark numbers here for the Higgs resonance, I show you this mu versus this heavy Higgs mass, these contours of what you would see for the direct detection cross-section. So this contour in the middle here would correspond for exact cancellation, but actually the current limits are barely on this plot, which are these black things over here. So you have this really wide funnel, which as long as you have that this sign of mu is negative, that within this funnel, the spin-independent direct detection cross-section is quite suppressed. So, you can easily do that just by having this sort of funny blind spots and the sign correlations. Now, again, I repeat that the spin-dependent direct detection, however, will not have this kind of cancellations, and so may well be the way that you actually end up seeing this. But now there's actually maybe something a little bit interesting with this spin-independent direct detection in some recent results. So if you look at what the cross-section looks like right now, so if you look at order of this region over here, say order of 50-100 GeV, you see that the observed line is maybe order of there may be a slight upward fluctuation from what.
Let me remind you to go to the conclusions in a couple of minutes. Thank you.
Yeah. So this is so there's a a little bit, maybe a fluctuation upwards, and so this could very well be what is consistent with this galactic center excess. And there's also this flux of antiprotons that AMS sees, which would also fit in with this very nice picture. But now the question is, what about the LHC? So doesn't that really rule out SUSY below the TeV scale? Well, let me remind you that the LHC is really a hadronic machine. And so the constraints are really on the strongly interacting sector. But the weak sector, on the other hand, is really not very strongly constrained. So the sleptons, for example, the staus that I showed you, are very weakly constrained beyond LEP limits. And the WINOs, as the NLSPs, are actually the most strongly constrained. But in general, the bottom line is that a SUSY scenario with large cascade decays, which has a bunch of light electroweak NOs, is in fact the most natural one from the theoretical perspective, and would fit with this whole picture of galactic center excess, direct detection, etc., and the least constrained so far. So just to show you what the kind of limits are right now is, so they're, as I said, they're quite weak. And in particular, this degeneracy region for, this is the STAU versus the neutralino mass. This is quite, weakly constrained. And this picture holds also for the WINO LSP. There's all sorts of other things that go into what the observed limits are, which is, when you have these additional states around, that can change what the branching ratios are, and so change the limits that you see from there. Heavy squarks, if they're around, they would also could in fact suppress the limits that are presented by at least a factor of a few. And again, the type of NLSP really makes a difference. So you have this Higgsino and WINO, and that could have, the Higgsino could have a much reduced cross-section at the LHC. So where do we stand with that? Well, we have the galactic center excess and the relic density and the spin-independent direct detection cross-section, and you can make all of this work in a bunch of weakly interacting stuff. The wink paradigm, therefore, is pretty alive and kicking. As far as the collider stuff is concerned, we basically need more data, right? So this is basically barely constrained at the LHC for these type of weakly interacting particles. So this is, in fact, where the high luminosity, the additional data that we'll be getting at the LHC may be most relevant, because this is where your statistics rather than energy limited. But at the end of the day, still Higgs-Xenos will remain weakly constrained. So, but you know, if you have future, for example, E+ E- machines, so machines which are more focused on the weak sector, you can directly probe this sort of weak physics if it is kinematically accessible, if you have enough energy. So with that, I end saying that, look, we have very strong gravitational evidence for the existence of dark matter, and maybe there's some now tantalizing hints of indirect and maybe direct detection for this type of WIMP dark matter. And an interesting question is to ask, well, what would we see at the colliders, and how would we see it? And one thing that I want to highlight is that the absence of evidence does not mean the evidence of absence. So we have to think about what we are actually observing and looking at and seeing. And so I will stop here. So thank you.
Thank you for this interesting talk on this very modern subject, and on which there's a lot of research. So are there questions? There's a question that I see here from Alexander Zakharov.
Okay, thank you very much. If you have dark matter distribution concentration near the galactic center, you have to have some dark matter, let us say, bulk distribution. So did you evaluate mass inside, let us say, orbits of bright stars like S2 and others? Because if you have a few % of black hole mass inside this orbit, you could spoil these perfect elliptical orbits for these stars. Thank you.
Sorry, say again. So what I do know is that
you have to have for explanation of let us say gamma excess with dark matter particles, you have to have some particles around the galactic center. So in this case, you have some distribution, okay, some model for distribution. In this
it
case,
looks approximately very spherical.
Spherical, yes. Yeah. And also you have some radial dependence. I mean, some model probably for radial dependence somehow. So usually people did it. But
yeah, I mean, they do all kinds of simulations. Yes,
yes, but it's no matter. It's you have to have some, let us say, concentration of matter. If you have dark matter distribution inside of orbits of bright stars like S2, in this case, you cannot have enough, let us say, dark matter probably for this, let us say, explanation of excess, because otherwise you could spoil orbits. Potential for S2 star has to be very close to Newtonian one. But if you have bulk distribution of matter, you could spoil these orbits. Do you understand?
I'm not completely sure I understand.
Because if you have ball, for instance, not let us say point-like source.
It's a pretty big distribution. So I think the galactic center excess actually extends out to about 10 degrees. It's not completely in the galactic plane. And that's one of the reasons why they think that
something
it may
like
be
radial distribution. It's not a big deal.
No,
but
this is the plane, right? This is the plane of the galactic center, like the galactic plane, and there is a bulge, not radially here.
Yes, but
bulge, this way. Yes, and
yes,
that's
exactly.
and it extends a lot more than where the regular matter is supposed to.
Yes, exactly.
Extend.
But by the way, if you have dark matter distribution, you have dark matter distribution until almost the center of our galaxy. And it's usual assumption. In this case, you have some dark matter inside these bright orbits, but you cannot put too much mass inside these orbits, because otherwise these orbits will be spoiled. Do you understand?
Sure.
Yes, of course.
Excuse me, please. I really hate to interrupt this
Oh, okay,
discussion.
sorry.
Let me suggest that you continue the discussion offline so that we can keep our only 15 minutes delay with respect to the schedule. So I apologize to everyone.
Apologize. Thank you very much.
And,
Thank you.
I thank you again, the speaker. And I would like to then invite Professor Jin Kim of the Kyunghee University to give the last talk of the session about black hole information. You are more than welcome to share the screen. I think you have your microphone off.
Show my screen.
Okay, yeah, we can see you. And then could you please share your screen?
Yes. Your screen.
You should be able to share the screen, I think.
Can you see?
Not yet. I don't see it yet.
I pushed your screen.
I think it's action needed from your part because I see I could share the screen. So it means that nobody else is using the screen. So it's really you that should capture the screen.
I pushed the share screen button, but why
Is there anyone by chance sharing the screen? I don't think so. I think the screen is free, but just in case, I'm asking anyone to check if by chance somebody is doing something
Can you see
wrong or
wrong?
Sorry?
You cannot see the screen.
You can,
you should press the green button and then choose what to share.
Yes.
Oh, yes, we see.
Yes. We see it now.
Okay. Okay. You can see now.
Yes.
I thank the organizing committee for giving me a chance to talk at this prominent conference. So it is actually here in the evening, and good afternoon, everybody. This talk is a simple point on what you all already know. I just remind you the known mathematical lemma can be related to a black hole. The example is for a charged black hole, but it can be applied to massive black holes also. Well, we know that black hole entropy was pointed out by Bekenstein comparing black hole and thermodynamics. They have similarities. A large black hole increases its mass by absorbing nearby masses. In comparison, thermodynamic system loses more information as time goes on. Another comparison is combining two same mass black holes, the surface area increases. In thermodynamics, we know that entropy also increases. So for Schwarzschild's black hole with a radius 2 gm. The surface area is actually 16 pi square g square m. So this expressing this area A in terms of a dimensionless surface area, we obtain roughly some m, where Bekenstein used irreducible mass, m irreducible mass square over Planck mass. So this is a kind of number, dimensionless number, which can be counted as the digitized information of black hole. So I worked on action, so I talk about ultralight action limit, ULA. First, its mass range, it can be 10 to the minus 33 electron volt to 10 to the minus 3 eV. But recently, Rogers and Pires commented that the mass, some regions can be excluded. As you know, Marsh et al. Excluded some regions studying structure formation, and Rogers et al. Excluded some region, preferred some regions. So this pink region is roughly the allowed area. 10 to the minus 22 eV is used for some by some people for explaining some problems on the galactic scale, large scales. Now we calculate the information. If our visible universe, whole visible universe is a black hole, then the information calculated in this way is about 10 to the 122, roughly this one. This is a famous number in cosmology, but somehow it happens to be about this number. The number of information number is about 10 to 122. Recently, this preprint commented about what if primordial black holes fills the space beyond our horizon, our horizon, and the possibility that the whole universe is black hole, and it excludes this possibility. On the other hand, if ULA provides information, if ULA mass is very small, as mentioned just before, about 10 to the minus 32 electron volt, then it can provide lots of information. In fact, if ULA mass is of order of 10 to the minus 32 eV, then it can provide the needed information. Irrespective of this famous, interesting number, can there be a method to see the inside of the black hole? This is the question I have today. I cannot prove this in physical terms, but I look for a logical possibility. Is there a logic? Is there some hole, some puncture through which we can look inside? The information I mentioned, I already mentioned this one. The digitized information of mass is about this form. If I use properly the dimensionless number, 10 to the minus 5 gram is some boundary. If black hole mass is less than 10 to the minus 5 gram, the information carried by particles inside the black hole is more than the mass information. If black hole mass is greater than 10 to the minus 5 gram, practically particle information is irrelevant compared to the information of the mass. So in most black hole physics, we prefer to use mass as the providing the needed information. Suppose we have a black hole and we have a puncture like diameter L. Somehow we can look at the inside of the black hole, not by the particles we know. So the information I want to get is not by particles, not by standard particles, waves, or etc. Just it is classical concept. No particles are coming out or coming in. If we can look at inside of the black hole through this puncture, if the number of this puncture is even, then some even number of punctures can be connected if classical concept, I said classical concept. So flux lines coming out through this puncture, then it can go there again through another black hole. So if there are even number of punctures, then all these black holes doesn't have any puncture left to be looked at. However, if the punctures, the number of punctures are odd, then there must remain one puncture through which flux lines are classical concept. So flux lines can come out, and if we consider some boundary near black hole horizon, then these flux lines must end on the surface of the black hole. There is no way, there is no other place for these flux lines to stop. So, as I said, this flux lines doesn't have any size. So in a sense, this is the topological concept. We do not count any quanta or masses, etc., the particles. So in this figure, I mentioned this figure just before. If we follow the flux lines backward, then by the famous Gauss theorem, we know how many charges are inside the black hole. It can be applied to U1 charges or non-abelian charges, whatever charges it is. Following through these flux lines, we know what information is inside the black hole. There's in mathematics, there's a lemma, that Sperner's lemma, that anyway, before stating that lemma, if we cover the surface of a sphere, we can, with some rubber band, we can cover the surface of a sphere. It can, if it is a triangle, it can, because triangle is topologically the same as any band of clothes, so triangle can cover the surface of a sphere. So triangle rubber, we can consider triangle rubber band. So in Let's gauge theory, some people calculate using Let's program the integrate about this boundary of some two-dimensional area, whatever disk or square or triangle, then the result is interpreted as a placket. Placket is actually f square integrated over the inside the bounded surface. We are not considering this placket, just we are considering some kind of this puncture and what kind of quantity can come out or go in through this puncture. So some quantity, we can consider some quantity can go through and out. These are not particles. For example, F mu nu A. F mu nu A, if black hole has some charge, then depending on the charge, some flux can come out through this puncture. A is here, here A is counting the adjoint representations, for example. if we consider the puncture is a triangle P and PQR, I use this PQR because I want to consider SU3 because we are very familiar. Particle physicists are very familiar with SU3 gauge theory. If we consider this one, basically we can consider U subgroup of it, U1 or SU2. So I just consider SU3. This is a good example. Depending on PQR, the quantity we consider is F mu nu A. This A is the counting the adjoint representation. Sperringer's lemma is actually there is an odd number of white triangles. I explain what is white triangle. And I follow the proof given in the homepage at Harvard University. This shows the proof, and I explain this one. I consider triangle because it can cover the surface of the sphere. This is a triangle. For example, here AB. I wrote here AB, but A is 1 and B is 2. And the top point is 3. 1, 2, 3 is, I count 3 colors of SU3, for example. Then Sperringer's lemma is that we can divide this triangle by many small triangles as shown in this figure. Then the lemma says there is an odd number of small triangles. That is the lemma. So the point is, I show this one and I relate the first figure, the puncture with the interpreting puncture. If there is an odd number of triangles, then even numbers can be removed by connecting 2 punctures, and there remain only 1 puncture. So because Sperringer's lemma is correct, in the black hole, there must be there must remain 1 puncture whose point are 1, 2, 3. 1, 2, 3. End points are 1, 2, 3. In SU3, end point 1, 2, 3 means the flux we consider inside the triangle surface is SU3 invariant. This is SU3 invariant. All other triangles, as you noted this from these numbers, there is no triangle with 1, 2, 3. So the proof goes in this way. The bottom line at the end AB, 1 is interpreted as A, 2 is interpreted B. And in the bottom line, there are small lines, small segments, 1, 2, 2, 2, 2, 1, 1, 1, 1, 2. Small segments are interpreted as a small AB. So for small AB, in the bottom line, if for every external AB, bottom line, AB square 1. For every internal line, you count triangles, then one time it goes up, one time it goes down. So for every internal AB, square 2. For all others, square 0. Then actually AB is present only at the bottom segment because 1 to 3 is on top and the side are only 1 and 3, or the other side 2 and 3. 1, 2 is only on the bottom segment. So AB is counted only from bottom segment, and from this example, actually there are 3 1, 2 lines. This is odd. There are 3 1, 2 lines. This is bottom segment. For triangles, if there is 1 to 3, then square 1 for every 1 to 3. For AAB and ABB, square 2. All others 0. Then actually the total square of triangles, ABC triangle for odd or even, is the same as the number of AB at the bottom line. Therefore, total number of ABC triangle is odd, because as I showed you before in the triangle, ABC triangle line is odd. So for that figure, I counted here again. So there remain only, I wrote different numbers here in this case, so that there remains only one triangle, one white triangle. And for color SU3, I inserted every colors, red color 1, blue color 2, green color 3, and some combination of colors, yellow or some green or white. White is when 1, 2, 3 are combined, then it is white. So external point 1, 2, 3, it is white. It is SU3 invariant flux lines can coming out through white. As you see in this figure, all other triangles are colored. So if I go through any other triangle, it breaks gauge invariance. So there is one triangle, there is one puncture through which gauge invariant flux lines can go out. So through this place we can see inside the charges. And this is, of course, I showed for these global charges, but you can move slightly 1, 2, 3 points, then it is a local point. Therefore, it applies to actually gauge series. So SU3 gauge charge can be counted through flux lines through this white. There's there remains one such a puncture to see SU3 gauge charges. So this, I tried to relate this Spearson lemma to relate the information on the surface of the black hole to the information inside. It is identical. I showed that it is identical. For this, I need inevitable one puncture. There's one puncture, isn't it? This is a logical possibility. If the puncture number is even, logically it is not possible. All the punctures can be closed. Therefore, because of this odd number of puncture means there must remain one inevitable puncture through which black hole information can be looked at. And I showed that Spearson lemma guarantees it, and I showed with colors of SU3 color. Thanks for your attention in this last talk.
Thank you so much for your talk about this very interesting subject. Are there questions from the audience? It is a rather late time, but we had kept the delay within 15 minutes. So I think we made a good job. I see Alexander here. Maybe we should like to thank all the speakers then of this session and let the word to Alexander.
Okay, well, thank you very much. Really, we are very thankful to all the speakers of this morning section and also to the convener. Indeed, we discussed a variety of different problems related to black hole, to galactic center physics, and some consequences that can be found here and there. And a lot of very exciting and intriguing issues and problems were touched. Yeah, thank you. And now we have, as we call it, a lunch break, but really this is, I think this is not quite enough time for this. But nevertheless, we start at what time, colleagues? I am asking. So we shall start exactly as it is indicated in the program, 14:40. Three parallel sessions will start simultaneously. Well, and I hope that everybody who just present here will join at least one of these sessions.
Thank you very much.
Yeah, thank you. See you very soon. Bye.
Thank you.
Alexander,
Bye.
Yeah.
Alexander, is Zakharov is speaking.
Yeah, please. Yeah.
You see, there is some mistake in the program of a session because first speaker, please take a look, because first speaker is 1 hour 20 minutes in according to your schedule, and other people did not inform about their real time. Do you understand?
Sorry, and where is Konstantin?
I think we could speak. You see, first speaker, you allocated 1 hour 20 minutes for first speaker, Kwon, but other people do not inform that their speaker, if it will be 20 minutes, other people do not know the time of their talk. Do you understand?
So you mean that if you just add?
No, it's up to you. It's
no. And what is the problem? I just look on the present program on the website.
Yes.
It's на site. So well, the problem, the point is that we have not changed time in the program on the website.
Support and others. Yes.
Yeah.
And this speaker do not inform about their time. If we'll shift, I don't know how to proceed in this case.
The first speaker should start 14:40. Yeah.
Okay, but second speaker did not inform.
Well, excuse me, Konstantin, would you please? There is a problem with timing on
schedule.
In the schedule, there's a problem. So the first speaker knows that we start 14:40, but the second speaker.
Yes, I sent for the next. I have recent.
So the point is that all speakers have been personally informed, about the change.
There was a mistake.
No, it is true that all the speakers were informed about the real time they should start. Personally, we shall emails. Yeah, we have already sent mails to all the session speakers.
I'm the first speaker.
With the real time when we shall start.
Okay,
Thank you.
20 minutes for all.
20 minutes, it's up to you, but we suppose that you will speak for 20 minutes. Yeah.
No, General.
Okay. Well, thank you. Well, okay. Thank you very much. Yeah.
Okay.
Okay.
I will start at 2:40.
Yeah, 2:40. CERN time. Yeah. CERN,
Okay.
Thank you very much. Thank you. Bye.
Konstantin, do you hear me? Konstantin.
Yes.
It's now it's again schedule is not quite correct because you allocated 10 minutes for Graz. It has to be 20.
Ah.
Okay, thank you.
Okay.
Thank you very much. We will correct.
Okay,
Thank you.
Because otherwise Graz will be okay. Good.
Yeah, thank you.
Professor Kwon, are you here?
Hi, I'm here.
Okay,
I am
fine,
not
fine.
a professor, though.
Let us try to share your screen. Just please, Konstantin, please unshare. Stop sharing. Because 1 minute until the beginning.
Okay.
Alexander,
Yeah.
organizing committee has to stop sharing the screen because it's now time to stop.
У кого экран? Okay, yeah, thank you. Now it's okay, yeah?
Okay, fine.
Thank you.
Okay, first speaker is Professor Kwon. 17 minutes for talk and 3 minutes for questions and discussion.
Okay.
Okay.
Can people see my screen?
Yes, fine. We saw
Okay.
it.
Sounds good. Okay. Should I begin or?
Yes. It's now it's time to start.
Okay.
Go ahead.
Lovely. All right. Thanks for having me here. Today I'm going to tell you about this experiment we did at Fermilab called the holometer. I think a lot of you might not be familiar with it. So our story begins with the holographic principle, the infamous one. We're all familiar with the black hole entropy bound that we have here. But amidst all these projections to the boundary that we typically do in, like, say, ADS-CFT, I think we've forgotten about some of its fundamental implications. In particular, we often don't really think about the fact that the information density decreases linearly with scale. And it's been well known since about 1998, since the Cohen-Kaplan-Nelson paper down here, that effective field theory has a serious infrared problem. If you just add up all the possible modes of a quantum field theory, just having all the virtual modes in a vacuum, 1/3 the size of the Baikal Sea will give you a black hole. And that implies that if you have a definite background and a background spacetime, and that background spacetime is at Planck resolution with the typical extensive scaling that comes with it, then that bulk simply just has too many degrees of freedom. And people like Tom Banks, for example, have been trying to get the community to address this issue for decades, but it just hasn't been receiving a lot of attention. This is closely related to another problem that I think is about a boundary condition, namely the cosmological constant. Lemaitre pointed out that this is likely the energy of vacuum, and that was later thoroughly worked out by the great Zeldovich. But the main point that I want to make here is that this cosmological constant should be considered actually an infrared boundary condition for the total number of degrees of freedom in any fundamental theory of quantum gravity, and not a local contribution to the energy density. So that leads us to this claim that even the low energy ground state limit of quantum gravity cannot be described by perturbative graviton fields on a background metric. The scaling of information just needs non-local correlations of space-time at large separations. It may be that conventional effective field theory just cannot accommodate the foundational principles that we need. For example, in quantum mechanics, you need a rejection of local realism, and in general relativity, you need background independence, right? So spooky correlations in the classical quantum mechanical, quantum entanglement sense, and not the quantum field theoretic sense, should exist even in flat space-time with no dynamics. So at the holometer, we tried to tackle a new phenomenological regime. Here, the y-axis is mass m, or inverse mode localization. The x-axis is system scale. And here we have a black hole. And here is a single quantum. We typically have LHC events here. And when you try to do UV completions like string theory, you go in this direction. And the paradox, the infrared paradox that I just mentioned for Cohen, Kaplan, Nelson is on this bold line. And the holometer exists here. This corresponds to the length of, say, a football field changing by 10 to the minus 18 meters. And if you go farther out this line, you get something like, say, the distance from the Earth to galaxy Andromeda changing by a micrometer. So these are really tiny, tiny numbers, but still way larger than the Planck scale as predicted by conventional effective field theory. So we built this thing at Fermilab to probe that regime. It's basically a smaller version of LIGO, designed with help from our colleague Rainer Weiss. But instead of measuring local metric fluctuations in stochastic gravitational waves, we probe similar stationary noise in space-time position, but at superluminal frequencies that are sensitive to both time-like and space-like correlations across the system. And to be precise, we have two interferometers. We measure fluctuation delta L in the arm length L. We take their dimensionless ratio, the strain. We cross-correlate two of them, and we still have a dimensionless quantity, right? And then we Fourier transform them. And the spectrum has now a unit of inverse frequency, which is time. And we seek to get that number down to Planck time. And the reason for this is, say, as a toy model, if you imagine there's one Planck scale jitter per Planck time, but the jitter is delocalized over the entire system scale, L over C, and generating a flat response over that time, then something like that toy model would give you a variance that scales like a random walk, Planck length times L, or alternatively, a power spectral density of Planck time multiplied by a bandwidth corresponding to the inverse light crossing time. Okay. And to get this kind of sensitivity, and our instrument is shot noise limited, to get there, we isolate the two interferometers meticulously and monitor only all the correlations between their noise in real time. If the noise is uncorrelated, we can time integrate the cross correlation, average away the noise, and extract only the coherent signal. So we got there. Each of these data points is an independent data point, and the right-hand side at 100 kilohertz, the uncorrelated noise is averaged down over 2 times 10 to the 11 independent measurements. And you can see that in units of strain, dimensionless strain, we reached an upper limit about a quarter of a Planck scale. So that's pretty good. What does that exactly tell us though? We should think of this as an exact verified symmetry. Like Michelson verified the frame-independent speed of light before Einstein's relativity. In this first experiment, all the light propagation was along two orthogonal directions in light-light directions from the beam splitter, following the boundary of a causal diamond. So perhaps this structure is in exact symmetry. So for the second generation, instead of looking at translational fluctuations, we decided to test models that are on these covariant structures. So correlations must be along these causal surfaces, and for example, transverse ones with rotational symmetry around the light cones. And by the way, this is not a new idea. Wheeler prefigured circa like 1950 that in a theory of quantum gravity, we should be dispensing with the concepts of space and time and take world lines and light cones as our basis. Okay, so we built a second experiment to test rotational fluctuations on light cones. We bent one arm to give a rotational response. We carefully did not touch anything else so that we can use the first generation detector as a null test. And we got the device sensitive enough to capture angular fluctuations around one axis at the level where a Planck wavelength wave would be diffracted. Pretty far away from the old days of Albert Michelson here. And this is the first ever measurement of rotation at this level of sensitivity, especially at superluminal frequencies. This time with it even more averaging than before by about 1.5 times to get to the same 1/4 Planck time sensitivity. And yeah, you guys have no idea how hard it was to take 1,100 hours of data, keeping the interferometers barely stable in the quiet dead of the night. Okay, so, and then here are our limits on the major noise correlations that might contaminate our data. Laser noise was measured in situ, and the electronics noise was measured ex situ with white optical noise injected for about 745 hours. And you might notice that the noise levels kind of get up there with the statistical limit of the interferometers. But what you want to actually focus on is the chi-square down here. Numbers above 3 indicate a detection of correlation at 95% confidence level. And you can see that there are only a few of those points, and those points have been vetoed out. Okay, so where do we go from here? There's actually been a lot of lessons since we started this project. And here are some of them on the theory side. I obviously can't go over all of them, but I highly recommend you read them. Especially the recent paper by Banks and Zurek is just a beautiful, stupendous paper. But basically, a lot of these converge towards the same conjecture that all causal horizons are universal boundaries of coherent quantum information, where the decoherence of space-time happens for the observer. For example, there is the Gerald-Tufts models of black hole information, and where he takes a particle on the horizon and calculates the gravitational frame dragging and back reaction from it. And that puts the entire horizon into a coherent quantum object. And Verlinde and Zurek have taken that and using topological black hole coordinates, mapped that onto that same angular correlation across the horizon onto causal diamonds in flat space. And they showed the same random walk scaling of Planckian fluctuations as probed by the holometer. And that same scaling of Planckian degrees of freedom is actually found in the holographic space-time framework of Banks and Fischler, where they say that all causal diamonds are their own Hilbert spaces, and then by saying intersecting or nested causal diamonds are tensor products or subspaces, they construct locality from scratch. Okay. But for now, a nice heuristic way to think about this is to just say, let's look at the coherent quadrupolar distortions needed for a black hole horizon of radius r equals C tau to radiate at the standard Hawking flux. And it gives that the strain in R should be T Planck time over tau. And the claim is that the fluctuations of this scale must exist even on causal diamonds in flat space, which are conformal killing horizons, because the thermodynamic behavior of black hole horizons applies equally to Unruh horizon entropy in accelerated frames. And this coherence across the horizon gives rise to an estimate way larger than the conventional effective field theory here by a ratio of tau over TP. And we actually find that the characteristics, okay, before we get to that, actually, so to model what this looks like in terms of real world data, I've gone back to slide 11 from the past, and let's remind ourselves of the symmetries that we were working with. Okay, and then let's say light cones are coherent quantum objects. And then so there's the boost degree of freedom, and then the boundary of a light cone is actually a two-sphere. So they have two transverse degrees of freedom. And we'll note that this is actually Dirac's light cone function for relativistic quantum commutators, which has a sign flip at the origin, just like the 2th black hole models do if you read those papers. If we just write down a stupid simple toy model of commutators between null vectors that are stuck on the surface of this light cone, and then remember that we're supposed to have decoherence happen when you cross the boundary, the closed boundary of these causal diamonds. You take that model and we find that actually the characteristics of this model match some really well-known CMB anomalies really quite well. So they show us some very tantalizing potential clues. For example, the odd multiples dominate up to about this number. And the 2-point TT correlation function is exactly 0 at 90, down to a few microkelvins out of thousands. And it kind of flips right around that point symmetrically and both those characteristics are as if TOOF's models of black holes were mapped onto the inflationary horizon, except just inverted. And it's not just one anomaly. There are tons with pretty low p-values. And at some point, we might want to look for a common explanation for many of them. So from all these lessons, we've designed an experiment that we think finally has the correct geometry to find the signal. The main idea is that we have to entangle all 3 dimensions. For example, here we're going to measure 2 orthogonal rotational axes and we think that they will correspond to incompatible observables that do not commute with each other. And this design can be tested at an experiment that is currently being built by our colleagues at Cardiff University. And I'm presently working on modeling signal spectra for these geometries that I've designed. The theory manuscript is forthcoming. And these are the people who funded us for the first 2 experiments. And please contact me if you're interested in any of our future endeavors. Thank you.
Thank you very much for a very interesting talk. We have time for questions. If there are no other questions, I would like to let us say, remark. It seems to me that one of the first Joe Weber detectors was installed in Argonne laboratory just near Chicago. Is it correct?
Sorry, could you repeat the question?
One of the first Joe Weber detectors was installed in Argonne laboratory near Chicago.
What kind? Sorry, I
bar detector, Joy Weber.
Oh, yes.
So many years ago, ancient times, for you.
Yes, no, I am aware of that. Yes.
So, but it's that is where this site is just near Chicago, but in suburbs. Where is this location?
Yeah, I've heard about. Yes. Yeah.
Okay. And other questions? Okay, if not, let us thank speaker again. Thank you very much. It was very interesting. Thank you. The next speaker is Любовь Panasenko about gravitational waves. Are you ready? Okay, good. 17 minutes for talk and 3 minutes for questions and remarks. Please start. Please unmute.
Yes, yes, I'm here. Do you hear me? Do you see my presentation?
No, it's fine.
Mm-hmm. I'm going to tell you about gravitational waves over arbitrary background. This report is based on the paper. We are in progress to publish it in the journal, but now it is just a e-print. I will start with a little introduction, what gravitational waves are, its sources. After that, I make brief remind how gravitational wave equation is derived. For simple example, flat space-time, Minkowski space-time. And after that, show you results of derivation for arbitrary space-time, excuse me, in the first perturbation order, and check this result for Friedmann space-time, and list some applications. Gravitational waves are metric perturbations, which are propagated at the speed of light. Background space is defined by metric tensor, which is connected with a space-time interval by this formula, where repeated indexes implies convolution. So in the linear approximation, there is usually this form, background metric and little perturbation, h mu nu, which is more smaller than unity. So when we have systems with asymmetric accelerations, we have generation of gravitational waves. For example, it can be colliding galaxies or collapse of compact objects, binary objects, black holes, neutron stars, and so on. Also, asymmetric supernova explosion can generate gravitational waves, pulsars with non-spherical shape, and interesting source of gravity waves can be cosmological inflation epoch. So in this case, we can speak about relay gravitational waves, which haven't been experimentally detected yet. But we can stop here a little bit more and talk about two stages in theory. There was firstly Parker theorem, which speaks that conformally flat non-stationary universe can't produce massless particles with non-zero spin because equations are conformally invariant. But Grishuk in 1974 showed that in fact field universe impose some non-conformally invariance in graviton equation. So conformally flat expanding universe can produce gravitons during inflation epoch, for example. I want to finish introduction, and next part of report is gravitational wave equation derivation for flat space-time, where we have metric which has this form. It is diagonal metrics. So we can write Einstein equation, general equation for where R mu nu is Ricci curvature tensor, which can be expressed through the second derivatives of metric tensor. R is scalar curvature, it is the trace of Ricci tensor, and T mu nu is energy momentum tensor. For flat space-time, we have this ratio. So this is Minkowski space-time and perturbation. And if it is vacuum solution, T mu nu is equal to 0. And from this equation, we go to this simple equation where square means D'Alembert operator. So since H mu nu is symmetric, we have only 10 independent components from 16, but after calibration, it is possible to make 0 also 8 components, so only 2 components left. It is orthogonal modes, which are illustrated in this picture. As I said, there are some conditions to fix gauge, which helps to calibrate our field and make solution simple. This form. So the first condition which is imposed, it is traceless. And the second, after using Fock harmonic gauge, so we introduce some boosts for coordinates. So tensor will change using this rule. And in this case, we have a simple connection between Ricci tensor and in harmonic gauge, we have this condition, which is equivalent to this one. And since we have H equal to 0, it goes to this one. So we have transversality. That's all about this example. I showed it in order to simplify understanding next section about new result. We derive equation for gravitational waves in conditions that they are arbitrary space-time, and more general case that background moment energy momentum tensor isn't equal to 0. So we can write total Einstein equation where bar means full quantities. So it is background values and the first order perturbations. So here, using definition of Ricci tensor, we can derive this equation in the first perturbation order, and accurately writing equation for scalar curvature, also neglecting some terms which are more than the first perturbation order. We have this one result. What else we have? We have the right side. And here I want to emphasize to make remark that conventionally it is assumed that the first perturbation order for energy momentum tensor with mixed components, mixed indexes is equal to 0. But it doesn't mean that if we use two down indexes, this correction is equal to 0 too, because if you write correctly, we see that there is an extra term which can be rewritten through Ricci tensor. So using this equation and equations that I showed below, we go to final equation for arbitrary space-time. It is interesting that this term doesn't vanish in the zero frequency limit. So for some tasks, this term can essentially change solutions. Now we can also check this result for generally accepted and described in more in many books and articles, Friedman metric. So in Friedman-Robertson-Walker-Lemaitre spacetime, we have this metric, and Ricci tensor is proportional to metric tensor, so it is proportional to Kronecker symbol, and we have this result that this term is proportional to trace, which is equal to 0, and this term vanishes in this case. And we achieve a conventional equation, which can be rewritten in this form. Dot means a derivative over time, and this is Laplace operator. Now it is interesting to list some possible applications of the new result when we have the third extra term. When we consider, for example, density perturbations, they consequently, we have deviation of the metric from Friedman space-time, and if we consider, for example, cloud of isotropically distributed matter, and using and we'll use Schwarzschild-like isotropic coordinates, we will write an interval like this using f1 and f2 functions of time and coordinates. We will see that Ricci tensor has not only the term which is proportional to Kronecker symbol, also there is another one term. So the third term in the equation isn't equal to 0. Another possible application, another example is collapse of dust-like matter, also known as Tolman solution, where we also have this term not equal to 0. And more exotic one example, it is perturbations of the inflation field, which also generates deviation from Friedman space-time. So to conclude my report, I want to say that we derived equation for gravitational waves propagating over arbitrary space-time. And in the future, and this work is in progress, we want to consider graviton to photon conversion for different frequency limits in external magnetic field in order to maybe explain lack of really gravitational waves because of this conversion. That's all. Thank you for your attention. Do you have any questions?
Okay. Questions?
Hello, can I ask you?
Sure.
Which kind of arbitrariness do you consider? Say, for example, if we consider the space-time generated by the infinite sized domain wall or cosmic string, also infinite with infinite length, they have space-time areas which are not asymptotically flat. Does your solution work for these space-times?
We can consider not asymptotically flat solutions, but it is important to remember about this one term, the first T menu, this one. For example, if you will consider some anisotropic stresses and so on, we have to add extra terms here. That's all that I can to say.
No, I mean not just to
obtain some equation, what you have, like Lichnerovich equation on the arbitrary space-time, but I mean some conceptual problems with the emitted wave state in the boundary of the space-time.
Could you please repeat your question? Do you understand you correctly? You ask if we concentrate on this problem and try to solve them using our approach. Do you understand you correctly?
No, okay. For this equation, you have some field H mini, which asymptotic should it satisfy on infinity? No, says spatial infinity. No, for concreteness, if we have the infinitely length cosmic string. I mean that direction in the direction of the cosmic string. It is not asymptotically flat near the string on the spatial infinity. Does this equation work in this space-time? It is not just the phenomenological problem. I will have a talk after you, and I just use some known formula for the graviton emission, but I am not sure that I do correctly everything.
I'm not not sure that my answer will be correct, but for this derivation, we only use Einstein equation, and if it works for strings, I'm not sure. Our result is correct.
Okay, it's just one remark, some general remark. Let us organize our session. So if you want to ask question, please raise your hand and please formulate your question, let us say, as short as possible and short answer. Otherwise, it will be some discussion. There is no time for discussion, sorry. But also I have some, let us say, question. Did you define small parameter? You are saying that you consider first, let us say, order perturbation. What do you mean first order? You have to define small parameter. What is it?
Small parameter, h mu is a small parameter. So
it's dimensionless. It has to be dimensionless.
It depends on definition of h mu. So to the scale factor, maybe it can be normalized.
Okay, it has to be some typical range in this case. It's because always a small parameter has to be dimensionless. But it's also some general question about, you said some metric, your term is important for let us say black hole solution, something like this. But usually gravitational waves are propagating in respect to, let us say, cosmological solutions. What about, let us say, room for your for applications? Because always, as I could imagine, so always gravitational waves propagating in respect to cosmological solutions. Is it correct?
May I make a comment? I don't know how can I raise the hand.
Okay. It's in this case, I will answer first. Alexander Dmitrich, excuse me.
It is not
first,
a question.
reaction, and after that reaction.
First of all, H is dimensionless, and it's supposed to be much smaller than unity. Second, we consider propagation in arbitrary space-time,
And without it is didn't study the production. It's a separate question, but simply how they propagate if background is fixed. It is not necessarily Friedman. Usually, you're absolutely right. Usually, people consider what is this? Conformally flat space-time. It many simplifies, but it's possible to consider any other. And for example, Luba presented an example of non-Friedman corrections. So that's not much thing. It's just formal expansion, and you see if there is deviation from Friedman expansion, there is an additional term, which is almost similar to mass in the sense that low frequency doesn't disappear. Okay, sorry for interruption.
No, it's okay, it's fine. But thank you for answer. But also just for, let us say, for organization. If you wanted to raise hand, please press reactions and after that raise hand. That is for all people, because otherwise it will be disorganized. Thank you very much for your talk. It's very interesting.
Thank you.
Thank you. Next speaker is Professor Gratz. Is it here? I do not see him.
Professor Gratz for today is me. We have the common talk.
Joint work. Okay. Okay, 17 minutes for talk and 3 minutes for questions. It's who is this? Spirin?
Yes, Pavel Spirin.
So, but you will have next talk or not?
Yes, of course.
Okay, good. Go ahead. For this talk, 17 minutes and 3 minutes for questions. Go ahead.
Yes, we discussed some kind of the potential with zero width. Could I talk?
Yes, of course. Go ahead.
We consider some kind of potentials with zero width or zero range in some notion. The motivation of our talk was originally cosmological. We considered the cosmic string with just a minute. Do you see my presentation?
Yes, we see.
Okay. I try to push a button, return to the conference.
Okay, it's okay. It's go ahead. It's not full screen, but it's if you could show it, it's okay. It's fine. What's happened?
Just a moment. Just a moment. Do you see the slide table of contents?
Yes.
Okay. So originally we considered the vacuum polarization near the cosmic string in different dimensionalities, and meet some discrepancies with the literature concerning the renormalized vacuum expectation value for the energy momentum tensor, and the good result with the field square. I mean, we considered the massless scalar field in the background of cosmic string. And the discrepancy for the energy momentum tensor is described by this factor, where C is the conformal coupling. So this discrepancy vanishes for the conformal or for minimal coupling. And after this, we have to consider the wave-like equation for the arbitrary coupling C, and in the some special limit which is here, we encounter the following two equations. First equation is valid for the two-dimensional spatial sector for a cosmic string, and the second one is described by the point impurity in 3 dimensions. So we will concentrate on the problem of the second equation due to we want to work with the quantum mechanical description, and we want to avoid some known problems with two-dimensional quantum mechanics. So we will consider this equation, and it is well known in the literature starting from the 60th years of the previous century, and we try to compute the vacuum polarization for this potential written abstractly here. We will try to do it first. The first approach is considering this potential as arbitrary, and then we set the concrete expression, this one. And second one is also known in the literature approach. It is the self-adjoint extension of the free Laplacian, and we have to compare these two approaches. So start for the first approach. It is the perturbation theory. We consider the potential as some perturbation for the Laplacian. No, or here we have some general form of the perturbation theory for arbitrary field operator L. So these formulae are just the perturbation theory, and in the single loop we meet the Feynman operator corresponding to the free space, and for the perturbation U we will have some Fourier expression in single loop. So in order to compute the quantities we have, the quantities we encounter, we use the dimensional regularization. So we set the basic dimensionality d small as 4, and d capital is the full dimensionality 4 plus some addendum. So we use the standard subtraction procedure. We subtract the Green's function corresponding to the flat space with no potential from the full Feynman propagator, and we compute the Fourier integrals for this. So both the field square and the energy momentum tensor has this form with some different q inside the internal integral. These quantities are listed in this table, and after this we obtain some general formula for the abstract potential U. here. It looks like the solution for the electrostatic potential in electrodynamics, but with different power of the delta R in denominator. So already from this formula, we see that this integral diverges inside the matter. So in order to work with it, we have to suppose that the potential has the compact support and consider the distances far from this potential distribution. For the delta function, we will have this condition automatically due to the support of the delta function potential is just the point. For now, we have no problem with this approach. We will meet them after. And after the computation, which is straightforward, we obtain for the delta potential, which is considered as point impurity in 3 dimensions, we get these two results. And from phenomenologically, we have to point out that the coupling lambda has a dimensionality of the length, and our perturbation theory implies that we work for large distances r much larger than the inverse lambda. The second, and here is the result for arbitrary c for lambda independent from the conformal coupling c of the scalar field. Now go to the second approach, which is self-adjoint extension. We factorize the time dependence as exponential in common way. After this, our field equation becomes the static quantum mechanical equation for the eigenvalues. Omega square is to be the eigenvalue of this Hamiltonian, and we decompose the Laplacian according to the basic quantum value L and split it on the direct sum after in a common way. After this, we find that only the L equal to 0 case has non-zero defect. So when we sum up over the modes and when constructed the renormalized Hadamard function, we have to also to subtract the free space modes from our exact ones. After this, only the zero L equal to 0 partial Hamiltonian contributes to this sum. Then we meet the second problem, is that it is the existence of the bound state for the alpha for the negative alpha. In order to avoid this, we restrict ourselves for the positive alpha case. Here alpha is exactly the parameter of the self-adjoint extension. It equals to plus infinity for the free space with no potential, and when alpha is finite, we have some self-adjoint extension. So for the positive alpha, our spectrum is completely continuous, and we have the proper resolution of identity, and we do the computer renormalized Hadamard function. Here it is after the substitution of the modes, which are listed here, which is we have the contribution only of the S wave, which corresponds to the L equal to 0, and after the computation we arrive at the following integral, this one, which can be expressed via the exponential integral function E1 or EI in the mathematical literature. So with help of this function, we compute phi square and the vacuum fixation value for the renormalized energy momentum tensor, and this result is full with no perturbation theory usage. Now we have also we can split the energy momentum tensor on the conformal and anti-conformal part. They have some different scaling according to the power of the distance from the origin. So this the rest is straightforward computation. Now we have the following. For small product of alpha and R, we have this expansion of the exponential integral function, but for large product alpha R, we have another expansion, these ones. Now we can compare two approaches and compare them for large alpha R. We see that if we look backward for the first approach, we find that the result is both results have the same coefficients, but with negative sign. This means that the problem will be solved if we set alpha, which is arbitrary self-adjoint extension parameter, equal to minus lambda. But now we meet the basic problem. For the absence of the bound states, in order to have the potential barrier and not the potential well, we have to have both positive alpha and positive lambda in the first approach.
Excuse me, Pavel. Sorry for interruption. For you spoke 18 minutes. So I could give you 2 minutes if you don't want to do not need questions.
Okay. Okay.
You need questions or not for your talk?
No, it is a question not for me. Okay, I will try to finish in 1 minute.
Okay.
Okay. In order to remove the discrepancy, we have to renormalize the coupling. So originally we tried to don't work with any problematic situation, but and we have no any problem with computation, and but now in order to have matching of two approaches, we have to renormalize coupling. We do it in this way. So if we plot the renormalized lambda and versus the original one, we have to set this quantity and it becomes okay. But now we have the main problem. In order to have the correspondence of two results, we also have to perform the renormalization in the first approach with abstract potential. So this is a conclusion. We compute the vacuum expectation values for the massless scalar field in two frameworks. And we have to renormalize the field strength in both approaches. After this, we can the prospect is our original problem is the two-dimensional point impurity, which corresponds to the real cosmic string, where the limit, the point like impurity arises originally and not as mind game like in the 3 dimensions. That's it.
Okay, thank you. Unfortunately, we have no time for questions. Next talk, please. But
okay.
you used 2 minutes from your time from next question, next talk, because
okay.
you were speaking for 22 minutes. Okay, go ahead.
Okay, the second talk is, as I said in the question, related with the graviton emission in the just a moment, in the space-time of this one, in space-time of the infinite cosmic string. We consider the Bremsstrahlung and the scattering of the point-like particle in the background of cosmic string. The cosmic string is supposed to have infinite length and infinitely small width. For the real cosmic string, we have to consider the restriction that the impact parameters should be larger than the diameter of cosmic string, which is estimated as 10 to the minus 29 centimeters. So we start with the metric. The cosmic string produces the space-time with the angular deficit, which is described by the parameter vita, and 1 minus vita becomes the angular deficit. So if we compute the curvatures, it turns out that the space is free outside the string and have delta-like singularity on the location of the cosmic string. So in order to work with the angular deficit, we introduce the complement y minus beta, and it is related with the string extension μ and Newton's constants g. In order, we consider the interaction of the cosmic string with the point-like particle. For now, we consider this particle as spinless. So the particle produces some Schwarzschild field, and we have originally perturbation theory. Our perturbation theory over the gravitational constant g eventually becomes the perturbation theory with respect to the dimensionless parameter b over the Schwarzschild radius Rg. B will be the impact parameter. So the action is this. It is just the gravitational part. This is the strings action. Here is particle action, and the Einstein's gravitational field for the interaction. In the second part, we also consider some scalar field in order to explain, in order to introduce some wave emissions. So for now, we have just Einstein equations and equations of motion for both particle and string. The first part of the work is the elastic encounter of the string and particle. The motion of particle in the field of cosmic string is well known. We just reproduce it in our Cartesian coordinates, but the main part of the first half of my work is the reaction of a string on the particle flight. In fact, we use the perturbation theory over the small ratio of gravitational radius over impact parameter. In zeroth order, we have free particle and free string. So the string is straight and aligned with the x-axis, and particle moves along the z-axis. So the y-axis is the impact parameter vector. In the first order, we have linearized fields generated by linearized gravitational fields generated by particle, this one, and by string, this one. So this is well-known solutions, and interaction is constructed in the sense that the particle moves in the linearized field of the string, and string moves in the background of the Newtonian field by particle. So after this, we solve the equation of motions for the particle and find this trajectory. This trajectory describes the well-known property of the cosmic string background is the gravitational lensing. Let me show the plot of it in just a moment. Here, all parallel particles have the same deflection angle, which directly proportional to the angular deficit of the cosmic string. Now we go to the solutions for the string's excitation. Here we have the wave-life equation for the deflections. The first order x is the string's deflection, and we have the gauge where we have only two fields, two transverse field for the deflection in z direction and in y direction. We have this Fourier-like solution for them, and computing this, I have to omit the details of contour integration. We find that both amplitude consist of two constituents. The first one is related with the integration over the cut of the branch points, and the second one is related with the poles of this integral. So after this, we have to compute these two integrals. They are not so huge. We find the following: the amplitudes for y direction are computed exactly, with no problem. They are finite, but both z amplitudes diverge logarithmically in infrared, and we have to impose some dimensional regularization to compute these integrals. After we do it, we have some finite result. Remarkably, the dimensional regularization happens firstly inside the internal integral, and then integration, the subsequent integration becomes finite. After this, we have to check that our solutions are good. Here I summarize the results. The constructed solutions are continuous with respect to both time and x. X is the coordinate along the string. They satisfy the equation of motion. They reflect the causal structure. They vanish in the limit of where particle is at rest, and the characteristic length parameter of the deflection is just the gravitational radius constructed from the energy of the particle. Gravitational radius of the particle constructed with respect to energy. So it is tiny, of course, for particles, but probably the computation of this effect for the beam, say, may give some multiplicity of this effect. So here are the plots of the string. Both solutions phi y and phi z has some wave-like solution. So in the string we have two waves propagating along it. Both waves are superluminal and both are transverse. So here we have the profile of the transverse perturbation along the impact parameter vector, and you see that the string with time string have this profile, and then this part goes to this asymptote. So in the infinity, eventually all the string moves from this initial position to this finite state. Okay, I meet this formula, and here the deflection with respect to the z. Z is the direction of the particle motion. So it also have wave-like solution. The apex goes from the center of the string, which is the closest proximity to the particle's trajectory, and the wave goes outside the string in both directions, plus and minus. Okay, here is the profile in that direction. The string originally was aligned with x-axis, and when particle goes, the particle goes, the string has this kind of deflections here, and then after the yellow state, it also has two waves which propagate to the vicinity of the string from the center. Okay, so we have if we compute the phase trajectory for both y and z axis, so eventually string from this one goes to this. Okay, now the second part is the inelastic encounter. We go beyond the first order, and we compute the gravitational emission due to this encounter. So we compute the Bremsstrahlung. In order to don't work with the tensor ones of gravity, we introduce some massless scalar field, which approximates both the gravitational Bremsstrahlung and electromagnetic. So in fact, we will have also the gravitational interaction due to the particle is the only one charged partner. So we use this well-known formula for the scalar emission, and we have just to compute this source J. In the presence of gravitational field, it consists of two parts. the first is row is just variation of the right-hand side of field equation.
Excuse me, Pavel, sorry for interruption. You have 1 minute more until the end of 40 minutes. One minute more.
Okay, so we know any approximations further. We compute this amplitude, radiation amplitude, and after it has this closed form, and after this we compute the emitted energy and the partial distributions for the Bremsstrahlung. So for the angular distribution with respect to the angle theta, we have this plot. The characteristic angle theta is the inverse of Lorentz gamma factor. So we have beaming for the ultra-relativistic case. The frequency distribution behaves like this. It is just the falling exponential. And in the ultra-relativistic regime, we can compute the total emitted energy in the closed form. In the generic case, we can interpolate this, the ultra-relativistic regime and non-relativistic, and have this formula where the function xi capital is of order unity. So our results, we have in the first order of perturbation theory, we have computed both the deflection of particle and deflection of string. And for the string, we obtain some wave-like solution along the string. In the next order of perturbation theory, we have computed all the characteristics for the Bremsstrahlung due to single particle. That's it. So, okay, these prospects for the subsequent work, you can read it by yourself. Thanks.
Thank you very much. Unfortunately, we have no time for questions. Thank you again. Next speaker is Professor Mikhail Filchenkov. Please stop sharing your screen. Okay, fine, thanks. "17 minutes for talk and 3 minutes for questions and discussions." Mikhail, are you here?
I can't open screen demonstration. I cannot find my file. Yes. There are some problems.
А вы еще раз запустите. Так обычно бывает.
Вы выбрали не то окно для шеринга.
Нет.
Еще раз PDF запустите, он тогда появится там в списке для расшаринга. Так, по-моему,
Михаил исчез вообще.
Михаил исчез из списка.
Ну, он отключился в Zoom.
Не, ну это часто бывает, что когда сначала файл запущен, то его не видно, а если его еще раз закрыть и запустить, то он виден в списке от того, что можно расшарить из Zoom.
Я боюсь, что он нас не слышит.
Нет, ну вот сейчас.
А, вот сейчас слышит, может быть. Михаил, please unmute yourself first. Михаил, вы меня слышите?
Слышу, конечно.
Ну так вот, зеленую кнопочку Share Screen.
Нажал, да. И теперь
А
я не
потом
могу найти.
выберите окно, где у вас PDF-файл, например, или PPT-файл. После Sharing Screen, когда вы нажмете, он предложит вам выбрать окно.
А, файлы что ли? Так вот я не знаю, как выбрать.
Ну, у вас должен быть открыт этот файл уже.
Ну, конечно, открыт. У меня он открыт.
Ну вот в это окошко войдите и все, в котором открыт ваш PDF или PPT файл.
Да. Да я не могу войти. Сейчас, секунду. Значит так. Нет, ну я должен найти набор файлов и нажать, правильно?
Вы должны нажать на то окно, где у вас находится ваша презентация.
Ну правильно, вот я и не вижу его, этого окна.
Ну, у вас Windows или Linux?
У меня обычный Windows. Я вот смотрю, там экран, там
Вот
изображение.
сейчас, вот вы расшарили запустить конференцию, вы выбрали не то окно для расшаривания, а надо было окно, где у вас лежит PDF-файл. Этот файл расшарить. Это надо стоп-ширинг, стоп-share your screen и снова провести эту процедуру, выбрав правильное окно, где у вас вот ваш экран весь.
Сейчас, одну секунду. Что-то мне не получается опять.
Так у вас файл этот не открыт.
Сейчас открою.
Вот, вы правильно.
А, вот, открыл.
Да, а теперь full screen лучше. Е-мое, отключилось. Такое ощущение, что Фильченков опять исчез из Zoom.
Человек разнервничался и не те кнопки нажимает.
Ну как тут помочь невозможно.
Ведь уже было все.
Здравствуйте, это Максим из Организационного комитета.
Да-да.
Я нашел презентацию профессора Фильченкова. Вот, я буду ее транслировать.
Ну, надо с ним связь.
Да, вот я,
выйти.
как только он вернет, как только вот он
Ну, в
вернется.
смысле, надо ему предложить это, потому что, ну, как он сможет или захочет, это я понимаю, да. Ну,
да, сейчас.
вот, вы знаете, у вас еще такой вопрос. Есть последний докладчик с индийской фамилией Баттачарея, но я его не вижу.
Да, сейчас мы с ним свяжемся.
Он здесь вообще или нет? Он знает, что он должен рассказывать?
Вот мне показывает, что он знает, что он должен. Вот,
но его не вижу.
Но его не видим, да. О, Михаил вернулся.
Ну, задайте ему этот вопрос, Михаил.
Да, конечно.
Спасибо.
Сейчас, Михаил, включите, пожалуйста, микрофон. Я вот...
Михаил опять исчез из видимости, зоны видимости. Михаил, пожалуйста, включите микрофон. Unmute yourself. First. Ё-моё, что ж такое? Михаил, прежде всего, unmute. Включите микрофон. Вам организационный комитет вопрос хочет задать.